When I was a boy, I spent all my spare time searching through rocks in places like this. Over time, I began to learn something about the Earth's evolutionary history. By and large, it's a story of slow, steady change.
In the beginning, before there were planets, oceans, or even the faintest spark of life, there was only a quiet cloud of gas and dust drifting through the darkness of our galaxy. A cold and silent nebula made of hydrogen, helium, and the scattered ashes of ancient stars. It floated for millions of years, undisturbed, until something changed. Perhaps the passing arm of the Milky Way compressed it. Perhaps a nearby supernova sent shockwaves rippling through space. Whatever the trigger, the effect was profound. Gravity began to pull the nebula inward, slowly at first, then with increasing force, drawing the cloud into a tight, spiraling collapse. This was the beginning of the Sun, and with it, the beginning of Earth. As the nebula contracted, particles collided, releasing heat at the center of this swirling cloud. Mass accumulated, forming a dense and warming core. Over time, this core grew hotter and heavier. Pressure increased until hydrogen atoms fused into helium, igniting the fire of nuclear fusion. The light switched on. The Sun was born. Its brilliance flooded the nebula, clearing out leftover gas and setting the stage for the formation of planets. Around the newborn Sun, a disk of debris took shape. Astronomers call it the protoplanetary disk. To the early universe, it would have looked like a glowing ring of dust, rotating slowly, holding within it the ingredients of future worlds. Dust grains, no larger than smoke particles, drifted through this disk. When they collided, they stuck together through electrostatic forces. At first, these collisions were gentle, almost delicate, but over tens of thousands of years, these specks gathered into larger clumps. Millimeter grains became pebbles. Pebbles became stones. Stones became boulders. Slowly, the architecture of a planet began to emerge. Gravity, even in its weakest forms, is endlessly persistent. Once a clump grew large enough, its gravity pulled in more material. These growing bodies, called planetesimals, orbited the young Sun in chaotic paths. They crashed into one another, fused, fragmented, and fused again. Each collision released heat, melting parts of their surfaces. In these moments, chemistry began to change. Metals separated from silicates. Molten cores formed within the larger bodies. The early solar system was a violent place, ruled by impacts and constant rearrangement. Earth's story began with one of these planetesimals. It was not yet the blue world we know. It had no oceans, no continents, and no atmosphere. It was simply a growing sphere of hot rock pulled together through relentless collisions. As it expanded, gravity became stronger, drawing in more material from the disk. Millions of impacts sculpted its surface. Some were small and barely noticeable on a planetary scale. Others were catastrophic, releasing enough energy to vaporize rock and reshape the planet entirely. Although we imagine planets as stable and solid, the early Earth was anything but. Its surface was molten, forming vast oceans of magma. The heat came from three sources: leftover energy from its formation, the constant rain of impacts, and the decay of radioactive elements buried within. Together, they kept the young planet glowing like an ember in the cosmic dark. While Earth was forming, so were the other planets. Closer to the Sun, Mercury and Venus grew in similar ways, though each developed a different fate. Farther out, the gas giants accumulated enormous atmospheres. But Earth remained in a delicate balance, close enough to receive warmth, but far enough to avoid vaporizing entirely. It was positioned in a region scientists call the habitable zone. At this stage, habitability was a distant promise, not a reality. Yet, the conditions for a future life-bearing world were beginning to take shape. In the swirling disk, turbulence sculpted rings of material. These rings fed the growing planets. Within Earth's ring, icy bodies from the outer solar system occasionally plummeted inward, delivering water in the form of vapor and frozen minerals. Long before oceans existed, the ingredients of water were already being incorporated into Earth's interior. As Earth grew, gravitational interactions altered the orbits of surrounding planetesimals. Many were pulled inward and collided with the forming planet. Others were ejected outward. But one collision would change everything: the impact that formed the Moon. Before that event, Earth was still incomplete, still undergoing the final stages of assembly. In the early solar system, instability was a natural state. Multiple planetary embryos, some as large as Mars, were moving through intersecting orbits. One such object, often referred to as Theia, existed near Earth's orbital path. Over time, gravitational forces nudged their trajectories closer. The solar system did not yet have the quiet predictability we see today. Theia and Earth were on a collision course, though it would take millions of years before their paths finally crossed. Meanwhile, Earth's accretion continued. Each new impact brought fresh material, metals, silicates, gases, all mixing into its growing mass. Its interior was now layering. Dense iron and nickel sank toward the center, forming the core. Lighter materials rose toward the mantle and crust. The dynamo that would one day create Earth's magnetic field was beginning to stir. This field would eventually protect the planet from solar winds and radiation, making it more hospitable for life. But at this early stage, the field was still weak, fluctuating unpredictably. The formation of the Sun also played a critical role in shaping Earth. In its youth, the Sun was far more active than it is today. It emitted powerful solar winds, streams of charged particles that swept across the solar system. These winds blew away much of the remaining gas in the protoplanetary disk. They also stripped atmospheres from many small bodies. Early Earth's first atmosphere, mainly hydrogen and helium, was likely blown into space. Yet this loss would become a necessary step for the formation of a second, more stable atmosphere produced by volcanic outgassing later in Earth's history. As the solar winds cleared the disk, the era of planet formation began to slow. Fewer collisions occurred. The environment stabilized. Earth had become a roughly spherical planet with a molten surface. Its interior churned with heat. Its exterior glowed with incandescent lava. Though destructive, this period was essential. The molten surface allowed heavy metals to sink and lighter silicates to rise, creating internal structure. Differentiation, as scientists call it, is a key process in forming planets capable of supporting complex geology. The solar system was now taking recognizable form. Jupiter, the giant, dominated the outer regions. Its immense gravity influenced the movement of countless objects, shaping the asteroid belt and protecting the inner planets from excessive bombardment. Mars formed smaller than Earth due to Jupiter's gravitational interference. Venus became similar in size but followed a different evolutionary path. Earth occupied the middle ground, a place of balance. Meanwhile, the planet continued to cool slowly. The surface began forming a thin crust, though impacts frequently shattered it. Beneath the crust, magma surged upward in plumes. Volcanic activity was immense. Gases trapped in Earth's interior, water vapor, carbon dioxide, nitrogen, sulfur, were gradually released into the sky. These gases formed Earth's second atmosphere, far thicker and more hostile than today's. Yet this atmosphere would eventually lay the foundation for life. In the silence of space, Earth rotated rapidly, completing a day in only a few hours. The Moon, after its formation, would slow this rotation, but that moment had not yet arrived. The young planet spun with tremendous speed, generating strong atmospheric currents and violent storms across its molten landscape. Lightning arced through the thick clouds, contributing to chemical reactions that would later be important for organic molecules. But for now, Earth remained barren. Still, change was constant. The solar system was evolving alongside it. Comets, made of ice and rock, continued to bombard the inner planets. These icy visitors contributed water and other volatile compounds. Although the source of Earth's water remains debated, many scientists believe a significant portion arrived during this period through millions of impacts, droplets of water mixed into the crust and mantle. Once the planet cooled enough, this water would eventually rise to the surface, creating the oceans. As the bombardment slowed, the sun's brightness increased. Young stars brighten gradually as they age, and the sun was no exception. The increase in energy began to influence Earth's climate. Though still molten in many places, some regions started to solidify. A more permanent crust formed, though it remained thin and unstable. Tectonic processes were beginning, driven by internal heat. The groundwork for future continents was being laid deep within the planet. Though we often think of planets as forming quickly, Earth's birth required tens of millions of years. The timeline is immense. Yet, in cosmic terms, it was rapid. From a cloud of dust to a glowing molten sphere, Earth's transformation was guided by physics, chemistry, and gravity. Each step brought it closer to becoming a world. Then came Theia. The collision itself belongs to the next outline, but its approach was already influencing Earth's orbit. Gravitational interactions destabilized both bodies. Their paths spiraled toward each other. Soon, the impact would reshape Earth forever, giving rise to the Moon and altering the rotation, tilt, and internal structure of the planet. It would be the final major event of Earth's formation. And so, the stage was set. The sun burned steadily at the center of the new solar system. The planets orbited in their new paths. Earth, still young and molten, awaited the collision that would transform it. What began as dust in a collapsing nebula had become the foundation for a future world. A world that would one day host oceans, continents, forests, and life in all its diversity. The birth of Earth is not just a geological story, but a cosmic one. It reminds us that everything around us, the air we breathe, the ground beneath our feet, the water we drink, even our own bodies began as particles drifting in the dark arms of the Milky Way. Through gravity, heat, and time, these particles assembled into a planet unique in the solar system. The journey from stardust to world was long, violent, and beautiful. Earth's story has only just begun. Earth, newly formed from collisions and cosmic debris, was still far from the stable, life-bearing world we know today. In this early chapter, the planet existed as a seething, violent sphere, wrapped in fire and chaos. The surface churned with molten rock, the interior boiled with radioactive heat, and the sky was nothing like the blue dome we see now. Instead, thick clouds of vapor, dust, and volcanic gases swirled into a dark and alien atmosphere. Lightning ripped through the sky constantly, illuminating a world dominated by destruction and transformation. This period is known as the Hadean Eon, named after Hades, the ancient realm of fire, and the name is appropriate. Earth's surface was a global magma ocean. Continents did not exist. Oceans had not yet formed. The crust was thin, fragile, and constantly broken by impacts. Volcanoes erupted across the entire surface, releasing immense plumes of gas and lava. The atmosphere was thick with carbon dioxide, nitrogen, sulfur compounds, and water vapor. No oxygen, no stable climate, and no conditions suitable for life. But despite this hostility, the groundwork for everything that would come later was being built. The young sun shone dimmer than it does today. It emitted strong solar winds, powerful enough to strip away the first atmosphere Earth had briefly held. This early atmosphere likely consisted of hydrogen and helium, remnants from the solar nebula, but these light gases were blown into space by the newborn star's radiation. This loss created room for a second atmosphere, one that would form from volcanic outgassing and cometary impacts. Earth's formation had generated enormous heat. Gravitational compression, radioactive decay, and the energy from countless collisions kept the interior molten. Within the planet, heavier elements like iron and nickel sank inward, forming the core. Lighter silicates rose to form the mantle. This differentiation released even more heat, contributing to convection currents deep within. These currents would eventually drive plate tectonics, but in the Hadean, the crust was far too unstable for organized plates. Instead, the surface constantly melted and reformed, never remaining still long enough to build lasting geological features. Comets and asteroids still bombarded the planet regularly. Though the heaviest phase of accretion was ending, the solar system remained crowded with debris. Each impact tore open the crust, ejecting molten rock into space and reshaping the surface. Some impacts vaporized entire regions, sending shockwaves across the planet. Others delivered new materials, including water-rich minerals that would play a crucial role in Earth's future oceans. But at this stage, the planet could not hold liquid water. The surface was too hot, and any water instantly evaporated, joining the thick, steaming atmosphere. Volcanic activity was ceaseless. The mantle churned beneath the thin crust, pushing magma upward in colossal floods. Volcanic gases filled the atmosphere with carbon dioxide and water vapor, creating an early greenhouse effect. Without this, Earth may have remained frozen once it cooled, since the young sun emitted less heat than today. Instead, the greenhouse atmosphere trapped warmth, keeping the surface extremely hot but dynamically evolving. Lightning storms were constant. Charged particles in the dense atmosphere created electrical imbalances, producing frequent strikes across the molten landscape. These storms may have contributed to early organic chemistry, though life was still far in the future. For now, these reactions were simply chemical experiments occurring in a hostile environment. The sky, thick with ash and gases, glowed red and orange from the reflection of molten lava. The horizon flickered with eruptions. Meteor trails cut through the atmosphere, leaving brief streaks of fire before exploding on impact. Each collision added to the intense heat. The crust, already fragile, often collapsed back into the mantle, recycling newly formed minerals and preventing the permanent creation of continental rock. In this dynamic world, nothing lasted long. Beneath the surface, the core continued to form. The inner core became solid, while the outer core remained liquid. This layered structure created the beginnings of Earth's magnetic field. Though weak at first, the field was crucial. It began protecting Earth from some of the sun's harsh radiation, preventing complete atmospheric loss. Without this magnetic shield, Earth might have ended up like Mars, stripped of its atmosphere and oceans. But even in this early stage, the seeds of protection were taking shape. The violent conditions of early Earth were not unique. Other planets in the solar system also experienced early bombardment and volcanic activity. But Earth held a special balance of mass, composition, and distance from the Sun. This allowed it to retain heat long enough to form a magnetic field, but not so much that it became a perpetual magma world like Venus. It retained volatiles like water, carbon, and nitrogen, while still avoiding the fate of gas giants. This balance would prove essential in the coming eons. As millions of years passed, the intensity of impacts gradually decreased. Large planetesimals were now rare. The crust began to cool slightly, forming thicker patches of solid rock. Though still unstable, these early proto-continents represented the first steps toward a more structured surface. Volcanic activity provided fresh minerals and gases, building a complex chemical environment. During this time, gases released from volcanoes formed what scientists call Earth's second atmosphere. It consisted mostly of carbon dioxide, with smaller amounts of nitrogen, methane, hydrogen sulfide, and ammonia. Water vapor was abundant, creating a thick, humid blanket around the planet. When Earth finally cooled enough, this vapor would condense into rain, but that moment was still far away. The Hadean world was shaped by energy in every form: heat from the interior, radiation from the sun, kinetic energy from impacts, and electrical energy from storms. These forces constantly sculpted the surface and atmosphere, ensuring that Earth remained dynamic. This energetic environment allowed complex chemical reactions to occur, setting the stage for the emergence of life much later. But at this stage, the planet was entirely barren. Deep within the mantle, convection currents shifted molten rock. These currents caused sections of the early crust to break apart and collide. Some regions thicker than others may have briefly existed as proto-continents, only to be melted down again by new impacts or massive volcanic eruptions. This recycling of crustal material enriched the mantle with minerals that would later fuel plate tectonics and continental growth. Temperatures at the surface remained extreme, likely above 1000 degrees Celsius. No liquid water could exist. The atmosphere was a toxic mixture of gases, unbreathable and dense. Yet, the greenhouse effect kept the planet from cooling too quickly. If Earth had cooled too fast, it might have become a frozen world, unable to support later evolution. Instead, the violent heat allowed the geological engine to stay active. During this era, a major event loomed on the horizon: the giant impact with Theia. This Mars-sized body had formed near Earth's orbit and drifted gradually into a crossing path. As Earth grew heavier, its gravity influenced Theia's movement. The two bodies slowly approached a catastrophic collision.
Though the impact belongs to the next chapter, its effects on Earth's environment were already building. Gravitational disturbances may have created additional impacts from smaller bodies.
The system was becoming increasingly unstable. Meanwhile, the atmosphere grew thicker with volcanic gases. Infrared radiation from the hot surface was trapped within this dense gas layer, slowing, cooling, and maintaining the molten state longer than expected. The oceans of magma beneath the crust moved in waves, forming and collapsing mountains of molten rock. These flows shaped the early topography, smoothing some regions and raising others. As the crust cooled slightly over time, chemical differentiation began. Minerals with higher melting points crystallized first, forming a primitive crust. Lighter minerals, especially silicates, floated upward, forming the earliest felsic rocks. These rocks were the ancestors of modern continental crust. Though most have long since been destroyed, small traces preserved in ancient zircon crystals reveal that Earth may have formed stable crust earlier than once believed. In this harsh world, the foundations of future oceans were forming in the atmosphere. Vast amounts of water vapor circulated above the molten surface. Storms raged for centuries without pause, driven by the extreme temperature differences between the surface and upper atmosphere. When the planet finally cooled to below the boiling point of water, this vapor would condense, falling as rain for millions of years. These storms would fill the first ancient oceans. But during the Hadean, the world remained too hot for that transformation. The pressure of the atmosphere prevented condensation, keeping water in vapor form. Yet the water collected in the atmosphere signaled what Earth would one day become a water-rich planet, unlike any other in the inner solar system. The Hadean Eon lasted hundreds of millions of years. Throughout this time, the planet underwent constant restructuring. Even the rotation of Earth changed. Early Earth spun faster, completing a rotation in roughly 6 hours. Over time, tidal interactions with the Moon, once it formed, would slow this rotation to the 24-hour cycle we experience today. But in the Hadean, the rapid spin contributed to atmospheric turbulence and extreme weather conditions. Chemical processes also began to establish the building blocks of future life. Volcanic vents released gases that reacted in the atmosphere. Ultraviolet radiation from the sun broke molecules apart, allowing them to recombine in new ways. Lightning provided additional energy for molecular transformations. Though no living organisms existed, Earth was becoming a chemically rich environment with increasing complexity. Beneath the surface, the core continued to grow solid. This inner core formation strengthened the magnetic field, gradually expanding its protective influence. A stable magnetic field is one of the most important features for maintaining life. It deflects harmful solar radiation and preserves the atmosphere. Though still weaker than today's field, the early magnetic bubble helped shield the developing planet during its most vulnerable phase. Earth continued to cool, but slowly. The crust thickened slightly. Some regions may have solidified entirely, forming the first long-lasting pieces of crust. These fragments drifted upon the mantle, carried by convection currents. This movement resembled an early version of plate tectonics, though far more chaotic and less organized. These floating fragments were the seeds of future continents. Through all this chaos, Earth edged closer to the moment that would define its future. Theia approached, pulled by gravitational forces into Earth's path. The impact would obliterate the early crust, reshape the interior, and form the Moon. But even before that moment, Earth's violent beginnings had already set the stage. It had formed a core, a mantle, a crust, and an atmosphere. It had accumulated water and volatile compounds. It had built internal heat engines and magnetic protection. It had survived a storm of cosmic impacts. What emerged from this turmoil was a planet ready for transformation. The Hadean world was not calm or gentle, but it was essential. This violence carved the framework upon which oceans, continents, life, and ecosystems would one day flourish. The newborn Earth was a world of fire, storms, and constant change, but within this chaos lay the hidden blueprint of everything that would follow. Earth's violent beginnings were only a prelude to the most defining event in its early history. Out of all the collisions, out of all the impacts that shaped the young planet, one stood apart in scale, consequence, and cosmic importance. It involved a planetary body, roughly the size of Mars, now known as Theia. This collision would forever change Earth's rotation, tilt, internal structure, and even its destiny as a life-bearing world. It would give birth to the Moon, reshape the atmosphere, and ignite geological forces that persist to this day. Without this single event, Earth would be unrecognizable, perhaps uninhabitable. Theia itself formed in the same protoplanetary disk as Earth, near the region of the inner solar system. Like Earth, it grew from dust, rocks, and molten material drawn together by gravity. For millions of years, Theia likely orbited close to Earth's path. Both worlds grew larger, their gravitational influence expanding. But planetary orbits during this era were unstable, influenced by countless interactions among forming planets and debris. Eventually, Theia's orbit began to intersect Earth's. The two bodies slowly drifted toward an inevitable collision. This approach took time millions of years. Tiny gravitational nudges gradually shifted Theia's path. Both worlds orbited the young Sun in slightly elliptical patterns. With each orbit, they inched closer. By the time Theia finally approached Earth, it was a fully formed planetary embryo, complete with its own molten interior. The collision that followed was one of the most energetic events in the history of the solar system. The impact occurred at an angle, not a direct head-on collision. This grazing strike released unimaginable energy, equivalent to billions of nuclear bombs detonating simultaneously. The force of the collision vaporized enormous amounts of rock and metal from both bodies. Much of Theia's mantle and a significant portion of Earth's outer layers were blasted into space. Molten droplets of silicate rock were hurled outward, forming a hot, glowing debris cloud encircling the planet. The impact reshaped Earth instantly. Its rotation sped up dramatically. A single day may have lasted as little as 4 to 6 hours after the collision. The spinning world bulged at the equator, distorted by the rapid rotation. The axis of rotation tilted significantly, creating the axial tilt that still governs Earth's seasons. Without this tilt, Earth's climate systems would be vastly different, lacking the complex seasonal patterns that help sustain diverse ecosystems today. Beneath the surface, the impact stirred Earth's interior. The collision caused the early core to grow hotter and denser. Material from Theia mixed with Earth, enriching the mantle with new elements. The heat unleashed by the impact created a global magma ocean, resetting the planet's crust. Any proto-continents that may have briefly formed in the Hadean were completely obliterated. The surface became a molten, fire-lit sea of rock. As the debris cloud cooled, particles began to clump together. Gravity pulled molten droplets into larger fragments. Within months or years, a short time on cosmic scales, these fragments merged into a single growing body. This body continued to attract surrounding debris, clearing a path around Earth's orbit. Eventually, it became the Moon. The Moon formed surprisingly close to Earth, likely only 20,000 to 30,000 kilometers away. At this distance, it appeared enormous in the sky, dozens of times larger than it appears today. Tidal forces between Earth and the infant Moon were intense. The Moon pulled on Earth's molten surface, creating tidal bulges of magma. These tides stirred the interior, helping to shape the early crust and mantle circulation. The gravitational interaction between Earth and the Moon slowed Earth's rotation over time, gradually elongating the length of a day. The Moon, meanwhile, drifted outward into a wider orbit. This slow outward migration continues even now. The Moon's creation also stabilized Earth's axial tilt. Without the Moon's gravitational anchor, Earth's tilt might have varied chaotically over millions of years, causing extreme climate shifts that could have hindered the development of stable environments. Instead, the Moon acts as a stabilizer, keeping the tilt within a relatively narrow range. This stability allowed Earth's climate to evolve over billions of years in a predictable pattern, enabling life to adapt and thrive. After the impact, Earth glowed with energy. Infrared radiation poured from its molten surface. The atmosphere thickened with vaporized rock, silicate droplets, and gases from the impact. The sky burned with red and orange hues, illuminated by the molten Earth and the glowing ring of debris that surrounded it. Over time, as the moon formed and the debris cleared, the atmosphere began to cool. Particles fell back to the surface as molten rain, further shaping the planet. The impact also contributed to Earth's chemical and isotopic composition. Studies of lunar rocks show remarkable similarities to Earth's mantle, confirming that the moon formed primarily from Earth's outer layers, not from Theia alone. This shared origin explains why the moon lacks a large iron core. Most of Theia's iron merged with Earth during the collision. The moon is therefore mostly silicate rock, a remnant of Earth's mantle cast into space. As the Earth-Moon system stabilized, new geological processes emerged. The immense heat from the impact slowly dissipated into space. A new crust began to form on the molten surface. Volcanic activity remained intense, releasing gases into the atmosphere. This outgassing helped form Earth's secondary atmosphere, dominated by carbon dioxide, nitrogen, and water vapor. In time, as the planet cooled further, water vapor would condense to create the first oceans. Theia's impact was not simply destructive, it was creative. It forged a double-world Earth and its moon forever linked in gravitational partnership. It established the planetary conditions necessary for long-term climate stability. It helped generate the core mantle dynamics that sustain Earth's magnetic field, a protector against solar radiation. It enriched the mantle with new materials, influencing the chemical evolution of the planet. The moon itself played a crucial role in the development of tides. Even when the oceans had not yet formed, its gravitational pull stirred the molten surface. Later, when liquid water covered Earth, tides would help mix nutrients, drive coastal ecosystems, and influence the biological rhythms of early life. The rhythmic ebb and flow of tides helped shape the environment in which life evolved. Without the moon, Earth's tides would be far weaker, and early coastal life may have developed differently. The impact also had long-lasting consequences for Earth's internal dynamics. The sudden injection of energy-enhanced mantle convection, promoting the early stages of plate tectonics. Earth's outer shell, though still forming, became more dynamic and mobile. This movement would eventually shape continents, build mountain ranges, and recycle nutrients through the crust. Plate tectonics is essential for maintaining a stable climate over billions of years because it regulates carbon dioxide through volcanic activity and rock weathering. Theia's collision indirectly set this engine into motion. As the moon slowly drifted outward, Earth continued to cool. The atmosphere cleared enough to expose the sky once more. Volcanic eruptions continued, releasing gases and shaping the landscape. But the violence of the Hadean era began to settle. The moon's presence created regular cycles, day and night, tides, rotational slowing that brought order to a once chaotic world. These cycles laid the foundation for the natural rhythms that would govern Earth throughout its history. The period after the Theia impact marked the transition from a molten world to a cooling planet capable of holding oceans and hosting chemical reactions that would one day lead to life. The impact set in motion a chain of events that guided Earth toward habitability. Without this collision, Earth might never have gained a large moon. And without a moon, Earth's climate stability, tides, and rotational balance would have been vastly different. Scientists believe that the Moon formed quickly within just a few thousand years after the impact. Once it reached its final form, it cooled into a solid, cratered world. Its surface preserves a record of early solar system bombardment, providing critical clues about the environment Earth experienced during its earliest eras. While Earth's active geology erased most evidence of the Hadean, the Moon retains this ancient history like a time capsule. With the Moon in place, Earth's evolution accelerated. Its crust thickened, its interior layered more distinctly. The magnetic field strengthened. Volcanic activity shaped the atmosphere. Water vapor began to accumulate and cool. Rain would soon fall for the first time, marking the beginning of the hydrological cycle that drives weather and erosion. But this moment came long after the impact's immediate aftermath. The Moon's creation also affected Earth's energy balance. It changed how sunlight reflected off the planet and how heat dissipated into space. It influenced the tilt of the axis, creating moderate seasonal changes. These changes prevented Earth from entering permanent climate extremes. Instead, the planet maintained oscillations that favored adaptability and evolutionary diversity. Over millions of years, the Earth-Moon system became one of the most stable partnerships in the solar system. While other planets experienced chaotic tilts, lost moons, or suffered major orbital instabilities, Earth and its Moon settled into a predictable pattern. This stability is one of the key reasons life could eventually emerge. In the aftermath of the Theia collision, Earth stood transformed. What had once been a molten, chaotic sphere was now a planet with structure, rhythm, and potential. The Moon orbited nearby, glowing white against the dark cosmic backdrop. The sky began clearing as debris settled. Volcanic plumes rose from the surface, painting streaks of red and orange across the horizon. Beneath the crust, the mantle churned with energy. The world was still violent, but its violence had purpose to shape the environment that would one day cradle life. Theia's impact marks the dividing line between Earth's raw formation and its progression toward habitability. It is the cosmic event that turned a molten sphere into a planet with oceans, continents, climate, and eventually, biology. Every living organism on Earth carries within it the legacy of this ancient collision. Every tide, every season, every eclipse is a reminder of the moment when two worlds became one. Earth and the Moon are forever bound by this shared origin. The impact was catastrophic, yet undeniably creative. From destruction came order, from chaos came structure. From molten debris came the beginnings of a stable, life-supporting world. And as Earth cooled, the next chapter prepared to unfold the formation of oceans, the thickening of crust, and the slow emergence of conditions that would make life possible. In the aftermath of the Theia collision, Earth remained a molten, glowing world. Its surface simmered at thousands of degrees, wrapped in an atmosphere thick with vaporized rock, carbon dioxide, sulfur compounds, and immense clouds of steam. The Moon, newly formed, circled close overhead, raising powerful tides in the molten surface below. Yet, even amid this hellish landscape, the foundations for oceans, continents, and stable crust were quietly taking shape. Earth was beginning the slow journey from fire to water, from chaos to equilibrium. As millions of years passed, heat radiated into space. The molten surface of Earth began to cool gradually. The magma ocean that had once engulfed the entire planet solidified from the outside in, forming a thin crust over the still molten interior. This crust was fragile and dynamic. Volcanic eruptions frequently shattered it, releasing new lava and gases into the atmosphere. Some regions cooled faster than others, creating thicker patches of crust precursors to the earliest continental fragments. Earth's early atmosphere played a central role during this cooling phase. After the first atmosphere was blasted away by solar winds and the Theia impact, volcanic outgassing built a second atmosphere composed primarily of carbon dioxide, water vapor, nitrogen, methane, and sulfur dioxide. This dense blanket trapped heat, slowing the planet's cooling. At the same time, it created a powerful greenhouse effect that kept the surface warm enough to prevent freezing while the interior continued to contract and cool. As the surface cooled, the temperature eventually dropped below the boiling point of water. This moment marked a dramatic transition. The vast amounts of water vapor trapped in the atmosphere, released from volcanoes, delivered by comets, and inherited from the planet's formation, began to condense. Clouds thickened. Storms intensified. For the first time in Earth's history, rain began to fall. The rain did not stop for millions of years. It poured relentlessly from the sky, filling basins, carving channels, and cooling the crust further. Each raindrop evaporated on contact with the still hot surface. But as cooling continued, more water remained liquid. Shallow pools formed in depressions. These pools grew into seas, and the seas expanded into primitive oceans. The hydrological cycle, evaporation, condensation, rainfall, began operating on a planetary scale. The formation of the oceans marked a turning point. Water is a powerful agent of change. It erodes rock, transports minerals, shapes landscapes, and regulates temperature. As the oceans grew, they absorbed carbon dioxide from the atmosphere, lowering greenhouse levels slightly and allowing further cooling. Oceans also acted as heat reservoirs, smoothing temperature fluctuations and stabilizing the young planet's climate. Beneath the surface, the mantle continued to churn. Convection currents pushed molten rock upward, creating volcanoes and igneous intrusions. These volcanic regions produced new crust, while older crust sank or fractured under the weight of accumulating water. The earliest form of plate tectonics may have begun during this time. The crust was thinner, hotter, and more flexible than today's, but water weakened it, allowing it to break into segments. These segments moved slowly, driven by the mantle's heat. This movement created new geological features, ridges, trenches, and volcanic arcs. The earliest continental fragments, known as cratons, began forming from buoyant, silica-rich rocks created deep within the mantle. These rocks were lighter than the surrounding basaltic crust, allowing them to float higher, resisting submersion beneath the oceans. Over time, these primitive continents grew through repeated melting and solidification. Volcanic activity added new material. Impacts from meteorites delivered additional minerals. The crust thickened, creating stable regions that would eventually become the cores of modern continents. The oceans themselves were far different from the blue waters of today. Early oceans were likely greenish or brownish, filled with dissolved iron and minerals leached from the crust. The atmosphere lacked oxygen, so iron remained in its soluble form, giving the water a distinct chemical character. Hydrothermal vents dotted the seafloor, releasing hot, mineral-rich fluids that reacted with seawater. These vents created complex chemical environments that scientists believe may have played a role in the origin of life. As Earth cooled further, the atmosphere continued to evolve. Volcanic eruptions released ongoing supplies of gases. Carbon dioxide remained abundant, maintaining a greenhouse effect strong enough to counter the faint young sun, which shone at only about 70% of its current brightness. Without this greenhouse effect, Earth might have frozen into a global ice world before life had a chance to emerge. Instead, the balance between volcanic emissions and oceanic absorption kept the climate warm enough for liquid water. The Moon played a crucial role during this era. Though it had moved farther from Earth than during its formation, it still orbited close enough to exert enormous tidal forces. These tides stirred the early oceans. Enhancing chemical mixing, the tidal cycles helped distribute heat and nutrients, shaping the conditions in which early chemical reactions occurred. The rhythmic rise and fall of the tides added structure to a world still finding its equilibrium. The crust continued to thicken. Volcanic island chains erupted throughout the oceans, forming archipelagos. These islands eroded under constant rainfall, delivering sediments into the seas. Sedimentary layers accumulated on the ocean floor, marking the first geological records preserved on Earth. While most Hadean rocks have been destroyed by tectonic recycling, tiny zircon crystals, some over 4 billion years old, remain as evidence of early crust and liquid water. These zircons tell a remarkable story. They contain oxygen isotopes that indicate interactions with liquid water at surprisingly early times. This means oceans may have existed while the surface was still cooling from the Theia impact. Earth transitioned to a water world far sooner than once believed. The presence of water helped moderate temperatures and accelerate geological processes. Even in its youth, Earth was already exhibiting features of a dynamic, evolving planet. As oceans expanded, they began covering most of the planet's surface. Earth may have appeared almost entirely blue, dotted only by small volcanic islands and tiny continental fragments. The deep ocean basins formed as the crust thinned in some areas. Mid-ocean ridges released magma that cooled rapidly, creating dense basalt. This basalt sank, forming deeper regions that filled with water. The interplay between ridges and basins shaped the global ocean system. The atmosphere gradually cleared of dust and debris. Thick clouds dominated the sky, but sunlight increasingly reached the surface. Volcanic gases continued influencing climate. Sulfur dioxide reacted with water to form acid rain, which etched rocks and altered the chemistry of the oceans. Carbon dioxide dissolved in seawater, forming carbonic acid and regulating atmospheric composition. Nitrogen accumulated as a stable atmospheric gas, forming the foundation of Earth's modern atmosphere. While oxygen remained absent, other gases played active roles. Methane, produced by geological processes, contributed to warming. Ammonia influenced early chemical reactions. Lightning storms continued to energize the atmosphere, breaking molecules apart and creating new ones. Ultraviolet radiation from the sun penetrated the atmosphere, interacting with water and volcanic gases to form complex organic molecules. Though life had not yet emerged, the planet was becoming increasingly chemically rich. Earth's crust, though more stable than during the Hadean, still experienced frequent impacts. The late heavy bombardment, a period of intensified asteroid strikes, occurred near the end of this era. Massive impacts vaporized portions of oceans, melted crust, and temporarily sterilized large regions of the planet. Despite this destruction, life would later emerge, showing the resilience of Earth's systems. But before life could rise, the planet needed to reach a new level of stability. As cooling continued, the mantle's convection patterns evolved. Heat escaped more efficiently through the thicker crust, allowing deeper mantle layers to solidify slightly. This change increased the contrast between oceanic and continental crust. Continental crust, being lighter and thicker, remained above sea level more consistently. Oceanic crust, thinner and denser, formed vast basins. This differentiation laid the foundation for the future arrangement of continents and oceans. The oceans themselves became more complex. Temperature gradients formed between shallow coastal regions and deep ocean trenches. Hydrothermal vent systems created chemically rich environments on the sea floor. These vents expelled superheated water laden with minerals, creating towering chimneys of solidified minerals known as black smokers. The boundary between hot vent water and cold ocean water produced steep chemical gradients ideal for early chemical evolution. The atmosphere stabilized enough to create the first weather patterns. Winds circulated heat from the equator to the poles. Storms formed as warm ocean water evaporated and condensed into clouds. Rainfall shaped the landscape, breaking down rocks and transporting minerals. Erosion sculpted early land masses. Sediment deposition created layered rocks, some of which survive today as the world's oldest geological formations. The cooling of the crust also strengthened Earth's magnetic field. As the core continued to differentiate, the dynamo effect in the liquid outer core intensified. This magnetic shield protected the atmosphere from being stripped away by solar winds. The preservation of the atmosphere was crucial for the stability of the oceans. Without the magnetic field, Earth might have lost its water to space, as happened on Mars. Over time, the oceans reached near modern volumes. Water covered most of the planet, creating a global environment capable of supporting complex chemistry. The oceans acted as a vast solvent, dissolving minerals and mixing elements. These elements would later become essential components of life. Among them were carbon, nitrogen, phosphorus, sulfur, and various trace metals. The oceans became a planetary laboratory, conducting endless chemical experiments. The presence of stable oceans also allowed Earth to reflect sunlight more effectively. The planet cooled further, balancing greenhouse effects and solar radiation. Climate cycles began to emerge. The rotation of the Earth slowed slightly as tidal friction from the Moon continued to influence motion. Each change contributed to the development of a stable environment. The earliest forms of continental crust grew larger. Volcanic islands merged, forming larger land masses. These continents remained small compared to today's, but they provided diversity in habitats, rocky shores, shallow seas, volcanic plains, and deep basins. These varied environments played crucial roles in shaping the future of life. Life would not emerge uniformly. It would arise in specific environments where chemical gradients and stability aligned. By the end of this era, Earth had transformed from a molten inferno into a water-rich world with a thickening crust. Its atmosphere, though still hostile to modern life, supported a stable climate. The oceans circulated heat, mixed nutrients, and provided a medium for chemical evolution. The continents began to form the skeleton of future geology. The Moon hung in the sky, gradually drifting outward, but still dominating tidal patterns. Earth was now ready for the next chapter, the emergence of life. But before life could appear, the planet needed further chemical evolution, driven by the oceans, the atmosphere, and the energy from the sun and mantle. The stage was set. A once fiery planet had cooled enough to host liquid water, stable crust, and complex chemistry. From fire came water. From chaos came stability. And within this stability, the first whispers of life were beginning to take shape. The Earth, now cooled enough to hold vast oceans, entered a new and remarkable chapter. The violent bombardment of the Hadean had subsided. The molten crust had hardened into a more stable surface. Clouds parted enough for sunlight to reach the oceans. Volcanic islands rose from steaming waters. Hydrothermal vents pierced the seafloor, releasing plumes of mineral-rich fluids into the dark abyss. Everywhere, chemistry was unfolding on a planetary scale. In this world, there were no plants, no animals, not even microbes. Yet the ingredients for life collected in the oceans, waiting for the moment when matter would cross the boundary into biology. Earth's early oceans were far from calm or simple. They were dynamic, filled with dissolved minerals, metals, and gases absorbed from volcanic eruptions and hydrothermal vents. Ultraviolet radiation from the young sun penetrated the upper layers of water, breaking molecules apart and producing new ones. Lightning storms energized the atmosphere, creating reactive compounds that washed into the seas. Meteorites delivered organic molecules formed in the interstellar medium. The oceans became a vast chemical laboratory full of potential. Life did not begin with a single spark or a single event. Instead, it emerged through countless interactions among molecules, driven by energy from the sun, the Earth's interior, and the environment itself. These interactions produced increasingly complex combinations of carbon-based molecules, amino acids, nucleotides, lipids, and sugars formed through a mix of geological and atmospheric processes. These molecules concentrated in specific environments: tidal pools, hydrothermal vents, volcanic lakes, and mineral-rich sediments. One of the most compelling environments for the origin of life existed deep beneath the ocean's surface: hydrothermal vents. Here, hot water rich in hydrogen, methane, and mineral ions flowed through cracks in the crust. When this superheated water met cold seawater, it created steep chemical gradients. These gradients provided energy that could drive chemical reactions. Mineral structures at these vents, particularly porous iron-sulfur formations, acted like natural reactors. Their tiny compartments offered protection, concentration, and catalytic surfaces for early molecules to assemble into more complex forms. In these environments, simple organic molecules began forming chains. Peptides formed from linked amino acids. Nucleotides bonded to create short strands resembling primitive RNA. Lipids assembled into spherical membranes that trapped molecules inside. These early membranes were fragile, but they represented a crucial step. They created boundaries. Life requires separation, an inside and an outside, and these lipid bubbles offered the first primitive form of cellular structure. The next challenge was replication. For life to take hold, molecules needed the ability to copy themselves. Before DNA existed, scientists believe RNA-like molecules played this role. RNA is capable of both storing information and catalyzing chemical reactions in the primordial seas. Short RNA strands may have formed spontaneously, aided by mineral surfaces that stabilized their structure. Some of these strands could fold into shapes that allowed them to copy parts of themselves. Imperfect copying introduced variation. Variation introduced evolution. Over time, the most stable and efficient sequences persisted. These replicating molecules did not exist alone. They interacted with lipids, peptides, minerals, and environmental forces. Eventually, some replicators became enclosed within lipid membranes. This created the first protocells, simple vesicles containing genetic material and chemical machinery. Though incredibly primitive, these protocells had two essential properties. They maintained internal chemistry and they reproduced, even if crudely. From this point forward, evolution had something to work with. The oceans provided the perfect environment for protocells to survive. Currents carried nutrients. Tides created cycles of concentration and dilution. Ultraviolet light-induced mutations, creating new molecular variations. Hydrothermal vent systems offered stable energy gradients, while shallow pools offered cycles of drying and refilling that concentrated molecules to useful levels. Protocells that survived environmental pressures grew more complex over time. The first true cells likely emerged when protocells stabilized their internal chemistry enough to sustain metabolism. Metabolism refers to the ability to use energy from the environment to drive chemical reactions inside the cell. Early metabolism may have been simple, relying on chemical gradients near vents. Over time, cells developed more sophisticated ways to generate energy. They used minerals like iron and sulfur to fuel reactions. They developed membranes that controlled the flow of ions, creating internal environments different from the outside world. These first cells were prokaryotes, simple, single-celled organisms with no nucleus. They were unlike anything alive today, yet they shared fundamental traits with modern bacteria and archaea. They possessed genetic material, membranes, metabolic pathways, and the ability to reproduce. Though microscopic, they represented a monumental step in the history of the planet. Inanimate matter had transitioned into living organisms. Once life began, it spread through the oceans. Early cells colonized hydrothermal vent systems, clinging to mineral surfaces. Others drifted in ocean currents, carried to new environments. Some adapted to shallow waters, where sunlight was available. Others survived near volcanic islands, feeding on chemical gradients produced by eruptions. Although life remained single-celled for a long time, it was already transforming the planet. One of the most profound transformations came with the evolution of photosynthesis. Before photosynthesis, early cells relied on chemical energy from the environment. This limited their growth and distribution. But some cells developed pigments capable of capturing sunlight. These pigments allowed them to harness light energy to drive chemical reactions. The earliest photosynthetic organisms may not have produced oxygen. They likely used hydrogen sulfide or other molecules instead. But eventually, a revolutionary pathway evolved: oxygenic photosynthesis. Oxygenic photosynthesis uses water as an electron source, releasing oxygen as a byproduct. When this process emerged, it changed the entire future of Earth. Suddenly, life could tap into an almost unlimited energy source, sunlight, and use water, one of the most abundant molecules on Earth, as fuel. This dramatically increased productivity in the oceans, setting the stage for further biological innovation. But oxygen was toxic to many early organisms. When oxygen first accumulated in localized environments, it caused oxidative stress. Some organisms died, others adapted. Still others sought refuge in oxygen-free regions. Over millions of years, oxygen levels began rising gradually in the oceans and atmosphere. This rise would culminate in the Great Oxygenation Event, a turning point that reshaped the planet. But that transformation belonged to a later era. In the early stages, life continued evolving in low oxygen conditions. Prokaryotes diversified into numerous metabolic forms. Some used sulfur, others used iron. Some fed on methane, others produced methane. The methane in the atmosphere contributed to a warming effect that helped compensate for the faint young sun. Biology and climate became intertwined, each influencing the other. The oceans themselves transformed as life expanded. Microbial mats formed on shallow sea floors, trapping sediments and creating layered structures known as stromatolites. These stromatolites are among the oldest fossils on Earth, dating back more than 3.5 billion years. They provide evidence that early microbial life was already forming complex communities. Within these mats, different microorganisms lived in layers, each performing specialized functions. Some absorbed sunlight, others broke down chemical wastes. Together, they created miniature ecosystems. The chemical composition of the oceans continued to shift. Dissolved iron reacted with oxygen produced by early photosynthetic organisms, forming iron oxide minerals that sank to the seafloor. These deposits created banded iron formations, geological layers that record the growing influence of biology on the planet. Each layer reveals a moment in Earth's chemical history, connecting geology and biology in a shared timeline. Life also influenced the stability of the crust. Microbial activity contributed to weathering, breaking down minerals, and altering the surface chemistry of rocks. Sediments created by biological processes built layers on the ocean floor, affecting tectonic movements. Although life remained microscopic, its impact grew steadily. The early atmosphere, while still harsh by modern standards, became more stable. Nitrogen dominated. Carbon dioxide remained abundant, but gradually declined as oceans and early organisms absorbed it. Methane from microbes contributed to warming. The interplay between gases created a delicate balance that kept Earth's temperature within a range suitable for liquid water. Evolution continued. Natural selection favored cells with more efficient membranes, more accurate replication, and more robust metabolic pathways. Diversity increased. Some cells specialized in certain environments, others adapted to extreme conditions, living near boiling vents or highly acidic waters. These extremophiles demonstrated that life could thrive in a wide range of habitats. They also revealed the resilience of early life, capable of surviving conditions far more extreme than most modern organisms. As time passed, genetic innovation gave rise to more complex biochemical systems. Enzymes became more specialized. Metabolic pathways became more interconnected. Cells gained the ability to repair damage, regulate internal chemistry, and adapt to environmental changes. Although the first billion years of life remained purely microbial, this period established the foundation for all future biological evolution. The oceans, once purely chemical environments, had become biological seas filled with microscopic life. These organisms interacted with geology, chemistry, and climate, influencing the entire planet. The emergence of life marked the beginning of a new era in Earth's story, one in which biology and geology would continually shape each other. Earth's journey from stardust to a living world was extraordinary. The birth of life in the primordial seas was not guaranteed. It required the right conditions, the right chemistry, and the right sequence of events. But once life emerged, it became an unstoppable force of transformation. From simple molecules came replicators. From replicators came protocells. From protocells came the first true organisms. These organisms would eventually give rise to the entire tree of life, from bacteria to animals to humans. And as life flourished, the next great transformation approached, the rise of prokaryotes and the long evolutionary journey toward complexity. After life first emerged in Earth's primordial oceans, the planet entered a new chapter, dominated entirely by microscopic organisms. These earliest inhabitants, prokaryotes, reshaped the chemistry of the atmosphere, altered the composition of the oceans, and laid the biological groundwork for every form of life that would follow. For more than 1 billion years, prokaryotes ruled the planet. Though invisible to the naked eye, their influence was immense. They were architects of ecosystems, engineers of chemical cycles, and the silent force guiding Earth toward complexity. Prokaryotes are simple cells with no nucleus. Their genetic material floats freely within the cytoplasm. Their membranes are thin but functional. Their metabolisms are versatile and inventive. These traits allowed them to survive in environments that would kill most modern organisms. When prokaryotes first appeared, Earth was a harsh world with volcanic activity, frequent impacts, high ultraviolet radiation, and oceans filled with dissolved metals. Yet prokaryotes adapted with remarkable ease, spreading from shallow coastal waters to deep ocean vents. At hydrothermal vents, early archaea, one of the two main branches of prokaryotes, found energy in chemical gradients created by the mixing of hot vent water and cold ocean water. These organisms used hydrogen, sulfur, and methane in their metabolic pathways. They fed on inorganic molecules, relying on the planet's internal heat rather than sunlight. This type of metabolism, known as chemosynthesis, allowed life to thrive in complete darkness. Even today, deep-sea vent communities rely on similar chemical processes, reminders of ancient ecosystems that once dominated Earth. Other prokaryotes settled in shallow waters where sunlight penetrated. They developed pigments capable of capturing light and converting it into chemical energy. This innovation marked the beginning of photosynthesis. At first, photosynthetic organisms used hydrogen sulfide rather than water as an electron donor, producing sulfur instead of oxygen. These early photosynthesizers were crucial because they expanded the availability of energy. Sunlight, abundant and constant, became a source of fuel for life. Eventually, a revolutionary adaptation appeared: oxygenic photosynthesis. This process used water as a source of electrons, releasing oxygen as a byproduct. Cyanobacteria, the prokaryotes responsible for this development, transformed the chemistry of the oceans and atmosphere. Oxygen was initially toxic to many early organisms, but cyanobacteria thrived because it allowed them to access an unlimited supply of water. Using sunlight and water, they produced energy with extraordinary efficiency. Cyanobacteria formed sprawling microbial mats in shallow seas. These mats trapped sediments and built layered structures known as stromatolites. These formations still exist today in a few isolated locations. But 3 billion years ago, they dominated the coastlines. Stromatolites served as living factories, continuously producing oxygen and altering the planet's atmosphere, layer by layer. They grew upward, preserving evidence of early life within their mineral skeletons. As cyanobacteria continued releasing oxygen, the oceans began to change. Dissolved iron in seawater reacted with the oxygen, forming solid iron oxides that settled on the ocean floor. This process created the famous banded iron formations, layered rocks that reveal shifting oxygen levels over geological time. Each band of iron represents a chapter in the story of Earth's transformation, written not by rivers or volcanoes, but by microscopic life. For a long time, oxygen produced by cyanobacteria was absorbed by the oceans and seafloor minerals. The atmosphere remained largely anoxic. Prokaryotes diversified in this low oxygen world, adapting to an array of ecological niches. Some became methanogens, producing methane, a powerful greenhouse gas that helped warm the planet under a faint young sun. Others became sulfate reducers, breaking down sulfur compounds. Still others specialized in nitrogen fixation, transforming nitrogen gas into biologically usable forms. This nitrogen fixation would become essential for all future life, as nitrogen is a fundamental component of DNA, proteins, and cell structures. As prokaryotes diversified, they formed complex ecosystems long before plants or animals existed. Microbial colonies covered vast areas of seafloor in shallow waters. Cyanobacteria built stromatolite forests. In deep ocean vents, archaea fed on hydrogen sulfide, supporting entire communities of organisms. Even beneath the sea floor, microbes lived within rock pores, feeding on the chemical energy released by interactions between water and minerals. Earth was alive at every depth. Prokaryotes also developed remarkable resilience. They evolved the ability to form spores, allowing them to survive extreme heat, cold, drought, and radiation. Some found refuge deep underground. Others survived freezing temperatures near the poles. This adaptability ensured that prokaryotes remained the most abundant and diverse form of life on the planet. Over time, oxygen produced by cyanobacteria began to accumulate in the oceans faster than it could react with minerals. Once the supply of easily oxidized materials was exhausted, oxygen levels rose more rapidly. Eventually, oxygen escaped into the atmosphere. This began a slow but profound transformation known as atmospheric oxygenation. Oxygen levels rose from near zero to detectable levels for the first time in Earth's history. Oxygen changed everything. For anaerobic organisms, oxygen was toxic. It damaged cellular structures and disrupted metabolic pathways. Many early prokaryotes went extinct. Others retreated into environments where oxygen could not reach, such as deep sediments, vents, and oxygen-poor waters. A few organisms evolved defenses against oxygen, developing enzymes capable of neutralizing reactive oxygen molecules. These adaptations allowed aerobic respiration to evolve. Aerobic respiration was far more efficient than anaerobic metabolism. Oxygen acted as a powerful electron acceptor, allowing organisms to extract significantly more energy from food molecules. This gave aerobic prokaryotes a tremendous advantage. They multiplied rapidly, colonizing new environments and diversifying into countless lineages. The rise of oxygen did not merely change the atmosphere, it changed the trajectory of life itself. As oxygen accumulated in the atmosphere, it also reacted with methane, reducing the greenhouse effect. This shift in atmospheric composition contributed to global cooling. Scientists believe these changes may have triggered one of Earth's earliest ice ages, possibly even a global glaciation. Prokaryotes survived this cold world, adapting to frozen oceans and icy conditions. Microbial life persisted beneath ice sheets, near hydrothermal vents, and in pockets of unfrozen water. During these transformations, prokaryotes continued to innovate genetically. Horizontal gene transfer, the ability to share genes between unrelated organisms, accelerated evolution. Unlike animals and plants, prokaryotes could exchange segments of DNA directly. This allowed beneficial mutations, such as antibiotic resistance or new metabolic pathways, to spread rapidly. Gene sharing turned microbial evolution into a collective process, enabling populations to adapt to new conditions with extraordinary speed. One of the most important evolutionary innovations occurred when some prokaryotes developed internal membrane folds, increasing the surface area for metabolic reactions. These folds may have been precursors to the internal structures found in later eukaryotic cells. Some prokaryotes also evolved primitive cytoskeletons, flexible protein frameworks that allowed them to change shape and move more effectively. Although still simple compared to modern cells, these adaptations hinted at the complexity to come. Prokaryotes did more than survive, they shaped the planet. They controlled the carbon cycle, breaking down organic matter and releasing nutrients back into the environment. They influenced the sulfur cycle, creating chemical gradients in ocean sediments. They fixed nitrogen, enabling future ecosystems to exist. Their metabolic activities helped regulate climate, atmospheric composition, and ocean chemistry. For billions of years, Earth was a microbial world, engineered and maintained by prokaryotes. Their power extended even deeper. Prokaryotes in the subsurface, living kilometers beneath the seafloor, created long-lasting ecosystems independent of sunlight. These deep biosphere organisms fed on hydrogen produced by water interacting with minerals in the crust. They reproduced slowly, sometimes dividing only once every 1,000 years. Yet they persisted, forming one of the largest reservoirs of life on the planet. Even today, the deep biosphere contains more biomass than all plants and animals combined. By this time, Earth's oceans and atmosphere were no longer purely geological constructs. They were biological systems shaped by living organisms. Oxygen levels continued to rise, eventually leading to the Great Oxygenation Event, a turning point that belongs to the next chapter. But before the Great Oxygenation, prokaryotes achieved one of the most astonishing innovations in the history of life: the symbiotic merging of different prokaryotic cells. Some archaea engulfed bacteria but did not digest them. Instead, the bacteria survived inside their hosts, providing energy in exchange for protection. This partnership marks the beginning of the eukaryotic cell, mitochondria, the energy-producing organelles in all complex life, originated from these engulfed bacteria. Later, some eukaryotes engulfed cyanobacteria, giving rise to chloroplasts, the structures that perform photosynthesis in plants. This moment, when one cell lived inside another, was one of the most important leaps in evolution. It created the foundation for complex life. Yet this transformation was possible only because prokaryotes had spent billions of years diversifying, adapting, and altering the planet's chemistry. Prokaryotes ruled Earth for most of its history. They created the atmosphere we breathe. They set the stage for the evolution of plants, animals, and humans. They built the world molecule by molecule. Without prokaryotes, Earth would remain barren and lifeless. Their legacy is still with us. In every human body, trillions of bacteria help digest food, regulate immunity, and maintain health. In every ecosystem, prokaryotes recycle nutrients and support food webs. In every ocean, they produce oxygen and drive chemical cycles. Even after billions of years, the planet remains a microbial world at its core. By the end of this era, Earth had undergone profound change. Oxygen levels began to rise significantly. Microbial ecosystems had matured. The first eukaryotic cells were beginning to form. The world was ready for the next dramatic transformation, the Great Oxygenation Event, a shift that would alter the climate, reshape the surface, and pave the way for complex life. For billions of years, Earth had been a world ruled by prokaryotes, thriving in oxygen-free oceans and atmospheres. Life was purely microbial, adapted to a chemistry dominated by methane, carbon dioxide, nitrogen, sulfur, and dissolved metals. The oceans were greenish and iron-rich. The skies were hazy, tinted by volcanic gases. Sunlight filtered through an atmosphere without ozone. And across the shallow seas, cyanobacteria continued to perform oxygenic photosynthesis, a groundbreaking innovation that would eventually trigger one of the most dramatic transformations in the planet's history. This transformation is known as the Great Oxygenation Event, and it would change the face of Earth forever. For millions of years after cyanobacteria evolved oxygenic photosynthesis, the oxygen they produced did not accumulate in the atmosphere. It was immediately consumed by chemical reactions in the oceans. Vast quantities of dissolved iron absorbed the oxygen, forming solid iron oxides that drifted to the seafloor. These deposits became banded iron formations, alternating layers of iron-rich minerals that still serve as geological witnesses to this ancient era. Each layer marks a moment when oxygen levels surged, triggering precipitation of iron before atmospheric accumulation could begin. For a long time, this process acted as a chemical buffer, preventing oxygen from entering the atmosphere in significant amounts. But the supply of dissolved iron was finite. Eventually, the oceans became saturated. Once the iron was fully oxidized, it could no longer absorb oxygen. At this tipping point, cyanobacteria continued releasing oxygen, but the oceans no longer had the capacity to neutralize it. Slowly, oxygen began to accumulate. At first, the rise was modest, tiny increases in atmospheric concentration barely detectable. But over time, the oxygen curve steepened. Earth's atmosphere entered a new phase. Rising oxygen levels created massive consequences. For many early organisms, oxygen was poisonous. Anaerobic microbes, which had evolved in a world without oxygen, suffered as reactive oxygen molecules damaged their proteins, membranes, and DNA.
These organisms were forced into oxygen, poor refuges, deep sediments, hydrothermal vents, and isolated environments where oxygen could not penetrate. Vast numbers of anaerobic species likely went extinct.
It was one of Earth's earliest mass extinctions, invisible to the naked eye but enormous in impact. As oxygen increased, it also reacted with methane in the atmosphere. Methane had been one of the most significant greenhouse gases, helping keep Earth warm under a faint young sun. Oxygen stripped methane from the atmosphere, converting it into carbon dioxide and water. This reduction in methane weakened the greenhouse effect, allowing Earth to lose more heat to space. Global temperatures dropped significantly. Some studies suggest this cooling triggered one of the first major glaciations in Earth's history, possibly even a snowball Earth, where ice covered large portions of the planet. Although debate continues about the extent of this glaciation, it is clear that the Great Oxygenation event had the power to reshape global climate. Oxygen's rise also transformed the chemistry of the atmosphere and oceans. Oxygen reacted with gases like hydrogen sulfide, reducing their abundance. It oxidized minerals on land, creating soils and binding metals into new forms. For the first time, oxidative weathering became a major geological process. This weathering released nutrients into rivers and oceans, altering marine ecosystems and opening opportunities for new microscopic life. As oxygen accumulated, the upper atmosphere began forming ozone, a molecule composed of 3 oxygen atoms. Ozone plays a crucial role in blocking harmful ultraviolet radiation from the sun. Before the ozone layer existed, Earth's surface was bombarded by intense UV light, limiting life to underwater environments or shaded regions. The formation of the ozone layer reduced UV exposure, allowing future life forms to explore shallower waters and eventually reach land. This protection marked a turning point, enabling biological expansion that would unfold over billions of years. While oxygen was dangerous to some life forms, it offered tremendous advantages to others. Aerobic respiration evolved as a powerful metabolic pathway. Organisms that could use oxygen to break down organic molecules extracted far more energy than anaerobic organisms could. This energy surplus supported more complex cellular structures and faster growth. aerobic prokaryotes flourished, diversifying rapidly in the oxygenated environment. The stage was set for one of the most important evolutionary leaps in history, the development of eukaryotic cells. Though eukaryotes did not immediately dominate during the Great Oxygenation event, the rising oxygen levels created the conditions necessary for their emergence. Mitochondria, the energy-producing organelles within eukaryotic cells, evolved from aerobic bacteria that entered into symbiotic relationships with other prokaryotes. This symbiosis was only possible because oxygen had become a stable part of the environment. Thus, the Great Oxygenation event indirectly laid the foundation for all complex life: plants, fungi, animals, and eventually humans. As oxygen transformed the planet's chemistry, the appearance of rust-colored soils became widespread. Iron minerals oxidized, staining landscapes red. These red beds are geological markers of the rise of oxygen. They reveal a world undergoing dramatic oxidation, with new minerals forming on continents and in ocean basins. The chemistry of rocks forever changed, reflecting the arrival of free oxygen in the atmosphere. The oceans also evolved. Once filled with dissolved iron, they gradually became clearer as the iron precipitated out. Oxygen began diffusing into surface waters, creating stratified layers. The upper ocean became oxygen-rich, while deeper layers remained anoxic for much longer. This stratification influenced marine life, driving new forms of metabolism and ecological partitioning. Some microbes specialized in oxygen-rich zones. Others survived in the oxygen-poor depths, maintaining ancient metabolic pathways that predated atmospheric oxygen. The Great Oxygenation event unfolded over hundreds of millions of years. It was not a sudden shift, but a complex, multi-stage transformation. Oxygen levels rose in pulses, influenced by climate, volcanic activity, tectonic movements, and biological evolution. Sometimes, oxygen increased rapidly, triggering bursts of oxidation. Other times it stabilized or even declined. But the long-term trend was unmistakable. Earth was transitioning into an oxygenated world. This transition dramatically altered Earth's energy cycles. With oxygen abundant, new chemical reactions became possible. Combustion could occur. Organic matter could burn. Oxidative decay became a central part of the carbon cycle. Ecosystems, even though still microbial, gained access to new resources and new modes of survival. As oxygen levels continued rising, atmospheric pressure and composition changed enough to influence weather patterns. Storms evolved. Rainfall chemistry shifted. Lightning frequency may have changed. Each alteration influenced chemical cycles on land and in the oceans. Even without plants or animals, the environment was becoming increasingly complex. During this time, prokaryotes continued to drive most biological processes. Cyanobacteria thrived in sunlit waters, forming large colonies and mat structures. These mats covered coastlines, creating oxygen-rich microenvironments. Beneath them, anaerobic organisms found refuge. These layered microbial ecosystems were precursors to future biodiversity. Even in their simplicity, they demonstrated patterns of cooperation, competition, and specialization. As oxygen accumulated further, it began penetrating deeper into the oceans. Sulfate concentrations rose as sulfur reacted with oxygen, altering marine chemistry. Increased sulfate supported the evolution of sulfate, reducing bacteria, which played major roles in nutrient cycling. Nitrogen cycling also intensified, with nitrifying and denitrifying bacteria becoming more active. These changes were essential for maintaining global nutrient balance. The Great Oxygenation Event also affected tectonic and geological processes. Oxidation of the crust weakened certain minerals and altered rock composition, influencing erosion rates and sediment formation. Increased weathering delivered more nutrients to the oceans, potentially boosting biological productivity. As productivity increased, more organic matter accumulated on the seafloor, altering carbon burial rates. Carbon burial, in turn, influenced atmospheric composition. Earth had entered a tightly coupled system where geology, chemistry, and life continually shaped one another. For anaerobic organisms, the Great Oxygenation was a biological catastrophe. Countless species vanished, pushed into extinction by the rise of a toxic gas they could not tolerate. But this extinction opened ecological space for aerobic organisms, which flourished in the new oxygen-rich environment. These aerobic microbes became the ancestors of the mitochondria that now power every eukaryotic cell. Their success marked a turning point in life's trajectory. Over time, oxygen levels reached a plateau, stabilizing at concentrations still far lower than today's. Earth had become a partially oxygenated world, with significant differences between atmospheric layers and ocean depths. This new environment supported increasing biological complexity, paving the way for the emergence of eukaryotic cells, the next major evolutionary step. The Great Oxygenation Event is one of the planet's most important transformations. It reshaped the atmosphere, changed the climate, altered the oceans, created new ecological niches, and laid the foundation for complex life. It marked the end of the purely microbial world and the beginning of a planet capable of supporting larger, more energy-demanding organisms. Without this event, Earth would remain an anaerobic world, devoid of plants, animals, and humans. The oxygen we breathe today is a legacy of cyanobacteria that lived billions of years ago, tirelessly producing oxygen long before any creature with lungs existed. By the end of the Great Oxygenation Event, Earth had become a different planet. The skies were clearer. The oceans separated into oxygen-rich and oxygen-poor layers. The land bore the scars of oxidation. And deep within the microbial world, new possibilities were emerging, possibilities that would eventually lead to the evolution of eukaryotes, multicellular organisms, and the vast diversity of life that would come to populate Earth. The planet had taken its first breath of oxygen. The next chapter would reveal the consequences of this profound shift, including global ice ages, new ecosystems, and the rise of increasingly complex life. After the Great Oxygenation Event reshaped Earth's atmosphere and oceans, the planet entered one of the most extreme climatic chapters in its history. Oxygen levels had risen enough to disrupt the balance of greenhouse gases, particularly methane, which until then had kept the young Earth warm under a faint sun. With methane levels falling and carbon dioxide unable to fully compensate, temperatures began to drop, slowly at first, then rapidly. The world drifted toward a global chill that would culminate in what scientists call snowball Earth, a time when ice may have stretched from the poles to the equator, turning Earth into a frozen sphere. This transformation did not occur all at once. Climate fluctuations were influenced by volcanic activity, continental positions, orbital changes, and biological feedback loops. But the weakening greenhouse effect played the central role. Methane, a powerful heat-trapping gas, reacted with rising oxygen to form carbon dioxide and water. Although carbon dioxide is also a greenhouse gas, it was not abundant enough to replace the warming power of methane. The atmosphere cooled. Oceans began absorbing more heat than they retained. Glaciers formed at the poles and slowly crept toward lower latitudes. The continents of the time were arranged differently from today. Most landmasses were clustered near the equator, which meant that once ice began forming on tropical continents, it reflected enormous amounts of sunlight back into space. This reflectivity, or albedo, triggered a runaway effect. The more ice that formed, the more sunlight was reflected away. The more sunlight was reflected, the colder Earth became. This feedback loop accelerated cooling, pulling the planet deeper into a global freeze. As temperatures continued to fall, oceans began to freeze along their surfaces. At first, the ice sheets were thin and patchy, melting during warm seasons and refreezing during colder periods. But once ice reached lower latitudes, the process accelerated. Water beneath the ice remained liquid, warmed slightly by geothermal heat, but the surface froze into a thick shell. Eventually, ice may have covered the entire ocean, forming layers up to a kilometer thick. The continents, too, lay buried under immense glaciers. Mountain tops disappeared under white blankets of frozen snow and compacted ice. Earth became a world wrapped in ice. The atmosphere thinned as water vapor. A greenhouse gas condensed and froze out of the air. Storms diminished. Rainfall ceased. Evaporation nearly vanished. The hydrological cycle slowed to a near halt. Dust storms swept across the icy surface, driven by katabatic winds descending from towering ice sheets. The oceans, insulated beneath the ice, became isolated worlds of their own. Life persisted, but barely. Ecosystems that had flourished in shallow sunlit waters were devastated. Cyanobacteria, once dominant in surface waters, retreated into cracks and melt pockets where light still penetrated thin ice. Some survived near volcanic hotspots, where geothermal heat created small regions of open water known as polynyas. Other microbes sought refuge around hydrothermal vents, far below the frozen surface. These vents released hot, mineral-rich water that sustained entire communities independent of sunlight. The deep ocean biosphere, already thriving on chemical energy, became a crucial reservoir of life. Chemical cycles also slowed dramatically. The weathering of rocks, a major sink for carbon dioxide, nearly stopped because ice covered most land masses. With weathering reduced, volcanic carbon dioxide gradually accumulated in the atmosphere. But the buildup was extremely slow, requiring millions of years to reach levels capable of warming the planet again. Beneath the ice, the oceans remained dynamic. Currents circulated heat and nutrients. Hydrothermal vents produced chemical gradients that fueled microbial ecosystems. Sediments continued to accumulate on the seafloor. Some organisms developed new metabolic pathways to exploit chemical energy more efficiently. Life became more resilient, adapting to extreme cold and low light conditions that would have been unimaginable in earlier eras. Meanwhile, volcanic activity continued on land and beneath the oceans. Each volcanic eruption released carbon dioxide into the atmosphere. Because the hydrological cycle weakened, this carbon dioxide was not efficiently removed over millions of years. It began to accumulate. As atmospheric carbon dioxide levels rose, the greenhouse effect slowly strengthened. Eventually, levels may have reached hundreds of times higher than present-day concentrations. Only then did the planet begin to warm enough to challenge the frozen equilibrium. Warming initiated the slow retreat of glacial ice. At first, the warming effect was minor, barely noticeable beneath the thick ice sheets. But as the atmosphere trapped more heat, temperatures increased steadily. Thin regions of ice melted, revealing patches of dark ocean. These open waters absorbed sunlight instead of reflecting it, accelerating warming. The feedback loop reversed. Warming melted ice, Melting exposed darker surfaces, and darker surfaces increased warming. Earth began emerging from its icy tomb. As temperatures rose further, the oceans responded. The vast reserves of carbon dioxide dissolved in seawater began to outgas, reinforcing atmospheric warming. The melting ice released trapped gases, further accelerating climate change. Volcanic eruptions continued adding greenhouse gases, helping the atmosphere retain heat. Soon, the planet reached a threshold where ice melted rapidly on a global scale. When Snowball Earth thawed, the transition was explosive. Vast inland glaciers collapsed. Meltwater carved massive channels through the landscape. Catastrophic floods reshaped coastlines. Continents shed enormous amounts of sediment into the oceans, delivering nutrients that would fuel a new wave of biological productivity. The oceans, deprived of sunlight for millions of years, suddenly experienced a surge of photosynthesis as cyanobacteria expanded rapidly into the newly sunlit waters. The release from Snowball Earth triggered dramatic environmental shifts. Oxygen levels began to rise again as photosynthesis accelerated. Nutrient-rich waters stimulated microbial blooms. Carbon cycles restarted. Weathering resumed, stabilizing atmospheric carbon dioxide over time. The planet returned to a more temperate state, capable of supporting a broader range of life. Some scientists believe Snowball Earth episodes occurred more than once. Evidence suggests major glaciations around 2.4 billion years ago, and again between 720 and 635 million years ago. Each event may have been triggered by a combination of biological, geological, and atmospheric feedbacks. Each event dramatically reshaped ecosystems, acting as both a filter and a catalyst for evolution. The aftermath of these global freezes was transformative. Life that survived became stronger, more adaptable, and more capable of innovation. Microbial communities evolved new metabolic strategies. Genetic diversification increased as populations adapted to extreme conditions. Stress-driven evolution accelerated the emergence of new lineages. The harsh conditions favored organisms capable of withstanding fluctuations in temperature, oxygen levels, and chemical environments. Snowball Earth also influenced geological cycles. The massive glaciers scoured continents, grinding rocks into fine sediments. When these glaciers retreated, the sediments washed into the oceans, enriching marine environments. This influx of minerals may have contributed to the rise of more complex life shortly after Snowball Earth episodes. The oceans, once starved of nutrients, became fertile grounds for evolutionary experimentation. Carbon dioxide buildup during global freezes also played a critical role in shaping Earth's climate system. The mechanism of entering a snowball state and escaping it created a natural thermostat, balancing greenhouse gases and temperature extremes. This feedback allowed Earth to maintain long-term habitability despite variations in solar output and continental configurations. Another crucial consequence of Snowball Earth was the strengthening of the ozone layer. Periods of high volcanic activity during and after glaciations released gases that contributed to atmospheric chemistry. With rising oxygen levels, ozone formation increased. This developing ozone shield reduced ultraviolet radiation at the surface, making shallow waters and eventually land more hospitable for future organisms. As the planet warmed fully after each snowball episode, ecosystems rebounded quickly. Microbial mats reoccupied shorelines. Photosynthesis surged. Oxygen levels continued their upward trend. And deep in this recovery, the world inched closer to its next evolutionary milestone. the emergence and diversification of eukaryotic cells. Eukaryotes, complex cells with internal structures, were already present before Snowball Earth, but their expansion may have been slowed by unstable climate and low nutrient availability. After the thaw, environmental conditions improved dramatically. Nutrient-rich oceans, rising oxygen levels, and new ecological niches opened the door for eukaryotic innovation. Many scientists believe the end of Snowball Earth events provided the ecological reset and environmental triggers that allowed multicellular life to flourish. Thus, Snowball Earth, while catastrophic, may have been essential for shaping the future of life. The freezes acted as selective pressures, eliminating fragile lineages and promoting resilient ones. They increased environmental complexity and drove evolutionary creativity. They prepared the planet for the dramatic biological explosions that would follow. By the time Earth fully recovered from its global freezes, the stage was set for a new era. Oxygen levels had climbed, oceans had reorganized, ecosystems had diversified, and eukaryotic cells, once overshadowed by prokaryotes, were ready to rise to dominance. The world that emerged from Snowball Earth was one of resilience, innovation, and renewed possibility. From frozen silence came the conditions for complexity. From a planet locked in ice came the future of life as we know it. After Earth thawed from its global freezes and the climate stabilized, the planet entered a new biological era. For billions of years, prokaryotes had dominated the world, shaping its atmosphere, oceans, and chemical cycles. They were efficient, adaptable, and abundant, but they were also simple. Their small size limited their internal complexity. Their metabolic pathways, though diverse, could only support certain levels of organization. Yet deep within the microbial world, a remarkable evolutionary leap was brewing, one that would forever alter the direction of life on Earth. This leap was the emergence of eukaryotic cells. Eukaryotes are fundamentally different from prokaryotes. They contain a nucleus, the compartment that stores genetic material. They possess internal membranes forming specialized organelles. They have cytoskeletons, structural frameworks that support movement and shape. They conduct complex metabolic processes with far greater efficiency. These innovations allowed eukaryotes to grow larger, evolve new biological strategies, and eventually give rise to multicellular organisms. But their origins lie in a profound event of biological cooperation, the endosymbiotic merger. Endosymbiosis refers to the process by which one organism lives inside another for mutual benefit. In the distant past, some prokaryotic cells engulfed other prokaryotes. Normally, such engulfed organisms would be digested, but in a rare and transformative scenario, the engulfed cell survived. It continued living inside its host, offering metabolic benefits in exchange for protection. These partnerships became permanent, and over millions of years, the engulfed organisms evolved into mitochondria, the energy-producing organelles found in all eukaryotic cells. The origin of mitochondria was crucial. Mitochondria allowed cells to extract energy from food with far greater efficiency through aerobic respiration. This meant eukaryotes could support larger cell sizes, more complex internal structures, and greater genetic material. Mitochondria provided a constant and powerful energy supply that enabled biological innovation on an unprecedented scale. Without mitochondria, the evolution of complex life would have been nearly impossible. The host cell that engulfed the bacteria was likely an archaeon, deepening the biological bond between archaea and bacteria. Modern genetics confirms this ancestry. The nuclear genes of eukaryotes resemble archaeal genes, while mitochondria closely resemble aerobic bacteria. Eukaryotes are therefore hybrid organisms born from the fusion of two ancient worlds. After mitochondria evolved, eukaryotic cells gained the ability to compartmentalize their internal chemistry. Internal membranes folded inward, creating structures like the endoplasmic reticulum and Golgi apparatus. These organelles managed protein folding, transport, and cellular maintenance. With compartmentalization came efficiency, allowing cells to control reactions more precisely. The emergence of the nucleus provided protection for genetic material, reducing the impact of damaging environmental factors like ultraviolet radiation and reactive oxygen species. The cytoskeleton also evolved. This dynamic network of protein filaments allowed cells to change shape, move, and perform complex processes such as phagocytosis, the engulfing of particles. The cytoskeleton enabled internal transport, ensuring that organelles and molecules moved efficiently within the cell. This internal mobility freed eukaryotes from the limitations of diffusion that constrained prokaryotic cell size. Eukaryotes grew larger, more flexible, and more versatile. After Earth's snowball episodes ended, the environment was ideal for the expansion of eukaryotes. Nutrient influx from melting glaciers enriched the oceans. Rising oxygen levels provided the foundation for aerobic metabolism. The planet's climate stabilized, allowing ecosystems to rebound. Eukaryotic cells, equipped with mitochondria, internal membranes, and cytoskeletons, found openings in ecological niches created by the aftermath of global change. Eukaryotes diversified into numerous lineages. Some evolved photosynthetic abilities by engulfing cyanobacteria in another endosymbiotic event. These engulfed cyanobacteria became chloroplasts, the organelles responsible for photosynthesis in plants and algae. Chloroplasts allowed eukaryotes to harness sunlight and produce their own food, expanding their ecological reach into sunlit waters. Like mitochondria, chloroplasts retained traces of their bacterial origins in their DNA, providing strong evidence of their symbiotic past. With both mitochondria and chloroplasts, eukaryotes became engines of biological productivity. Photosynthetic eukaryotes enriched the oceans with oxygen, fueling further evolutionary change. Non-photosynthetic eukaryotes fed on bacteria, algae, and organic matter, forming early food webs. This interplay between producers and consumers marked the beginning of complex ecological networks. Eukaryotic cells also evolved intricate cell cycles, regulating growth and division. They developed sexual reproduction, which allowed genetic recombination between individuals. Unlike the simple binary fission of prokaryotes, sexual reproduction increased genetic variation, fueling rapid evolutionary innovation. This diversity allowed eukaryotes to adapt to new environments, exploit new resources, and withstand changing conditions. For millions of years, eukaryotes remained single-celled, but their internal complexity set the stage for multicellularity. Some eukaryotic cells began forming colonies, living together in coordinated groups. At first, these were loose associations, where each cell remained mostly independent. But over time, cells within colonies developed specialized roles. Some focused on movement, others on feeding or reproduction. The first steps toward multicellular organisms had begun. Yet even before multicellular life emerged, single-celled eukaryotes explored a vast range of ecological roles. They grazed on bacterial mats, swam through sunlit waters, drifted in planktonic clouds, and occupied sediments. Some evolved to be predators, hunting other microorganisms. Others became parasites or symbionts. Single-celled eukaryotes developed locomotion through flagella, cilia, and pseudopodia, displaying behaviors far more dynamic than those of prokaryotes. The evolution of eukaryotes also altered the chemistry of the oceans. Their metabolic activity contributed to the cycling of nutrients, such as nitrogen, phosphorus, and sulfur. They helped shape marine sediments through biomineralization, the production of minerals by living organisms. Some eukaryotes began forming shells or tests made of silica or calcium carbonate. These structures sank to the seafloor after death, creating new types of sedimentary layers that recorded their presence in the fossil record. As eukaryotes spread, they coexisted with prokaryotes, not replacing them, but forming new relationships. Prokaryotes remained the planet's dominant life form in terms of abundance and biomass. They continued driving essential chemical cycles, while eukaryotes added complexity and diversity to ecosystems. Together, they formed the dual foundation of Earth's biosphere. Earth's increasing oxygen levels played a critical role in enabling eukaryotic expansion. Aerobic respiration allowed eukaryotes to support complex internal structures and active lifestyles. Higher oxygen concentrations also supported the evolution of larger cell sizes. While early oxygen levels fluctuated, long-term trends favored organisms capable of exploiting this powerful electron acceptor. Following the emergence of eukaryotes, Earth experienced additional environmental events that continued shaping evolutionary trajectories. Periods of glaciation and warming, shifts in ocean chemistry, and tectonic changes created ecological pressures. Eukaryotes responded with adaptation, speciation, and innovation. Some lineages thrived in sunlit waters, giving rise to early algae. Others specialized in low-oxygen environments, maintaining ancient metabolic strategies. Some evolved in deep sediments away from sunlight. One of the most profound innovations that emerged from eukaryotic evolution was multicellularity. While simple multicellular forms may have existed sporadically earlier, stable multicellular organisms began to appear after eukaryotic cells gained the ability to adhere to one another, communicate chemically, and differentiate into specialized tissues. Multicellularity evolved independently in several groups: fungi, plants, animals, and certain algae. Each lineage followed its own evolutionary path, but all share the advantages of eukaryotic complexity. The emergence of eukaryotic cells was not a single event, but a long evolutionary process shaped by symbiosis, environmental change, and genetic innovation. The merging of archaeal and bacterial lineages created cellular architectures that could support greater complexity. Internal membranes protected genetic material and allowed compartmentalization of biochemical pathways. Mitochondria provided immense energy. Chloroplasts provided photosynthesis. Sexual reproduction generated diversity. Cytoskeletons enabled movement and structural organization. These innovations allowed eukaryotes to transcend the limitations of prokaryotic biology. They could grow larger, move faster, sense their environment more effectively, and process energy with far greater efficiency. This new level of biological sophistication prepared the world for the next major evolutionary transition: the first multicellular organisms. In the wake of Snowball Earth's retreat and the stabilization of climate, eukaryotes diversified rapidly. Fossil evidence from this era includes a variety of enigmatic forms, some resembling simple sponges or colonies of cells. Others formed tessellated patterns in sediments. While the exact identity of many early fossils remains uncertain, they represent experiments in complexity. Evolution was exploring the boundaries of multicellularity long before animals rose to dominance. Eukaryotes also played an important role in oxygen production. Photosynthetic algae increased atmospheric oxygen levels, enabling the eventual expansion of larger and more complex organisms. The oxygenation of deep ocean layers continued slowly, providing habitats suitable for new evolutionary experiments. Environmental fluctuations, including changes in nutrient availability, ocean circulation, and climate, encouraged bursts of innovation and diversification. As eukaryotic lineages expanded, the foundations for the Ediacaran and Cambrian periods were quietly forming. The world was moving toward an explosion of biological diversity unlike anything before. Complex body plans, tissues, organs, and behaviors would soon emerge. But all of these possibilities rested on the existence of eukaryotic cells, the cellular framework capable of building multicellular life. The emergence of eukaryotes marks one of the most transformative events in Earth's history. It is a story of cooperation between species, innovation born from adversity, and the merging of life's ancient branches. It represents the transition from a world of simple cells to a world capable of supporting complex organisms and ecosystems. With eukaryotes established and diversifying, Earth was ready for the next great evolutionary leap, the rise of multicellular life and the strange organisms of the Ediacaran world. The rise of eukaryotic cells marked a turning point in the history of life on Earth. But the next transformation would push biology into entirely new dimensions. For billions of years, life had existed only in microscopic forms, single cells drifting through oceans, clinging to sediments, or living within microbial mats. These cells were diverse and innovative, but each lived alone. Then, in a series of evolutionary steps that unfolded over hundreds of millions of years, some eukaryotic cells began working together. They formed colonies, shared responsibilities, and eventually fused into organisms composed of many cells. This transition, the emergence of the first multicellular life, opened the door to complex bodies, new behaviors, and ecosystems of unprecedented diversity. Multicellularity did not emerge in a single moment or in a single lineage. Instead, it evolved independently multiple times across different groups of eukaryotes in algae, fungi, plants, and animals. But long before these familiar groups appeared, early experiments in multicellularity were taking place in ancient oceans. Simple colonies formed when individual cells failed to separate after division. These clusters gained advantages. They were harder for predators to consume, better able to stay in nutrient-rich waters, and more resistant to environmental stress. Natural selection favored these cooperative groups. In the beginning, these colonies behaved much like their unicellular ancestors. Each cell performed the same functions: capturing energy, processing nutrients, and dividing when conditions allowed. But over time, specialization began to emerge. Some cells focused on movement, using flagella or cilia to propel the colony. Others took on reproductive roles, producing offspring, while non-reproductive cells supported the colony's structure. This division of labor marked a critical step toward true multicellularity. As cell groups grew larger, they required more organization. Chemical signaling evolved, allowing cells to communicate and coordinate activities. These signals regulated growth, reproduction, and differentiation. They enabled cells to respond collectively to changes in their environment. Communication allowed multicellular organisms to behave as unified individuals rather than loose assemblies of cells. With communication came complexity. Early multicellular organisms likely resembled gelatinous sheets, hollow spheres, or simple filaments drifting through shallow waters. They lacked tissues, organs, and symmetry. They moved slowly, if at all, yet they represented something entirely new on Earth. bodies composed of coordinated cells that work together for shared survival. These early forms laid the foundation for future innovations in structure and behavior. The environment played a crucial role in enabling multicellularity. After the snowball Earth glaciations ended, the climate stabilized. Oceans became richer in nutrients due to massive glacial erosion and runoff. Oxygen levels rose, providing the energy needed to support larger bodies. Chemical gradients in shallow seas, fueled by sunlight and tidal mixing, encouraged metabolic diversity. These conditions created ecological niches ideal for multicellular experimentation. Among the earliest known multicellular organisms were simple algae. Fossil evidence from this period includes red and green algae, some forming filamentous structures, others forming sheets or spherical colonies. These algae performed photosynthesis, contributing further to rising oxygen levels and shaping marine ecosystems. Their multicellular forms were stable and persistent, demonstrating the evolutionary staying power of cooperation. Fungi also began experimenting with multicellularity. Though early fungal lineages remain poorly understood in the fossil record, molecular evidence suggests that simple fungal networks emerged during this period. These organisms may have lived in association with microbial mats, recycling organic material and influencing nutrient cycles. In deeper waters and on the sea floor, other multicellular forms evolved unique strategies. Some formed soft-bodied structures resembling sponges, porous bodies that allowed water to flow through internal channels. These early sponge-like organisms may represent some of the earliest ancestors of the animal kingdom. They filtered nutrients from seawater, benefiting from the increased oxygen and nutrient availability of post-glacial oceans. These sponge-like creatures lacked nervous systems, muscles, or digestive tracts. But their organization signaled a major evolutionary breakthrough: the ability to build three-dimensional structures composed of different cell types. Their bodies contained specialized cells for feeding, support, and reproduction. They exemplified the earliest stages of tissue differentiation, the hallmark of animal life. As multicellular life spread, ecosystems changed dramatically. Microbial mats, once dominant in shallow waters, encountered competition from multicellular organisms that grazed on them or competed for space. Sediments became richer in organic material as multicellular forms shed cells, secreted mucus layers, and produced metabolic waste. Nutrient cycles intensified, driven by the interactions between unicellular and multicellular organisms. This period also saw the emergence of simple predators. Some multicellular organisms developed the ability to engulf or digest other cells. Although still rudimentary, these predatory behaviors marked the beginning of complex food webs. The presence of predators exerted evolutionary pressure on prey, encouraging defensive strategies such as clustering, hardening cell walls, or developing larger bodies. This predator-prey dynamic fostered innovation and diversification. The exact timing of the earliest multicellular organisms remains debated. Fossil evidence suggests that multicellularity may have begun more than 2 billion years ago, but stable and complex multicellular life became widespread only after 800 million years ago. The Ediacaran period, beginning around 635 million years ago, marks the first clear appearance of large multicellular organisms in the fossil record. Although the Ediacaran fauna belongs to the next chapter of Earth's history, its roots lie in the early experiments of primitive multicellular forms. As multicellular organisms evolved, they became increasingly specialized. Cells within these organisms communicated through chemical gradients and signaling molecules, ensuring coordination across the body. Some cells became permanent structural components, providing rigidity or flexibility. Others formed protective outer layers. Some specialized in capturing energy through photosynthesis or filtering nutrients from water. Reproductive cells diverged from somatic cells, ensuring the continuity of the organism while allowing for complex body structures. One of the major challenges multicellular organisms faced was the distribution of nutrients and waste. Larger bodies meant that diffusion alone was insufficient for transporting materials. Early organisms developed internal channels or relied on water flow to move nutrients. Sponges, for instance, used pores and canals to direct water through their bodies, capturing food particles in the process. These early transport systems set the stage for circulatory systems that would evolve later in animals. Movement also became more sophisticated. While many early multicellular organisms were sessile, attached to rocks or sediments, others developed simple forms of locomotion. Cilia and flagella coordinated across cells, generating waves that propelled organisms through the water. Coordinated movement required communication between cells, strengthening the evolutionary importance of signaling pathways. Multicellularity also influenced reproduction. Some organisms reproduced by releasing specialized reproductive cells into the water, allowing genetic mixing and increased diversity. Others reproduced asexually by splitting or budding. The combination of reproductive strategies promoted rapid evolution and adaptation. As multicellular life continued to diversify, entire ecosystems formed around these new organisms. Coral-like structures began to emerge, though true corals evolved much later. Mats of multicellular algae covered shallow seafloors, creating layered habitats. Sponge-like animals filtered water, while simple predators explored new ways of hunting. Sediments became more dynamic as organisms burrowed, anchored, or grazed across them. And still, the fossil record from this era remains sparse. Soft-bodied organisms rarely leave behind hard evidence. But the traces that do exist, impressions in sediment, chemical signatures, microfossils, reveal a world in transition. They display swirls, ridges, and patterns representing bodies that lived, grew, and interacted. These patterns demonstrate coordinated cell growth and organized body plans, milestones in the evolution of complexity. Environmental stability played a significant role in this expansion. After the snowball Earth glaciations, global temperatures moderated, ocean chemistry stabilized with increased oxygenation. Nutrient availability rose dramatically due to erosion and runoff. These changes created fertile conditions for larger organisms to thrive. Multicellularity flourished because the planet provided both the energy and the stability needed for complex life to succeed. The emergence of multicellularity also altered the planet's atmosphere and oceans. Photosynthetic algae increased oxygen production, further oxygenating shallow waters. This oxygenation supported the evolution of aerobic metabolism in multicellular organisms, allowing them to grow larger and more active. As oxygen levels rose, new ecological possibilities opened, paving the way for animal evolution. The first multicellular organisms were simple, but they embodied the essential characteristics that define complex life. They demonstrated division of labor, communication between cells, structural organization, and coordinated reproduction. From these foundations, the animal kingdom would later emerge. Sophisticated tissues, organs, and nervous systems were still far in the future, but the blueprint for complexity was already in place. Even the earliest steps, simple colonies hollow spheres, soft-bodied structures signaled an evolutionary direction that would transform the planet. Multicellularity enabled new interactions, new ecological relationships, and new possibilities for adaptation. It marked the end of a world dominated entirely by single cells and introduced the beginning of biological diversity that would eventually fill oceans, land, and sky. By the end of this period, multicellular life had taken root across Earth's oceans. Simple eukaryotic organisms thrived in shallow seas, forming the foundation for more complex forms to evolve. The stage was prepared for the next major chapter in Earth's history, the rise of the Ediacaran organisms, the first truly large and enigmatic multicellular creatures to inhabit the planet. After billions of years dominated by microbes and hundreds of millions of years of experimentation with early multicellularity, Earth entered a strange and extraordinary biological phase. Beginning around 635 million years ago, after the last snowball Earth glaciers retreated, a new world emerged. A world filled with soft-bodied organisms unlike anything alive today. This era is known as the Ediacaran period. It marked the first appearance of large, complex life forms visible to the naked eye, yet their bodies, behaviors, and evolutionary relationships remain mysterious. These organisms represented a grand experiment in multicellular life, exploring biological designs that would vanish before the rise of animals as we know them. The Ediacaran seas were warm, shallow, and rich in nutrients. Oxygen levels were rising, currents circulated more vigorously, and sediments carried minerals that fueled biological growth. The oceans were lit by sunlight that penetrated increasingly transparent waters. The planet had emerged from extreme ice ages, and with the thaw came a surge of evolutionary creativity, ecosystems reorganized. New forms spread across the seafloor, creating the first macroscopic landscapes of life. The earliest Ediacaran organisms were unlike any modern creatures. Many had no mouths, no digestive tracts, no muscles, and no recognizable organs. They came in simple geometric shapes: discs, fronds, tubes, ovals, spirals. Some lay flat against the seafloor, others rose like soft, leafy structures anchored in sediment. Their bodies were often quilted or segmented in repeating patterns, as if stitched together from soft compartments. Little evidence remains of their internal anatomy, suggesting that most had simple tissues and relied on diffusion to obtain nutrients and oxygen. One of the most iconic Ediacaran organisms was Dickinsonia. Shaped like an oval mattress with rib-like segments radiating from a central axis, Dickinsonia grew up to a meter long, making it one of the first large animals on Earth. Despite its size, it lacked a mouth or gut. It likely absorbed nutrients directly through its underside, living atop microbial mats. As it fed, it left behind footprints, shallow impressions in the sediment that preserve its movements across ancient seafloors. Another notable organism was Rungia, a frond-like creature with delicate branching patterns. It stood upright, like a soft fern anchored in the sediment. Each frond contained intricate vascula, like channels that increased surface area for absorbing nutrients. These patterns suggest a sophisticated method of capturing dissolved organic matter. Like many Ediacaran organisms, Rungia lacked hard parts and left behind only faint impressions in sandstone. Sprigina was another enigmatic form, shaped like a segmented worm, with a crescent-shaped head shield. It has long been debated as a possible precursor to early arthropods. Its bilateral symmetry, a body arranged into left and right halves, hinted at an evolutionary direction that would later dominate animal life. Yet, Sprigina vanished from the fossil record before the Cambrian explosion, leaving behind questions about its true lineage. Frond, like organisms such as Charnia, carpeted the seafloor, forming fields of soft, leaf-shaped bodies anchored like plants. Although they resembled modern sea pens or feather stars, they were structurally different, built from repeated branching modules that defy easy classification. Charnia likely absorbed dissolved nutrients directly from seawater, using its large surface area to maximize intake. Some ediacaran creatures floated freely. Others attached themselves to microbial mats. Some burrowed shallow impressions into the sediment. Yet few left behind evidence of active movement. The ediacaran world was not dominated by predators or mobile organisms. Instead, it was a gentle ecosystem where organisms mostly absorbed nutrients, filtered organic particles, or fed on microbial mats that covered the sea floor. The absence of predation created a unique evolutionary environment. Ediacaran organisms could grow soft, broad, and delicate without fear of being eaten. This allowed the evolution of large body sizes and unusual shapes. But it also meant that many ediacaran innovations were not built for the competitive pressures that would arise later during the Cambrian explosion. The sediments of the ediacaran world tell a detailed story of these organisms. Microbial mats covered much of the sea floor, forming thick, sticky layers that preserve the impressions of soft-bodied creatures. These mats stabilized sediments and created microenvironments rich in nutrients. Many ediacaran organisms depended on these mats for food, oxygen, and habitat. The relationship between microbial mats and early macroscopic life was one of the foundational ecological interactions of this period. The ediacaran experiment also included mobility. Though rare, some organisms developed the ability to move across the sea floor. Kimberella is one of the best examples. It had a soft, slug-like body and a hardened structure at its front that may have functioned like a scraping organ. Kimberella left behind feeding trails that show it grazed on microbial mats, marking one of the earliest known examples of directed feeding behavior. This organism hints at the transition toward more animal-like forms. The rise of mobility introduced new ecological dynamics. Organisms that could move, gained access to new feeding grounds, dominated more space, and avoided competition. These behaviors set the stage for the predatory interactions that would later revolutionize ecosystems during the Cambrian. The ediacaran environment supported various modes of life: suspension feeders, surface grazers, absorptive organisms, and possibly even early filter feeders. Though diversity was high, ecological interactions remained relatively simple. Competition existed, but predation was minimal. Niches were broad. Organisms coexisted without intense pressure to evolve defensive traits. This peaceful world would soon change. The biological innovations of the ediacaran period extended beyond body shapes. Some organisms showed evidence of coordinated growth and tissue specialization. Though simple, they represented early versions of developmental processes later refined in animals. For example, the quilted bodies of rangermorphs displayed fractal-like patterns, suggesting regulated growth from modular units. Such growth strategies allowed rapid expansion and efficient nutrient capture. Life in the ediacaran also expanded vertically. Some organisms grew tall fronds, reaching into higher water columns to access better light or nutrient currents. Others spread broad, leaf-like surfaces across the sea floor. These variations increased ecological complexity, allowing organisms to partition resources more effectively. Spatial structuring. The idea that different organisms occupy different layers or zones began to develop in the oceans. The global distribution of Ediacaran fossils reveals that these organisms lived in diverse environments across multiple continents. Fossil beds in Australia, Russia, Namibia, Canada, and the United Kingdom display similar body plans, suggesting that Ediacaran life spread widely and adapted to a variety of conditions. The worldwide presence of these fossils indicates that Ediacaran ecosystems were interconnected by ocean currents and favorable climate conditions. Another remarkable feature of the Ediacaran period is trace fossils. Though many organisms lacked hard parts, they sometimes left behind tracks, grooves, or tunnels in the substrate. These traces reveal behavior, something fossils rarely capture. Some traces show organisms moving in deliberate paths, suggesting sensory systems capable of detecting chemical or physical cues. Others show evidence of burrowing, which would later become a key ecological innovation. Burrowing allowed organisms to access buried nutrients, oxygenate sediments, and reshape seafloor environments. As the Ediacaran period progressed, environmental changes began altering ecosystems. Oxygen levels continued to rise, nutrient availability fluctuated, sea levels shifted due to tectonic movements. Microbial mats, once widespread, began to decline in some regions as burrowing organisms disrupted their structure. This disruption marked the beginning of bioturbation, the mixing of sediments by living organisms. Bioturbation changed the chemistry and stability of sediments, impacting organisms that relied on microbial mats. Some Ediacaran organisms adapted to these changes. Others could not. The decline of microbial mats reduced the habitat and food source for many mat-dependent species. The emergence of more mobile and active organisms introduced competition. New behaviors, such as grazing and burrowing, reshaped the ecosystem. Although the Ediacaran experiment produced remarkable diversity, it was fragile, dependent on environmental stability and low predation pressure. Toward the end of the Ediacaran, extinction waves began affecting these organisms. The exact causes remain uncertain. Possibilities include climatic fluctuations, ocean chemistry shifts, rising predation from newly evolving animals, and ecological competition. What is clear is that many Ediacaran lineages vanished completely before the Cambrian period began. Their disappearance opened ecological space for the dramatic biological explosion that would follow. The Ediacaran experiment was a unique moment in Earth's history, a period when life explored forms and strategies that have no modern parallels. Though few Ediacaran organisms gave rise directly to modern animals, the period provided essential evolutionary groundwork. It demonstrated that multicellularity could produce large bodies, complex shapes, and coordinated behaviors. It tested developmental pathways, ecological roles, and structural possibilities. The Ediacaran world was a canvas of soft life, painted with fronds, discs, segmented ovals, and quilted forms. It was a quiet world, free from predation, dominated by gentle feeding strategies and slow movements. But it was also a world preparing for transformation. Beneath the surface of these soft-bodied experiments, evolutionary mechanisms were gearing up for the next chapter, a chapter defined by innovation, arms races, and rapid diversification. As the Ediacaran period came to a close, the stage was set for one of the most extraordinary events in the history of life, the Cambrian explosion. After the quiet, soft-bodied world of the Ediacaran came one of the most dramatic turning points in the history of life on Earth. Around 541 million years ago, biological innovation accelerated at a pace never seen before. Ecosystems transformed, new body plans emerged, predators burst onto the scene. Shells and skeletal structures appeared for the first time. Life diversified into nearly every major animal group known today. This extraordinary moment is called the Cambrian explosion, not an instant event, but a rapid geological interval during which complexity flourished and the foundations of modern animal life were established. The Cambrian seas were warm, shallow, and filled with oxygen. Tectonic activity created extensive continental shelves bathed in sunlight. Nutrient-rich runoff flowed into oceans, stimulating productivity. Rising oxygen levels allowed organisms to grow larger and develop energy-demanding tissues such as muscles, nerves, and circulatory systems. The biological and environmental conditions aligned perfectly for evolutionary experimentation. One of the defining features of the Cambrian explosion was the sudden appearance of hard parts: shells, exoskeletons, spines, and teeth. These structures provided protection from predators, support for movement, and new ways of interacting with the environment. The fossil record from this time is rich because these hard parts preserved well, capturing the details of organisms that would otherwise have disappeared without a trace. Trilobites became some of the most iconic inhabitants of the Cambrian seas. These arthropods possessed segmented bodies, jointed legs, and hard exoskeletons. They crawled across the seafloor, burrowed in sediments, or swam gracefully through the water. Trilobites developed compound eyes made of calcite, some of the earliest and most sophisticated visual systems in the animal kingdom. Their diversity exploded, producing hundreds of species with unique shapes and behaviors. Trilobites represent the power of adaptation during this era, flourishing across varied environments. Another remarkable creature was Anomalocaris, often considered the first apex predator. It grew up to a meter long, a giant of its time. With large compound eyes, a flexible body, swimming lobes, and ring-shaped jaws lined with hard plates, Anomalocaris hunted trilobites and other prey with precision. Its rise signaled a major shift in ecosystem dynamics. The presence of predators introduced evolutionary pressure, driving prey to develop defenses such as armor, burrowing behaviors, and escape strategies. Hallucigenia, a small but bizarre organism, walked on spindly legs while sporting long dorsal spines for protection. Its unusual appearance puzzled scientists for decades, but it represents the experimentation of the Cambrian, a time when life tested biological designs that sometimes bordered on the surreal. The Cambrian explosion introduced diverse body plans known as phyla, the highest major groups in animal classification. Many modern phyla emerged during this time, including arthropods, mollusks, annelids, echinoderms, brachiopods, chordates, and cnidarians. Each phylum represents a distinct blueprint of body organization. These blueprints, once established, persisted for hundreds of millions of years and still define animal diversity today. One of the most significant developments during the Cambrian was the evolution of the chordates, the group that includes fish, amphibians, reptiles, birds, mammals, and eventually humans. Early chordates such as Picaia and Hycoichthys possessed flexible rod-like structures called notochords, which supported their bodies and allowed undulating swimming motions. They also had segmented muscles, primitive nervous systems, and early versions of gill structures. Though small and simple, these ancestors marked the beginning of a lineage that would dominate vertebrate evolution. The Cambrian seas teemed with brachiopods, shelled filter feeders resembling clams and mollusks, including early snails and soft-bodied ancestors of squids. Echinoderms, distant relatives of modern starfish, appeared in primitive forms with radial symmetry, Cnidarians, the group that includes jellyfish and corals, diversified into new shapes and sizes. Burrowing behaviors became widespread during the Cambrian. Organisms dug into sediments for protection or to access buried food sources. These burrows transformed seafloor environments, oxygenating sediments and altering chemical cycles. Bioturbation, the mixing of sediments by living organisms, reached new levels, impacting nutrient availability and reshaping ecosystems. Skeletonization was a major evolutionary innovation. Organisms began secreting calcium carbonate or calcium phosphate to build shells and protective structures. The availability of minerals in seawater facilitated this process. Skeletons allowed for greater mobility, structural support, and predator resistance. They also created new ecological opportunities, such as reef building and complex habitat formation. The Cambrian explosion was fueled not only by external environmental change, but also by internal genetic developments. One of the most important innovations was the evolution of Hox genes, master regulatory genes that control the layout of body plans. Hox genes guide the formation of segments, limbs, organs, and overall body structure. Once these genes evolved, they enabled rapid diversification, because small genetic changes could produce significant differences in anatomy. This flexibility accelerated evolution, allowing organisms to explore a vast range of body designs. Ecological interactions also drove diversification. Predator-prey, arms races created selective pressures that encouraged rapid adaptation. Predators evolved better senses, mobility, and weapons, while prey evolved armor, camouflage, and defensive strategies. Competition for food and space encouraged organisms to occupy new niches, leading to the diversification of species and ecological roles. The Cambrian seas grew increasingly complex. Reefs formed from early sponges and coral-like organisms, creating three-dimensional habitats. Planktonic organisms drifted through sunlit waters, forming the base of food chains. Scavengers roamed the sea floor, feeding on organic debris. Filter feeders pumped water through specialized structures, capturing suspended particles. Predators patrolled the middle waters. Every layer of the ocean became an arena for life, filled with interactions and behaviors that defined ecological communities. Soft-bodied organisms that had dominated the Ediacaran world declined dramatically. Some were outcompeted by more active, armored Cambrian animals. Others could not survive the rise of predators. As ecological pressure intensified, the gentle Ediacaran world faded, replaced by a dynamic and often violent ecosystem shaped by competition and survival. Major fossil sites, such as the Burgess Shale in Canada and the Chengjiang Formation in China, provide exquisite snapshots of Cambrian life. Their exceptional preservation reveals detailed anatomy of soft-bodied organisms, offering rare insights into the diversity of ancient ecosystems. Creatures preserved in these deposits include Opabenia with 5 eyes and a proboscis-like appendage, Wywaxia covered in protective scales, and Morella, a delicate arthropod with intricate spines. These fossils display the experimental nature of evolution during the Cambrian, a period when evolution seemed to invent new designs with extraordinary freedom. As the Cambrian period progressed, ecosystems stabilized somewhat. The rapid burst of new body plans slowed, and many experimental forms vanished. The major phyla solidified into recognizable lineages that would persist for hundreds of millions of years. The world had transitioned from a planet dominated by microbial mats and soft-bodied organisms to one filled with armored predators, burrowing creatures, and complex food webs. This transformation set the stage for future evolutionary advancements. Oxygen levels continued to rise, supporting larger body sizes and more active lifestyles. Nutrient cycles intensified, driven by biological activity. Tectonic processes reshaped oceans and coastlines, influencing habitats and promoting further diversification. Evolutionary innovation continued, but the foundational explosion of body plans had already established the blueprint for future life. The Cambrian explosion was not merely a moment of rapid evolution, it was a permanent shift in the trajectory of life. Every animal on Earth today traces its ancestry to creatures that first appeared during the Cambrian. The basic structures of eyes, limbs, digestive systems, muscles, nerves, and circulatory networks were all established during this time. The architecture of life became increasingly modular, allowing new adaptations to arise through variations on established themes. The presence of predators for the first time changed the behaviors of organisms dramatically. Hiding, burrowing, swimming, camouflage, and hard shells all emerged as responses to predation. Ecosystems became dynamic rather than static. The Cambrian explosion transformed oceans into complex arenas of interaction, innovation, and survival. By the end of the Cambrian, the stage was set for further developments in animal evolution. The earliest vertebrates were poised to rise. Ecosystems became more interconnected. Marine life grew more sophisticated. Plants and fungi were preparing for their eventual colonization of land. The Cambrian explosion had created the biological foundation upon which all future life would build. It was a turning point, a moment when Earth shifted from simple multicellularity to a world of predators, prey, shells, eyes, limbs, and breathtaking diversity. Evolution had taken a bold leap forward, and nothing would ever be the same. After the Cambrian explosion reshaped the living world with predators, hard shells, complex body plans, and dynamic ecosystems, the oceans entered a new era of biological expansion. During the Ordovician and Silurian periods, life did not simply diversify, it spread into every corner of the seas. New ecosystems emerged in deep waters, on continental shelves, and within reef systems flourishing in warm, sunlit shallows. Marine life became more structured, more interconnected, and more complex. The oceans transformed into vast theatres of evolution, where countless organisms explored new strategies for feeding, moving, defending, and reproducing. In the Ordovician seas, trilobites remained abundant, but they were no longer the sole dominant group. Brachiopods, with their hinged shells, flourished on seafloors, attaching themselves to rocks or soft sediments. Some developed long stalks that lifted their shells above the substrate, accessing nutrient-rich currents. Bryozoans, colonial organisms that built intricate lattices of calcium carbonate, spread across seafloors like living carpets. These colonies created structured habitats that sheltered small organisms, contributing to the complexity of marine environments. Coral-like organisms also began building reefs, forming barriers and platforms that reshaped coastlines. While these early reefs were not dominated by true corals, they provided similar ecological roles. Reefs supported fish-like creatures, arthropods, mollusks, and countless invertebrates. They created shelter, feeding grounds, and nurseries. As these ecosystems expanded, the complexity of interactions between species grew dramatically. Cephalopods, distant relatives of modern squids and octopuses, became formidable predators of the Ordovician seas. Some developed long, straight shells, while others evolved coiled shells for better mobility. These cephalopods used jet propulsion to move swiftly, hunting trilobites and soft-bodied prey. Their rise marked a new level of sophistication in predatory behavior. They had sharp beaks, powerful tentacles, and keen sensing abilities. For the first time in Earth's history, ocean predators were not just opportunistic hunters, but intelligent, adaptable, and versatile. The Ordovician period also saw major advancements in jawless fish. Though they lacked jaws, these early vertebrates known as agnathans possessed cartilaginous skeletons, gill structures, and primitive sensory systems. They filtered particles from the seabed or scavenged organic matter. Some developed bony armor plates on their heads and bodies, providing protection against predators. This early armor would later influence the evolution of bony fish and armored aquatic vertebrates. As life expanded in the oceans, primary productivity increased significantly. Plankton, tiny drifting organisms, flourished in sunlit upper waters. Phytoplankton performed photosynthesis, producing vast amounts of oxygen and forming the base of marine food webs. Zooplankton fed on phytoplankton, providing prey for larger organisms. This planktonic boom supported the expansion of predators at every level, from tiny crustaceans to giant cephalopods. The Ordovician oceans were rich in biodiversity, but they also experienced profound environmental change. Plate tectonics shifted continents and opened new ocean basins. Sea levels rose and fell. Volcanic activity altered atmospheric composition. One of the most significant geological events of the time was the formation of the Appalachian Mountains, whose erosion enriched oceans with minerals that fueled life. These environmental changes shaped ecosystems, driving evolutionary innovation and diversification. Yet this dynamic age ended abruptly. Around 444 million years ago, the Ordovician-Silurian mass extinction struck, eliminating nearly 85% of marine species. Likely triggered by a combination of global cooling, glaciation, and falling sea levels, this extinction drastically reshaped marine life. Shallow seas disappeared as ice sheets expanded, destroying habitats. Organisms adapted to warm waters struggled to survive, trilobites suffered major losses, and many brachiopods, bryozoans, and reef builders vanished. But extinctions, while devastating, often open ecological opportunities. Survivors evolved rapidly in the aftermath, rebuilding ecosystems during the Silurian period. As Earth warmed again, sea levels rose, flooding continental shelves. New reef systems formed, now dominated by organisms more similar to modern corals. These reefs teemed with life, serving as hotspots of evolution. During the Silurian, fish underwent major evolutionary advancements. Jaws evolved a breakthrough that transformed vertebrate biology. Early jawed fish, known as placoderms, developed armored plates on their heads and thoraxes. Their jaws allowed them to bite, crush, and manipulate prey with far greater control than jawless fish. This innovation opened new feeding strategies, from active predation to the consumption of hard-shelled organisms. The evolution of jaws was one of the most significant steps in vertebrate evolution, setting the stage for sharks, rays, and eventually land vertebrates. Cartilaginous fish, the ancestors of modern sharks, also began emerging. Early forms had streamlined bodies, paired fins, and powerful tails. They were agile predators, hunting fish and invertebrates with increasing speed and precision. Their development marked the birth of true piscine predators capable of dominating marine ecosystems. Bony fish, another major vertebrate lineage, also appeared during this time. Unlike cartilaginous fish, bony fish developed internal skeletons made of bone. They evolved swim bladders, internal gas-filled organs that allowed them to control buoyancy. This adaptation enabled them to inhabit deeper waters, hover effortlessly, and maneuver with precision. The rise of bony fish diversified marine vertebrate ecosystems further. Marine plants and algae continued spreading across coastal regions. Photosynthetic organisms expanded their range, growing in shallow waters and creating oxygen-rich habitats. These zones supported grazing organisms, filter feeders, and predators, forming early versions of modern coastal ecosystems. Arthropods also diversified. Eurypterids, giant sea scorpions, became some of the top predators. Some eurypterids grew over 2 meters long, with powerful claws, segmented bodies, and armored exoskeletons. Their dominance in shallow seas demonstrated the competitive intensity of marine life. Other arthropods, such as early crustaceans, scuttled across seafloors or swam through water columns, feeding on detritus, plankton, or small fish. As life flourished, ecosystems grew increasingly interconnected. Predators influenced prey populations. Prey shaped predator evolution. Coral reefs created refuges for smaller organisms, encouraging biodiversity. Sediment burrowers, oxygenated seafloors, filter feeders cleaned water and redistributed nutrients. Every organism contributed to a web of interactions that supported the entire marine environment. By the late Silurian, the oceans had become highly complex. Reef systems expanded across tropical regions. Vertebrates diversified rapidly. Arthropods evolved new forms. Plankton productivity remained high. Earth's marine ecosystems were vibrant, dynamic, and filled with evolutionary experimentation. One of the most profound consequences of oceanic diversification was the gradual emergence of organisms capable of exploring environments beyond water. Plants and algae began colonizing damp shorelines. Arthropods ventured onto tidal flats, breathing air through simple respiratory structures. Fish developed stronger fins and internal systems that would one day allow them to crawl onto land. Though the conquest of land belongs to later chapters, it began with the innovations forged during the ocean's golden age. The oceans of this era were not just habitats, they were evolutionary engines. New sensory systems evolved, including primitive lateral lines in fish that detected water movement. Eyes became more refined across many lineages. Nervous systems grew more complex. The evolution of jaws revolutionized feeding. Fins evolved into structures capable of finer control. Respiratory systems became efficient at extracting oxygen from water. Reefs, in particular, became centers of innovation. They offered shelter, competition, and varied resources. Organisms developed camouflage, mimicry, and predatory strategies. Some evolved symbiotic relationships with algae or bacteria. These interactions drove diversification, reinforcing the role of reefs as evolutionary hotspots. The conquest of the oceans also shaped Earth's climate. Photosynthetic organisms continued producing oxygen, gradually increasing atmospheric levels. Marine life helped regulate carbon dioxide by sequestering carbon in shells and sediments. Over time, these processes stabilized climate patterns, influencing everything from ocean circulation to atmospheric chemistry. Mass extinctions punctuated this era, each reshaping ecosystems and opening opportunities for survivors. Each recovery period brought bursts of evolutionary innovation. Life in the oceans displayed resilience and adaptability, continually evolving in response to environmental challenges. By the end of this chapter, the oceans had become unrecognizable compared to their early days. What began as simple microbial environments had transformed into dynamic kingdoms of fish, arthropods, mollusks, cephalopods, corals, and countless other organisms. The foundations of modern marine biodiversity were firmly in place. But evolution was not finished expanding its reach. Soon, life would take one of its most dramatic steps, leaving the oceans and venturing onto land, reshaping the planet forever. For billions of years, Earth's land masses were barren landscapes of rock, sand, and volcanic debris. Continents were shaped by tectonics, carved by wind and water, and sculpted by long eras of geological activity, but no green life yet covered the surface. Everything above the shorelines was empty. The only signs of water-driven erosion came from rain and rivers. The only colors came from minerals and weathered stone. But during the Silurian and early Devonian periods, a profound transformation began. Life, which had thrived in the oceans, made a bold leap onto land, and the first pioneers to reshape the continents were plants.
It was an astonishing vision of a completely unknown world, a world that had existed since the beginning of time. All sorts of things that you've no idea ever existed, all in a multitude of colors, all unbelievably beautiful.
The conquest of land was neither sudden nor simple. It unfolded step by step as different groups of algae gradually adapted to terrestrial environments. The earliest land-dwelling photosynthetic organisms were likely microbial mats of cyanobacteria and simple algae that formed thin films on moist rocks. These primitive colonizers survived where waves splashed coastal rocks or where tide pools evaporated and refilled. They could withstand drying for limited periods, anchoring themselves to sediment and rock surfaces and altering the landscape for the first time. The ancestors of true land, plants, were green algae, specifically a group known as charophytes. These algae lived in shallow freshwater environments where fluctuating water levels created conditions that favored survival during occasional drying. Over millions of years, charophyte-like organisms accumulated adaptations that made the transition to land possible. These included protective structures to prevent desiccation, reproductive strategies that did not rely on open water, and simple mechanisms for nutrient uptake from substrates rather than surrounding water. The earliest terrestrial plants appeared around 470 million years ago. They were tiny, soft, and simple, far from the towering forests that would come later. These early plants resembled modern mosses and liverworts. They lacked true roots, stems, or leaves. Instead, they had flattened bodies only a few centimeters tall, spreading across damp surfaces along rivers, lakes, and coastlines. Their tissues could absorb water directly from the environment, but they were vulnerable to drying. Thus, these pioneer plants could survive only in consistently moist environments. Though small, these plants changed Earth profoundly. They trapped sediments with their bodies, reducing erosion. They stabilized soils along waterways. They began cycling nutrients on land through growth and decay. And most importantly, they initiated the long-term transformation of atmospheric carbon dioxide by performing photosynthesis on the continents for the first time. One of the major challenges for early plants was reproduction. In aquatic environments, gametes could simply drift through water. On land, reproduction required new strategies. Many of the earliest plants continued to rely on water for fertilization. Their sperm needed moisture to swim to eggs. This dependence limited their distribution, confining them to wet habitats. But it was a crucial early step in plant evolution. As the Devonian period began, plants evolved new structures that allowed them to grow taller, spread farther, and inhabit drier environments. The evolution of vascular tissue, specialized tubes for transporting water and nutrients, revolutionized plant life. These tubes, known as xylem and phloem, allowed plants to maintain internal water pressure and survive away from constant moisture. Vascular tissues also provided structural support, enabling plants to grow upright. The first vascular plants, such as Cooksonia, appeared around 430 million years ago. They were still small, only a few centimeters tall, with simple branching stems and no true leaves. Their sporangia spore-producing structures sat atop their stems. Though these plants had limited size and complexity, their ability to stand upright represented a major evolutionary leap. They could capture more sunlight, disperse spores more widely, and access new ecological niches. As vascular plants diversified, they developed roots, specialized organs that anchored them into the soil and absorbed water and nutrients. Roots allowed plants to grow in more stable and predictable ways, colonizing areas beyond the reach of constant surface moisture. With roots came the ability to break down rock into soil more effectively. Roots penetrated cracks, secreted organic acids, and initiated chemical weathering on unprecedented scales. Continents began transforming beneath these pioneering forests of small vascular plants. Leaves evolved soon after. Early leaves were simple flaps of tissue that increased surface area for photosynthesis. Over millions of years, leaves became more complex, developing veins, cuticles, and stomata, tiny regulated pores that allowed gas exchange while minimizing water loss. With leaves, plants could capture sunlight more efficiently and produce more biomass. Landscapes grew greener and more productive. By the mid-Devonian, forests of primitive trees had begun to form. Early trees such as Archaeopteris and Cladoxylopsids evolved woody tissues that allowed them to grow tall, reaching heights of 10 meters or more. These trees had root systems that stabilized soils and influenced river systems. Their canopies altered climate by increasing transpiration, the release of water vapor from leaves into the atmosphere. Forests shaded the ground, cooled local climates, and created new ecological niches for animals and fungi. The development of spores and later seeds played central roles in the expansion of land plants. Spores, protected by resistant outer coatings, allowed plants to reproduce across greater distances. They could survive harsh conditions and remain dormant until moisture returned. But spores still required water at some stage of fertilization. Eventually, plants evolved seeds resilient, nutrient-packed capsules that protected developing embryos and enabled reproduction independent of standing water. However, this would occur later in the Devonian and Carboniferous periods. The colonization of land by plants transformed Earth's atmosphere. As forests expanded, plants absorbed massive amounts of carbon dioxide during photosynthesis. This reduction in carbon dioxide contributed to long-term cooling trends. At the same time, plants released oxygen into the atmosphere, increasing concentrations and fueling the evolution of larger, more complex animals. The arrival of plants also reshaped the soil. Before plants, soils were thin or non-existent. Decomposing plant matter created organic rich layers that held water and nutrients. This enriched soil provided a foundation for future ecosystems, including the colonization of land by arthropods and eventually vertebrates. Fungi also played a crucial role in this process. Mycorrhizal fungi formed symbiotic relationships with early plants, helping them absorb nutrients in exchange for carbohydrates. These partnerships were essential for the success of terrestrial plants and remain fundamental to modern ecosystems. As plants spread across continents, they created the first terrestrial food webs. Fungi decomposed dead plant material. Detritivores fed on decaying tissues. Arthropods grazed on leaves and spores. Predators hunted these arthropods. For the first time, the land supported complex ecological interactions. Plants provided shelter, food, and stability to a world that had been barren for billions of years. The rise of land plants also influenced waterways. Roots stabilized riverbanks, reducing sediment erosion. This stability led to meandering river systems and the formation of floodplains. Plants slowed water flow, creating wetlands that supported new forms of life. As rivers evolved, so did the organisms that inhabited them. Fish and amphibious vertebrates found new habitats in swampy environments created by vegetation. By the late Devonian, land plants had become towering forest ecosystems. Lycophytes, horsetails, and early ferns dominated the landscape. Some lycophytes grew over 30 meters tall. These forests created deep shade, stratified habitats, and complex microclimates. The expansion of forests also contributed to one of Earth's most significant environmental transformations, a major drop in atmospheric carbon dioxide. This cooling may have contributed to Devonian glaciations and mass extinctions, illustrating the profound impact plants could have on global climate. Plants also altered nutrient cycles. They drew minerals from deep soils and released them through leaf litter, creating cycles that enriched upper soil layers. This nutrient flow fed fungi, arthropods, and early terrestrial vertebrates. The emergence of forests accelerated the weathering of rocks, which pulled carbon dioxide from the atmosphere and helped regulate Earth's climate over millions of years. As plant diversity increased, so did structural complexity. Some plants developed seeds, which protected embryos from desiccation and allowed plants to colonize drier environments. Gymnosperms' early seed plants appeared near the end of the Devonian. Their seeds allowed them to spread into uplands and more arid zones, further expanding the range of terrestrial ecosystems. Fungi evolved alongside plants, becoming major decomposers on land. Giant fungi such as prototaxites, towering structures several meters tall, dominated early terrestrial landscapes before being replaced by trees. Fungi formed essential symbiotic relationships and developed the ability to break down tough plant tissues like lignin. Without fungi, forests would have been buried under their own debris, and nutrient cycles would have stagnated. The colonization of land by plants did more than transform ecosystems. It transformed the entire planet. The air became richer in oxygen. Soils deepened. River systems changed form. Climate shifted. Continents turned green. New habitats emerged for arthropods, which would soon take their own tentative steps onto land. Amphibious vertebrates would follow, marking another profound evolutionary milestone. By the end of this chapter, the once barren continents had become living landscapes. From tiny moss like pioneers to giant Devonian forests, plants had reshaped the world in ways that would continue to influence life for hundreds of millions of years. The stage was now set for the next great leap in Earth's history, the arrival of animals onto land, an event that would forever change the planet's evolutionary trajectory. As plants transformed barren continents into lush green landscapes, a new opportunity emerged for life. For the first time in Earth's history, land offered food, shelter, and stable habitats. But leaving the water was no simple task. Oceans had been the cradle of life for billions of years. Water supported bodies, facilitated movement, protected delicate tissues and provided oxygen-rich environments for gills. Land, in contrast, was harsh. Gravity pulled on unprotected bodies. Air dried out exposed tissues. Temperatures fluctuated dramatically, and oxygen had to be taken from the atmosphere rather than dissolved water. Yet, slowly, step by step, life began to crawl out of the oceans. The first land animals were small, fragile, and few, but they initiated one of the most important expansions in evolutionary history. Long before vertebrates ventured onto land, arthropods made the leap. Arthropods were well suited for terrestrial life. Their hard exoskeletons reduced water loss and provided structural support. Jointed legs allowed them to move efficiently on solid surfaces. Their bodies were already adapted to life at the interface of land and water, thanks to ancestors that lived in shallow seas, tidal flats, and near-shore environments. The earliest known terrestrial arthropods appeared around 440 million years ago, during the late Ordovician and early Silurian periods. These pioneering creatures likely resembled today's millipedes, centipedes, mites, and primitive insects. Many fed on decaying plant matter or microbial mats that grew on moist soils. Others were predators, hunting smaller arthropods or feeding on soft-bodied invertebrates. These early land animals helped create the first terrestrial food webs and accelerated the breakdown of plant material, enriching soils with nutrients. Millipede-like organisms were among the first true residents of land. Fossils such as Pneumodesmus from the Silurian period show clear evidence of spiracles, breathing holes used for air respiration, indicating genuine terrestrial adaptation. These creatures likely fed on detritus and plant fragments, establishing themselves as important decomposers. Centipede-like arthropods, equipped with venom claws and strong legs, became some of the earliest land predators. Agile and fast, they hunted smaller organisms in the leaf litter and along riverbanks. Their predatory lifestyles encouraged the evolution of defensive adaptations in prey species, sparking early terrestrial arms races. Insects also began their long evolutionary story during this time. Although the earliest insects may have lived in freshwater habitats, some early forms ventured onto land during the Devonian. Their bodies evolved waxy coatings to reduce water loss and tracheal systems to breathe air efficiently. Insects would eventually become the dominant animal group on land, but their true explosion would occur later, after the evolution of wings. Arachnids, the group that includes spiders, scorpions, and mites, were also early pioneers. Scorpion fossils from the Devonian display adaptations that allowed them to breathe air, suggesting they spent part of their time on land. Early spiders likely evolved from aquatic ancestors that spun silk for capturing prey or protecting eggs. Over time, spiders became agile terrestrial predators, using venom, webs, and stealth to dominate small prey. While arthropods spread across land with growing success, vertebrates lagged behind. Fish had dominated oceans for millions of years, but their bodies were not initially suited for terrestrial environments. Their gills collapsed in air. Their fins could not support weight. Their eyes dried out, and their diets were tied to aquatic food webs. Nevertheless, environmental pressures and opportunities pushed vertebrates toward the shoreline. The first steps toward terrestrial vertebrates began in shallow, swampy waters, where lobe-finned fish such as Eusthenopteron and Panderichthys evolved stronger, bone-supported fins. These fins were capable of bearing weight, allowing fish to push themselves along the bottom of muddy lakes and rivers. Living in environments prone to droughts or fluctuating water levels, some fish developed lungs derived from primitive air sacs. These organs allowed them to gulp air when oxygen levels in water became low, providing a tremendous advantage during environmental stress. Tiktaalik, often called a fisherpod, represents one of the most iconic transitional forms, living around 375 million years ago. Tiktaalik possessed both fish-like and tetrapod-like features. It had fins with wrist-like bones, allowing it to support part of its weight. It had a flat skull with eyes on top, suitable for peering above water. It had a neck, a trait absent in fish, enabling its head to move independently of its body. Although not fully terrestrial, Tiktaalik could navigate shallow waters and mudflats, edging closer to life on land. True tetrapods, four-limbed vertebrates, emerged soon after. Early tetrapods, such as Acanthostega and Ichthyostega, still lived primarily in water, but had limbs capable of walking in shallow environments. Acanthostega had 8 fingers on each hand, and limbs suited more for paddling than walking. Ichthyostega, more robust, could haul itself onto land, but likely moved awkwardly. These early tetrapods were not fully terrestrial animals. Instead, they were amphibious, exploring the interface between water and land. The transition from water to land required numerous evolutionary innovations beyond limbs and lungs. Vertebrates needed stronger backbones and rib cages to support their bodies. They needed sensory adaptations to see and hear in air rather than water. They needed skin resistant to drying, though early tetrapods still relied heavily on moist environments. Their circulatory systems had to adapt to changes in pressure and oxygen intake. Each adaptation represented millions of years of gradual change. As vegetation spread across continents, new ecological opportunities emerged. Lush Devonian forests created shaded wetlands, swampy floodplains, and streams filled with leaf litter. These environments provided shelter, food, and breeding grounds for early amphibious vertebrates. Insects and other arthropods offered new food sources. Predators and prey established new interactions that drove further evolutionary refinement. By the late Devonian, tetrapods had diversified into various forms, occupying different ecological roles. Some hunted small arthropods along riverbanks. Others remained mostly aquatic, but used limbs to navigate dense vegetation. Vertebrate life on land remained limited, but the foundations for future expansion were firmly established. However, this era was also marked by significant environmental challenges. Late Devonian extinctions, likely driven by global cooling, ocean anoxia, and habitat loss from the spread of forests, affected both marine and freshwater ecosystems. Many early tetrapods disappeared, but the survivors carried forward the traits necessary to thrive on land, paving the way for the evolution of true amphibians. Amphibians became the first widespread vertebrate inhabitants of land. They developed stronger limbs, more advanced lungs, and sensory systems adapted to terrestrial environments. Though still tied to water for reproduction, laying eggs that required moisture, amphibians spread across wetlands and forest floors. They fed on insects, worms, and other small animals, expanding terrestrial food webs further. Arthropods and tetrapods began shaping the land in ways that influenced global ecosystems. Burrowing animals aerated soil. Decomposers accelerated nutrient cycles. Predators and prey established dynamic interactions. The land, once lifeless, became a vibrant and complex biosphere. The colonization of land by animals also impacted Earth's climate and chemistry. Burrowing organisms increased soil turnover, spreading nutrients. Herbivorous arthropods fed on plants, influencing vegetation patterns. Early terrestrial predators introduced new ecological pressures, driving adaptation and diversification. Ecosystems grew more structured, feeding behaviors became more complex, and habitats diversified. As time progressed, vertebrates continued adapting to terrestrial life. Some developed more efficient lungs. Others evolved tougher skin. Limb structures became stronger and more refined. Eventually, the first amniotes, animals capable of laying eggs protected from desiccation, would emerge, freeing vertebrates from their dependence on water for reproduction. This leap would allow vertebrates to conquer drier environments, deserts, uplands, and open plains. But that development lies ahead. During the Devonian period, land animals were still pioneers, exploring a new frontier filled with challenges and opportunities. They were the first to leave footprints on ancient soils, the first to breathe air through lungs, the first to listen to the sounds of wind and rustling plants. Their arrival represented one of the most profound transitions in Earth's biological history. From the oceans to the forests, life had begun reshaping the continents with movement, behavior, and ambition. And soon, with the evolution of more advanced vertebrates, reptiles, and eventually dinosaurs, the land would become a stage for evolutionary dramas on a scale never before seen. After plants and animals first colonized the land, Earth entered a period of extraordinary ecological expansion. During the Carboniferous period, beginning around 359 million years ago, the continents transformed into lush landscapes filled with towering forests, sprawling swamps, and dense undergrowth. These forests created habitats teeming with life and dramatically altered the atmosphere. Insects, arthropods, and amphibians thrived in this world, some reaching gigantic sizes thanks to unusually high oxygen levels. The rise of giant forests and insects marked a unique chapter in Earth's history, one defined by immense biomass, evolutionary experimentation, and profound planetary transformation. The Carboniferous world was warm, humid, and rich in rainfall. Vast regions near the equator were covered in wetlands. Shallow seas, lagoons, and river systems meandered through continents blanketed by vegetation. The atmosphere contained high concentrations of oxygen, far higher than today, reaching levels of up to 35% at peak intervals. This oxygen-rich air created conditions that were both beneficial and challenging for life. One of the defining features of the Carboniferous was the development of enormous forests built by primitive trees. Unlike modern conifers or flowering trees, these ancient plants belonged to groups such as lycophytes, horsetails, and ferns. Lycophytes like Lepidodendron towered over 30 meters high with thick, scaly trunks and crowns of narrow leaves. Sigillaria, another giant lycophyte, grew in straight columns with patterned bark. Horsetails of the genus Calamites grew in bamboo-like clusters, some reaching heights of 20 meters. Seed ferns, early relatives of modern seed plants, spread across forest floors and developed seeds long before flowering plants evolved. These forests created layered ecosystems. Towering trees formed dense canopies that filtered sunlight. Beneath them, smaller plants filled the understory, and beneath that, mosses, ferns, and fungi blanketed the ground. Swampy pools and muddy floor-beds supported a rich diversity of organisms. The dense vegetation trapped moisture, maintained humidity, and influenced weather patterns. These forests were not simply collections of trees, they were vast ecosystems shaping the atmosphere itself. One of the most significant biological consequences of these forests was the dramatic increase in atmospheric oxygen. Plants absorbed carbon dioxide and released oxygen through photosynthesis. Because the Carboniferous environment allowed rapid plant growth, more biomass accumulated than in earlier periods. Much of this biomass fell into swampy environments where oxygen was scarce, slowing decomposition. As dead plant material piled up and resisted decay, carbon became locked away in sediments. This process removed carbon dioxide from the atmosphere and stored it underground as peat, which over millions of years would transform into coal. The carbon sequestration allowed oxygen levels to continue rising. The high oxygen levels had profound effects on animals, particularly insects and other arthropods. Because insects rely on passive diffusion for breathing, using tracheal tubes rather than lungs,
Is that no one is
increased
uploading
oxygen
Urbex or
allowed them to grow larger than modern atmospheric conditions would permit. Dragonfly, like insects such as Meganeura, with wingspans of over 70 centimeters, soared through the air. Giant millipede like arthropods known as Arthropleura reached lengths of more than 2 meters, roaming forest floors as herbivores or detritivores. Enormous scorpions and spiders inhabited the leaf litter, hunting small prey. These giant arthropods dominated terrestrial ecosystems. Their size gave them advantages in competition and predation. They filled ecological niches left vacant by the absence of large terrestrial vertebrates, which had not yet evolved to dominate land. Though amphibians existed, they were still tied to water for reproduction and lacked the adaptations needed to thrive in dry environments. Thus, insects and arthropods became the rulers of the Carboniferous forests. The oxygen-rich atmosphere also influenced fire. While the forests were humid, periods of drying could trigger widespread wildfires. High oxygen made these fires burn intensely, shaping forest turnover and opening new ecological opportunities. Burned forests created space for new plant growth and cycles of ecological succession, promoting biodiversity. The Carboniferous also saw the rise of advanced amphibians. Amphibians had emerged earlier from lobe-finned fish ancestors, but during this period they diversified into numerous shapes and sizes. Some amphibians resembled modern salamanders or crocodiles, inhabiting swampy waters and preying on insects and small vertebrates. Others developed heavily armored bodies or elongated limbs for navigating dense vegetation. However, despite their diversity, amphibians remained largely dependent on moist environments due to their permeable skin and reproductive needs. One of the most significant evolutionary milestones of the Carboniferous was the emergence of amniotes, the group that would eventually give rise to reptiles, birds, and mammals. Amniotes evolved eggs with protective membranes and shells, allowing embryos to develop on land without drying out. This innovation freed early reptiles from reliance on water for reproduction, giving them access to drier environments that amphibians could not inhabit. Early amniotes were small and lizard-like, feeding on insects and avoiding larger predators, but their evolutionary potential was enormous. Their skin prevented moisture loss more effectively than amphibians. Their limb structure supported efficient terrestrial locomotion. Amniotic eggs allowed them to spread across forests and uplands. Though small and inconspicuous, these reptiles would eventually give rise to some of the most dominant groups in Earth's history, including the dinosaurs. In parallel with these evolutionary developments, Earth's landscapes continued transforming. Roots of giant trees stabilized soils, altering erosion patterns. Waterways filled with plant debris, creating peat-rich swamps. Fungal decomposers evolved enzymes capable of breaking down lignin, the tough substance that strengthened plant cell walls. Before these fungi evolved, plant debris accumulated in enormous quantities, contributing to the formation of coal deposits. The interactions between plants, fungi, arthropods, and amphibians formed intricate food webs. Herbivorous insects fed on leaves, stems, and spores. Fungi decomposed fallen trees and leaf litter. Predators hunted across the canopy, forest floor, and swamp waters. Ecosystems became more complex than at any previous time in Earth's history. Climate also played a major role. During the Carboniferous, Earth experienced periods of glaciation, especially in the southern hemisphere. Fluctuating sea levels created cycles of swamp expansion and contraction. When seas retreated, forests grew across coastal plains. When seas advanced, these forests drowned, creating thick layers of organic-rich mud. These cycles contributed to the extensive coal seams found today in many parts of the world. The rise of forests also affected global temperatures. As plants removed carbon dioxide from the atmosphere, the greenhouse effect weakened, contributing to global cooling. Ice sheets expanded, particularly across the ancient continent of Gondwana. This cooling climate eventually led to the collapse of some Carboniferous ecosystems. Toward the end of the period, environmental instability increased. Shifting climates caused forests to fragment. Drying conditions reduced swamp habitats. Giant arthropods, dependent on high oxygen and humid conditions, began to decline. Amphibians faced increasing competition from reptiles, which were better adapted to drier environments. The end of the Carboniferous marked a transition from swampy, oxygen-rich landscapes to more seasonal and arid climates. But during the height of the Carboniferous, Earth witnessed a unique moment of ecological grandeur. Forests towered over continents. Insects grew to unimaginable sizes. Amphibians spread widely across wetlands. Reptiles took their first steps toward evolutionary dominance. The atmosphere transformed, and vast coal deposits were laid down that would fuel human industry millions of years later. The rise of giant forests and insects reshaped Earth in ways that would influence all future life. It created the oxygen-rich atmosphere that allowed large animals to evolve. It established ecosystems with complex food webs and interactions. It prepared the stage for the next major evolutionary chapter, the rise of reptiles and the emergence of early amniotes that would eventually give rise to the magnificent age of dinosaurs. The world was green, humid, and filled with life of astonishing size and diversity. But as climates shifted and ecosystems changed, new opportunities emerged. And soon, evolution would move forward once again, guiding life toward an era dominated not by amphibians or arthropods, but by reptiles that would rule the land for the next hundreds of millions of years. As the Carboniferous period progressed and lush forests covered the continents, amphibians were among the dominant vertebrates on land. They thrived in the warm, humid swamps, feeding on abundant insects and laying their eggs in water-filled environments. But beneath this flourishing world, a quiet and revolutionary transformation was taking place. A new kind of vertebrate was emerging, one better suited for life away from swamps, one capable of reproducing on dry land, and one destined to reshape the planet's ecosystems. These were the early reptiles, the first amniotes, and their rise marked a turning point in Earth's history. To understand how amphibians gave way to reptiles, it is essential to recognize the limitations amphibians faced. Although amphibians were the first vertebrates to fully explore terrestrial habitats, they were deeply tied to water. Their eggs lacked protective shells, making them vulnerable to desiccation. Their skin was permeable, requiring moisture to prevent drying out. They needed damp environments for respiration, hydration, and reproduction. As long as Earth remained wet and swampy, amphibians prospered. But when environmental conditions shifted, their vulnerabilities became critical. In contrast, early reptiles evolved traits that freed them from these constraints. Their most important adaptation was the amniotic egg, a self-contained life support system equipped with membranes that provided protection, nourishment, and gas exchange. This innovation allowed embryos to develop on land without drying out. The leathery or partially calcified shell prevented water loss, while internal membranes created a controlled aquatic environment for the embryo. For the first time, vertebrates no longer needed water to reproduce. This single evolutionary leap opened vast new territories previously inaccessible to amphibians. The amniotic egg was only one part of the reptile's success. Early reptiles also developed tougher, more keratinized skin that reduced water loss. Unlike amphibians, whose skin absorbed water and oxygen, reptiles relied on lungs and minimized moisture loss through their outer layers. This made them far more resilient in dry conditions. Their limbs became stronger and more efficient for walking on land. Their senses adapted to detecting prey and predators in open terrestrial habitats, and their metabolism allowed them to survive in a wide range of environments. The earliest reptiles appeared during the late Carboniferous, around 315 million years ago. Fossils such as Hylonomus from the coal forests of Nova Scotia provide some of the oldest evidence of true reptiles. Hylonomus was small, lizard-like, and agile. It hunted insects and small arthropods in the leaf litter of dense forests. Its body plan already showed many reptilian traits: elongated limbs, strong vertebrae, and a skull with openings that allowed for more powerful jaw muscles. Early reptiles belonged to several distinct evolutionary branches. Some of the first were anapsids, reptiles with solid skulls lacking temporal openings. These early anapsids included ancestors of turtles and many extinct reptilian lineages. Another major group, the synapsids, evolved a single temporal opening behind each eye. This opening allowed for stronger bite forces and more advanced jaw muscles. Synapsids would eventually give rise to mammals, but in the late Carboniferous and Permian, they were some of the dominant terrestrial predators and herbivores. A third major lineage, the diapsids, evolved two temporal openings on each side of the skull, providing even greater flexibility and strength for jaw movement. Diapsids would eventually give rise to lizards, snakes, crocodiles, birds, and the dinosaurs. Although diapsids were not yet dominant in the late Carboniferous, their evolutionary potential was enormous. The rise of reptiles coincided with changes in climate and environment. During the late Carboniferous, Earth began experiencing increased seasonality, glaciations in the southern hemisphere, and fluctuations in sea levels. Swamp forests fragmented as periods of drying became more common. Amphibians, dependent on stable and humid environments, struggled in this shifting landscape. Many amphibian lineages declined as habitats shrank and became more isolated. Reptiles, however, were not as restricted. Their waterproof skin enabled them to move into upland regions, drier forests, and open plains. Their amniotic eggs allowed them to reproduce away from water sources. Their more robust bodies allowed them to navigate diverse terrains. As ecosystems changed, reptiles expanded into niches amphibians could not occupy. During the Permian period, reptiles diversified dramatically. Synapsids, in particular, became prominent. Early synapsids, like Dimetrodon, often mistaken for a dinosaur, were apex predators long before dinosaurs existed. Dimetrodon possessed a large sail on its back, possibly used for thermoregulation. Its powerful jaws and sharp teeth made it a formidable hunter. Other synapsids evolved herbivorous lifestyles, developing barrel-shaped bodies and grinding teeth for processing plant material. Diapsids also began their ascent during this time. Early diapsids evolved lighter, more flexible skeletons that allowed quick movement and agility. Some adapted to aquatic lifestyles. Others became swift terrestrial hunters. Though small at first, diapsids were laying the groundwork for future dominance. Reptiles were no longer limited to tiny insect hunters. They were evolving into predators, herbivores, climbers, and burrowing specialists. Amphibians continued to exist alongside early reptiles, but their diversity diminished as reptiles took over terrestrial ecosystems. Some amphibians attempted to adapt by growing larger, developing more robust skeletons, or evolving specialized feeding strategies. Giant amphibians like Eriops and Seimuria roamed Permian wetlands and rivers. These creatures were formidable, reaching lengths of several meters. They fed on fish, small reptiles, and invertebrates. Yet, despite their size, they remained constrained by their reliance on water. The fragmentation of carboniferous forests further challenged amphibian populations. As trees declined and landscapes dried, amphibians lost the moist microhabitats they depended on. Reptiles, with their ability to conserve water and thrive in dry climates, expanded into these new territories. Evolution favored reptiles' adaptive traits, and amphibians gradually retreated to environments where moisture remained abundant. Reptiles also possessed metabolic advantages. Although not warm-blooded like mammals or birds, early reptiles had more efficient respiratory systems than amphibians. Their lungs were larger and more complex. Their rib cages facilitated stronger airflow. These traits allowed them to sustain higher activity levels, pursue prey more effectively, and explore open environments where amphibians could not survive. As reptiles spread across the continents, they set the stage for large-scale ecological changes. They became dominant herbivores, reshaping vegetation through constant browsing. They became apex predators, influencing prey populations. They diversified into burrowers, climbers, gliders, and swimmers. Their eggs allowed reproduction independent of rainfall or aquatic habitats, giving them an evolutionary edge that no amphibian could match. The transition from amphibian dominance to reptile dominance reflects one of the major ecological shifts in Earth's history. It was not a sudden replacement, but a prolonged process driven by climate change, habitat fragmentation, and biological innovations. Amphibians had flourished in the warm, swampy, carboniferous world, but the shifting Permian climate favored animals better suited for dryness and fluctuating conditions. By the mid-Permian period, reptiles had firmly established themselves as the ruling vertebrates on land. Their diversity continued to expand, particularly among synapsids and diapsids. Synapsids produced a variety of predators and herbivores, some of which grew to impressive sizes. Diapsids, though still relatively small, evolved traits that would eventually give rise to the archosaurs, the ancestors of crocodiles, pterosaurs, and dinosaurs. Amphibians did not disappear. They continued surviving in moist environments, evolving into new lineages, and maintaining diversity in freshwater ecosystems. But their era as the dominant land vertebrates had ended. The future belonged to reptiles and their evolutionary descendants. The rise of reptiles also played a role in reshaping Earth's climate and geology. As reptiles expanded into new regions, they changed plant-animal interactions. Herbivorous reptiles influenced vegetation growth patterns. Predators influenced prey behavior and distribution. Ecosystems became more structured and dynamic. Terrestrial environments became arenas of competition, predation, and adaptation. As the Permian period advanced, Earth's environments continued to shift. Regions near the equator grew hotter and drier. Deserts expanded. Seasonal climates intensified. Reptiles thrived in these conditions. Amphibians, unable to cope with such dryness, became increasingly restricted. The stage was set for reptiles to diversify further and for evolutionary paths that would eventually lead to the rise of dinosaurs. In this era of transition, amphibians passed the torch of terrestrial dominance to reptiles. The small, lizard-like amniotes of the late Carboniferous evolved into the great reptilian lineages of the Permian, Triassic, and beyond. Their innovations, the amniotic egg, waterproof skin, efficient lungs, and strong skeletons, paved the way for future evolutionary successes. Soon, the world would witness even greater reptilian diversity. Mammal-like reptiles would flourish. Early archosaurs would rise. And after a catastrophic mass extinction at the end of the Permian, the planet would prepare for a dramatic new chapter, the Age of Dinosaurs. As the Permian period unfolded, Earth underwent a geological transformation of colossal scale. Drifting continents, shaped by millions of years of plate tectonics, gradually moved toward one another. By around 299 million years ago, they collided and fused into a single, enormous landmass known as Pangaea. This supercontinent stretched from pole to pole, surrounded by the vast global ocean Panthalassa and bordered on its eastern side by the smaller Tethys Sea. Pangaea was a world unlike anything Earth had seen before, a world that reshaped climates, ecosystems, evolution, and the destiny of life itself. The formation of Pangaea began long before the Permian. Ancient continents such as Laurentia, Gondwana, and Baltica had been moving steadily across the planet. Their collisions during the late Carboniferous and early Permian created massive mountain ranges, including the Ural Mountains, which formed as the continents finally joined. These collisions profoundly altered atmospheric circulation, ocean currents, and rainfall patterns. As the land masses locked together, the supercontinent grew immensely diverse in its landscapes, yet unified in its geological presence. Pangaea's size created extreme climate contrasts. The interior of the supercontinent was vast and far from the moderating influence of oceans. Temperatures in these inland regions were scorching during the day and freezing at night. Intense seasonal variations occurred due to Pangaea's enormous size and the shifting tilt of Earth's axis. Monsoons, droughts, and desertification became common across central Pangaea. Meanwhile, coastal regions experienced more moderate climates and supported lush vegetation. The supercontinent's interior is believed to have hosted immense deserts, including the Karoo and Erg deserts, which rivaled or surpassed the modern Sahara. Sand dunes reached towering heights shaped by relentless winds. Few life forms could survive in these arid zones. The lack of moisture, combined with extreme temperature swings, made the central regions of Pangaea some of the harshest environments ever known. In contrast, the coastal fringes of Pangaea supported rich and diverse ecosystems. River systems flowed from the interior toward the edges, carving valleys and nourishing plant life. Swampy regions reminiscent of Carboniferous landscapes persisted, though they gradually declined as climate shifted. Forests composed of seed ferns, conifers, and cordytes grew near coasts and riverbanks. These plants were better adapted to drier conditions than the giant lycophytes and horsetails of earlier periods. Pangaea's formation played a crucial role in the evolution of terrestrial life. As climates became drier and more seasonal, amphibians struggled to survive outside of moist environments. Reptiles, with their amniotic eggs and water-conserving skin, thrived in the new conditions. Early synapsids and diapsids diversified across the continent. Some adapted to desert regions, while others populated forests and floodplains. The challenges posed by Pangaea's climate accelerated evolutionary change, shaping organisms into more resilient and specialized forms. Among the dominant terrestrial animals of this era were the synapsids, often called mammal-like reptiles, though they were not true mammals. These creatures included Dimetrodon, Edaphosaurus, and later therapsids. Dimetrodon, with its iconic sailback, roamed Pangaea as an apex predator. Its sail may have helped regulate body temperature in Pangaea's extreme climate. Herbivores, like Edaphosaurus, fed on tough vegetation using specialized teeth. The later therapsids evolved more advanced jaws, differentiated teeth, and limb postures increasingly resembling those of mammals. Therapsids became particularly successful during the Middle to Late Permian. They diversified into carnivores, herbivores, and omnivores. Some evolved insulating body coverings, possibly early forms of hair. These adaptations represented evolutionary steps toward the mammals that would appear long after the Permian ended. In the dynamic environments of Pangaea, therapsids became the dominant land vertebrates, inhabiting ecosystems from the coasts to the interior plains. Diapsids also continued evolving, giving rise to early reptiles that would later dominate the Mesozoic. While diapsids were not yet as diverse or as dominant as synapsids during the Permian, they occupied important ecological roles. Some became agile predators, others adapted to arboreal lifestyles, and still others explored semi-aquatic niches. Their evolutionary trajectory would set the stage for the rise of archosaurs and ultimately the dinosaurs. Plants on Pangaea adapted to increasingly dry conditions. Conifers, with their tough needles and water-efficient structures, spread across uplands and dry plains. Seed ferns remained common in wetter areas. Glossopteris, a widespread seed fern, dominated much of Gondwana, revealing patterns of climate and continental arrangement through its fossil distribution. Its presence across southern regions provided early evidence for the theory of continental drift. The oceans surrounding Pangaea were equally remarkable. Panthalassa, the vast global ocean, covered most of Earth's surface and influenced global climate through deep currents and powerful storms. The Tethys Sea, located between the northern and southern portions of Pangaea, became a hotspot of marine diversity. Reefs, fish, ammonites, and early marine reptiles flourished in these warm, nutrient-rich waters. Trilobites, however, were declining, having suffered losses in earlier extinctions. The movement of Pangaea also influenced volcanic activity. Tectonic collisions created mountain ranges, while rifting zones and volcanic arcs formed along coastal regions. Volcanic eruptions released gases that affected climate patterns. Some eruptions contributed to short-term cooling through aerosols in the atmosphere. Others released carbon dioxide, contributing to long-term warming. The supercontinent also influenced Earth's rotation and the distribution of sunlight. Because Pangaea extended from pole to pole, it disrupted heat distribution and intensified seasonal differences. Monsoon cycles became stronger. Rainfall patterns shifted dramatically. Some regions experienced extreme wet seasons, followed by prolonged droughts. Life had to adapt, to these unpredictable conditions. Despite these challenges, ecosystems flourished. Freshwater habitats supported amphibians, fish, and early aquatic reptiles. Terrestrial ecosystems housed diverse synapsids, diapsids, and invertebrates. Extensive forests supported food webs filled with insects, small reptiles, and large herbivores. Predatory therapsids patrolled woodlands, hunting creatures hidden among ferns and conifers. But the stability of Pangaea was fragile. The very forces that created the supercontinent also set the stage for dramatic environmental changes. Reduced coastal areas, limited marine habitats. Large-scale atmospheric circulation patterns created extreme climates. Volcanic activity and changes in ocean chemistry contributed to ecological stress. Environmental instability increased toward the late Permian, leading to declines in biodiversity. Ultimately, Pangaea became the stage for the greatest mass extinction in Earth's history, the Permian Triassic extinction event. Occurring around 252 million years ago, this catastrophe wiped out roughly 90% of marine species and 70% of terrestrial vertebrate species. Massive volcanic eruptions in the Siberian traps released enormous amounts of greenhouse gases, leading to global warming, ocean acidification, and widespread anoxia. Pangaea's vast interior exacerbated the impacts, creating inhospitable environments across the continent. Yet, before this devastating event, Pangaea had played its evolutionary role. It forced life to adapt to new climates. It shaped the evolution of reptiles, including the ancestors of dinosaurs and mammals. It concentrated habitats and drove competition. It created deserts, forests, mountains, and coastlines that challenged organisms to innovate and evolve. The supercontinent was both a crucible of life and a harbinger of mass extinction. After the collapse of the Permian ecosystems, Pangaea did not disappear immediately. It would remain intact well into the Mesozoic era, eventually breaking apart and giving rise to the continents we know today. But during the Permian, Pangaea stood as a monumental expression of geological forces, a single landmass filled with dynamic ecosystems, a world of challenges and opportunities. The story of Pangaea is the story of Earth's shifting face, of climates pushed to extremes, of biological innovation under pressure. It was a world where early reptiles and mammal-like synapsids rose to dominance, where vegetation adapted to dryness, and where atmospheric and geological changes set the stage for both flourishing and devastation. And as the Permian drew to a close, the world braced for an event that would reset life on Earth, clearing the way for a new era, the rise of the dinosaurs and the beginning of the Mesozoic. The world of the late Permian was a place of extremes. The supercontinent Pangaea stretched across the globe, reshaping climates, ocean currents, and ecosystems. Life had diversified into a wide range of forms, from giant forests to advanced synapsids, from early reptiles to complex marine communities. But beneath this thriving surface, Earth was approaching a catastrophic turning point. Around 252 million years ago, the planet experienced the most devastating mass extinction in its history, the Permian mass extinction. Often called the Great Dying, it marked the end of the Paleozoic era and reshaped life on Earth forever. The scale of the Permian mass extinction was unprecedented. An estimated 90 to 96% of marine species vanished. Roughly 70% of terrestrial vertebrate species disappeared. Countless invertebrates, insects, plants, and microorganisms went extinct. Entire ecosystems collapsed. Reefs that had thrived for millions of years disintegrated. Forests died back. Food webs were disrupted at every level. Life on Earth came closer to complete annihilation than at any other known time. The cause of this extinction was not a single event, but a cascade of environmental catastrophes, many of which were triggered by massive volcanic eruptions in what is now Siberia. These eruptions, known as the Siberian traps, lasted for hundreds of thousands of years. They released tremendous volumes of lava, covering millions of square kilometers. But the lava itself was only part of the problem. The eruptions also unleashed colossal amounts of greenhouse gases, particularly carbon dioxide and methane, into the atmosphere. The rapid increase in greenhouse gases triggered severe global warming. Temperatures rose sharply, leading to heat stress across many ecosystems. In some regions, temperatures may have exceeded the tolerance limits of both marine and terrestrial life. The combination of direct volcanic emissions, warming oceans, disrupted circulation, and atmospheric instability initiated a chain reaction of environmental changes that life could not withstand. One of the earliest consequences of the warming atmosphere was ocean acidification. As carbon dioxide dissolved into seawater, it formed carbonic acid, lowering the ocean's pH. Many marine organisms, particularly those with calcium carbonate shells or skeletons, struggle to survive in these increasingly acidic waters. Corals, brachiopods, and other calcifying species declined. Reefs that had been stable for millions of years dissolved or collapsed. As warming continued, ocean temperatures rose significantly. Warm water holds less oxygen, and as temperatures climbed, oxygen levels in the oceans decreased. This oxygen loss triggered widespread anoxia regions of water completely devoid of oxygen. In these dead zones, marine animals suffocated. Entire ecosystems collapsed as fish, mollusks, and arthropods perished. Only specialized anaerobic microbes could survive in these conditions. The anoxic waters also promoted the growth of certain bacteria that produced hydrogen sulfide, a toxic gas. As these bacteria flourished, hydrogen sulfide levels increased in the oceans and possibly in the atmosphere. This toxic gas could have caused mass die-offs of marine and terrestrial organisms alike, damaging respiratory systems and disrupting biological processes. Volcanism also released large amounts of sulfur dioxide, which initially caused short-term cooling by reflecting sunlight. But as carbon dioxide accumulated, long-term warming overwhelmed these temporary cooling phases. The climate became unstable, swinging between extremes. Droughts, heat waves, and unpredictable weather patterns became common. Many plants died due to the intense climate fluctuations, leading to reduced oxygen production and increased atmospheric carbon dioxide. Drought and desertification spread across Pangaea's interior. Once lush forests withered under the relentless heat. As vegetation declined, soils eroded, rivers changed course, and ecosystems collapsed. Herbivores starved. Predators lost their prey. Complex food webs unraveled rapidly. On land, synapsids suffered catastrophic losses. Once dominant species like Dimetrodon had already disappeared earlier in the Permian. But many surviving therapsids, the advanced synapsids more closely related to mammals, were wiped out during the extinction event. Only a few lineages survived, including small burrowing species that could escape surface heat and drought by living underground. These survivors would eventually give rise to mammals millions of years later. Insect populations also experienced severe declines. The Permian mass extinction stands as one of the rare times when insects suffered global extinction events. Many species that depended on forests or specific plant groups vanished as vegetation patterns changed dramatically. Earth's oceans faced equal devastation. Marine life had already been stressed by warming and acidification, but anoxia intensified the collapse. Deep waters turned into toxic environments filled with hydrogen sulfide-producing bacteria. Coral reefs completely died off. Trilobites, which had existed for over 270 million years, went extinct entirely. Ammonoids, brachiopods, some fish groups, and countless invertebrates suffered dramatic losses. As conditions worsened, methane clathrates frozen. Methane deposits beneath the seafloor may have destabilized due to warming oceans. This released large quantities of methane, another potent greenhouse gas, further accelerating global warming. This runaway feedback loop pushed temperatures even higher, possibly by several degrees, creating one of the hottest periods in Earth's history. The devastation was not limited to oceans and coasts. Volcanic activity from the Siberian traps may have ignited coal seams, releasing additional carbon dioxide and toxic gases. Ash clouds darkened skies. Acid rain fell across continents, harming plant life and altering water chemistry. Ecosystems that depended on stable climatic cycles were overwhelmed by the rapid changes. Yet the Permian mass extinction was not instantaneous. It unfolded over tens of thousands to hundreds of thousands of years, a blink in geological time, but long enough for multiple waves of extinction. Some species declined gradually, while others were suddenly wiped out during peak environmental stress. The patchwork of extinction patterns reflects the complexity of the crisis. After the initial collapse, recovery was slow. The world that emerged after the extinction was drastically different from the one that existed before. Forests had vanished in many regions. Ecosystems were simplified. Biodiversity was low. Many ecological roles remained empty for millions of years. The survivors were often small, generalist species, capable of withstanding harsh conditions. In the oceans, microbial communities dominated for a time as they adapted quickly to high temperatures and low oxygen. Sponges and bivalves slowly re-established themselves, but reefs remained absent for millions of years. Terrestrial ecosystems saw the rise of hardy synapsids and early archosaurs, which would eventually give rise to the dinosaurs. Recovery took at least 5 million years to show significant progress, and up to 15 million years to fully restore ecological complexity. Scientists studying the Permian mass extinction have uncovered evidence from volcanic rocks, fossil records, isotope analyses, and sediment cores. These clues reveal a picture of cascading environmental collapse triggered by volcanism, intensified by greenhouse gases, and amplified by feedback loops involving oceans, climate, and biological processes. It was a moment when Earth's interconnected systems spiraled into catastrophe. The Permian extinction reshaped the evolutionary landscape. By eliminating dominant groups, it opened ecological space for new lineages to rise. Early archosaurs, which were small and relatively obscure before the extinction, diversified rapidly in the New World. Their descendants, crocodiles, pterosaurs, and dinosaurs, would dominate terrestrial and aerial ecosystems during the Mesozoic era. Similarly, the ancestors of mammals survived only as small, inconspicuous species, but carried forward the traits needed for future success. The Permian mass extinction also serves as a stark reminder of Earth's fragility and resilience. Life nearly disappeared, yet the survivors found ways to adapt, evolve, and eventually flourish. Ecosystems rebuilt themselves through slow processes of colonization, diversification, and ecological specialization. The world that emerged from the ashes was a blank canvas, ready for new forms of life. And in the next chapter of Earth's history, evolution would paint that canvas with some of the most iconic creatures ever to walk the planet, the dinosaurs. the Permian mass extinction reset life on Earth. When its devastation finally eased, the world that emerged was almost unrecognizable. Ecosystems were stripped bare, biodiversity had collapsed, and only a fraction of species survived. Yet, in this emptiness lay opportunity. Evolution began again from the surviving branches, and in the rejuvenated Triassic landscapes, a new caste of reptiles rose to dominate the Earth. Among them were the earliest dinosaurs, still small and overshadowed at first, but destined to become icons of the Mesozoic era. After the extinction, Earth entered the Triassic period, beginning around 252 million years ago. The climate was hot and dry across much of the supercontinent Pangaea. Deserts stretched for thousands of kilometers. Monsoons battered coastal regions. The recovery of life was slow, but as millions of years passed, plants, insects, and vertebrates gradually filled vacant niches. Conifer forests spread, ferns and cycads flourished, and early coral reefs began rebuilding. Ecosystems stabilized, and new evolutionary experiments emerged. The dominant terrestrial animals of the early Triassic were not dinosaurs, but the survivors of the synapsid lineage. Therapsids, often called mammal-like reptiles, had weathered the extinction better than most groups. Species such as Lystrosaurus became extraordinarily abundant. Lystrosaurus, a stocky herbivore with tusks and a beak-like mouth, spread across Pangaea and may have accounted for over half of all terrestrial vertebrates. Its remarkable success was due to its generalist diet, burrowing lifestyle, and ability to withstand harsh environmental conditions. Other therapsids, including cynodonts, also persisted. Cynodonts were small, agile creatures with differentiated teeth and advanced jaw structures. They possessed traits such as whisker-like sensory hairs and possibly warm-blooded metabolism, bringing them closer to true mammals. They hunted insects, scavenged, and exploited ecological niches unavailable to larger reptiles. Though they were overshadowed by reptiles later in the Triassic, cynodonts would give rise to mammals long after the age of dinosaurs ended. While synapsids dominated early recovery, reptiles soon diversified into powerful new lineages. Among the most important were the archosaurs, the group that would eventually produce crocodiles, pterosaurs, dinosaurs, and birds. Early archosaurs evolved erect postures, strong limbs, and efficient respiratory systems that could support high activity levels. These adaptations allowed them to thrive in the hot Triassic climate, where oxygen levels were lower and endurance was essential for survival. Archosaurs split into two major branches: the pseudosuchians, which would lead to crocodiles, and the avemetatarsalia, which would lead to dinosaurs and pterosaurs. During the early and mid-Triassic, pseudosuchians dominated terrestrial ecosystems. They evolved into a variety of forms, some heavily armored, some slender and fast, and some apex predators. Among these pseudosuchians was Postosuchus, a powerful predator with long legs, sharp teeth, and a skull built for crushing prey. Postosuchus and its relatives patrolled Triassic floodplains, hunting early reptiles, amphibians, and small synapsids. Other pseudosuchians, such as atosaurs, became armored herbivores with body plates and crocodile-like appearances. Their diversity demonstrated the evolutionary potential of archosaurs long before dinosaurs rose to prominence. The earliest dinosaurs appeared around 233 million years ago, during the late Triassic, but they were not yet the giants that would rule the Jurassic and Cretaceous. They were small, lightly built animals, often overshadowed by larger archosaurs. Early dinosaurs included forms such as Heterosaurus, Eoraptor and Staurikosaurus, slender bipedal predators or omnivores that hunted insects and small vertebrates. Their lightweight skeletons, long tails, and hollow bones made them agile runners. Dinosaurs were distinguished by their unique hip structure, enabling an upright gait with legs positioned directly under the body. This posture increased speed, endurance, and efficiency, giving dinosaurs an edge over sprawling reptiles. Their respiratory system, possibly involving air sacs similar to those in modern birds, allowed for high metabolic output and sustained activity. These anatomical advantages laid the foundation for their future dominance. Herbivorous dinosaurs also appeared during the Triassic. Early forms such as Plateosaurus, a large, long-necked prosauropod, grazed on ferns and cycads. Plateosaurus could walk on 2 or 4 legs and used its long neck to reach vegetation. Though not yet a true giant, it represented the first wave of large herbivorous dinosaurs that would later evolve into the colossal sauropods. Alongside dinosaurs, pterosaurs, the first vertebrates to achieve powered flight, took to the skies. Their wings were formed from membranes stretched along elongated fourth fingers. Early pterosaurs such as Eudimorphodon soared over coastlines and lakes, hunting fish and insects. Their hollow bones, lightweight frames, and specialized musculature allowed them to dominate aerial ecosystems long before birds appeared. Marine reptiles also diversified during the Triassic. Ichthyosaurs, resembling dolphin-like predators, evolved streamlined bodies and powerful tails that made them swift swimmers. Nothosaurs and placodonts patrolled shallow seas, with some specialized for crushing shellfish and others for capturing fish. These marine reptiles filled ecological roles left vacant after the Permian extinction, helping rebuild ocean ecosystems. As the Triassic progressed, dinosaurs began to expand. The climate became more favorable, vegetation increased, and crocodilian relatives began to decline in many habitats. Competition among reptiles drove adaptation and specialization. Dinosaurs gradually diversified into multiple groups, including theropods, sauropodomorphs, and ornithischians. Their ability to walk upright, breathe efficiently, and regulate body temperature gave them advantages in diverse environments. Toward the end of the Triassic, another major extinction event struck. Volcanic eruptions associated with the breakup of Pangaea released massive amounts of carbon dioxide, triggering global warming and ocean acidification. This extinction eliminated many of the dominant pseudosuchians, opening ecological space for dinosaurs. Unlike the Permian extinction, the late Triassic extinction was smaller in scale, but its impact on evolution was profound. With their competitors diminished, dinosaurs surged into dominance. Once the early reptiles and archosaurs that had overshadowed them declined, dinosaurs expanded rapidly across Pangaea. They diversified into predators, herbivores, scavengers, and omnivores. Their body sizes grew. Their ecological roles multiplied. By the beginning of the Jurassic period, dinosaurs were firmly established as the dominant terrestrial vertebrates on Earth. The age of early dinosaurs and reptiles was a time of experimentation and transition. Life was recovering from near annihilation. Ecosystems were rebuilding. Reptiles adapted to new climates and seized new opportunities. Archosaurs diversified into powerful forms that would shape the Mesozoic. Synapsids persisted but shifted into smaller, nocturnal niches. Marine reptiles took to the oceans. Pterosaurs claimed the skies. What began in the aftermath of catastrophe ended in the rise of one of the most successful groups of animals in Earth's history. Dinosaurs, still small and relatively obscure during much of the Triassic, emerged from this period poised for evolutionary triumph. Soon, they would grow into giants, dominate every continent, and rule the planet for more than 150 million years. When the Triassic period came to a close with yet another extinction event, many dominant reptile groups vanished, clearing ecological space across the supercontinent Pangaea. Into this newly opened world stepped the dinosaurs, who, over millions of years, grew larger, more diverse, and more successful than any land animals before them. The Jurassic period, beginning around 201 million years ago, marked the true flourishing of dinosaurs. It was a time of warm climates, lush vegetation, rising sea levels, and vast forests. Ecosystems stabilized and diversified, creating an environment where gigantic herbivores could thrive and shape the world around them. During the early Jurassic, the breakup of Pangaea had begun. Rifts opened across the supercontinent, forming new coastlines and shallow seas. Climates became more humid and stable as ocean circulation patterns changed, monsoon systems diminished, and deserts that characterized the Triassic interior began shrinking. This climatic shift supported an explosion of vegetation, ferns, conifers, cycads, and ginkgos-filled landscapes from coastlines to uplands. With abundant food and stable environments, dinosaurs expanded dramatically in size and diversity. The most iconic creatures of the Jurassic were the giant herbivorous sauropods. These massive animals evolved from earlier prosauropods of the Triassic, adapting to a world of towering trees and expansive forests. Sauropods developed long necks that allowed them to reach high vegetation, enabling them to feed on conifer branches and leafy canopies. Their powerful legs supported enormous bodies, some weighing more than 50 tons. Their long tails provided balance and defense. Among the earliest and most famous sauropods was Diplodocus, with its whip-like tail and long, slender neck. Apatosaurus, formerly known as Brontosaurus, possessed a more robust body and thick, muscular limbs. Brachiosaurus towered above other dinosaurs, with its front legs longer than its hind legs, giving its body a distinctive upward slope. This posture allowed Brachiosaurus to browse vegetation at heights no other herbivore could reach. The selective pressure on plants caused by these massive herbivores shaped Jurassic ecosystems. Trees developed tougher foliage, thicker bark, and higher growth patterns to avoid being eaten. Forests adapted to the constant browsing of herds that roamed in vast numbers. In turn, sauropods developed specialized teeth and digestive systems capable of extracting nutrients from fibrous plant material. Some species swallowed stones, gastroliths, to grind food in their massive stomachs. Sauropods lived in social groups, migrating across large territories in search of fresh vegetation. Their movements influenced entire ecosystems. As they fed, they cleared forests, opened grassland like clearings, and stimulated new plant growth. Their footsteps carved pathways through woodlands. Their massive dung-enriched soils and sustained insect populations. In many ways, sauropods acted as ecological engineers, shaping the environment through their feeding and movement behaviors. While sauropods dominated the herbivorous niche, other dinosaur groups flourished as well. Stegosaurs evolved armor plates, spikes, and tail weapons for defense. Stegosaurs, such as Stegosaurus, roamed floodplains, feeding on low vegetation like ferns and cycads. Their iconic backplates may have played roles in thermoregulation or display. The sharp spikes on their tails the thagomisers served as powerful weapons against predators. Ornithopods, the ancestors of later duck-billed dinosaurs, were smaller but highly adaptable herbivores. Early ornithopods, such as Camptosaurus, moved on 2 or 4 legs and fed on a variety of plants. Their agility and keen senses allowed them to evade predators, while their flexible jaws and grinding teeth let them exploit diverse vegetation. Jurassic ecosystems also supported diverse predators. Apex predators of this era included the allosaurids, large theropods with sharp teeth, powerful jaws, and curved claws. Allosaurus, one of the most well-known predators of the Jurassic, hunted sauropods, stegosaurs, and ornithopods. It possessed strong hind limbs for running and a flexible neck that allowed it to deliver deep, slicing bites. Though not as large as later theropods like Tyrannosaurus, Allosaurus was agile and highly effective. Predators needed varied strategies to hunt enormous herbivores. Some may have hunted in groups, coordinating attacks on weakened or young sauropods. Others relied on ambush, using forest cover to strike with speed. Even small theropods played important roles as scavengers or swift hunters of smaller prey. The diversity of predatory strategies mirrored the complexity of Jurassic ecosystems. Pterosaurs also expanded during the Jurassic. These flying reptiles diversified into many forms, from small insect eaters to large fish-hunting species. Their wings, supported by elongated fourth fingers, enabled efficient gliding and soaring. Pterosaurs occupied coastal cliffs, lakesides, and river valleys. They hunted insects, fish, and small vertebrates. Some species developed elaborate crests, possibly used for display or mating rituals. Jurassic seas were equally rich and diverse. Marine reptiles flourished as they adapted to new marine environments created by the breakup of Pangaea. Ichthyosaurs reached peak diversity, resembling dolphins in speed and agility. Plesiosaurs evolved long necks and small heads for catching fish, while pliosaurs developed massive jaws and muscular bodies for hunting larger prey. Ammonites, spiral-shelled cephalopods, thrived in the oceans and became important index fossils for identifying Jurassic rock layers. Coral reefs continued to expand, supporting vibrant ecosystems of fish, crustaceans, mollusks, and marine reptiles. Marine food webs were complex, with predators occupying multiple trophic levels. The stability of the Jurassic climate contributed to the growth and diversification of ocean life. As vegetation spread and dinosaurs diversified, insects evolved alongside them. Jurassic forests supported beetles, dragonflies, termites, and early butterflies. Insect pollination began to develop more extensively, especially among cycads and ginkgos. Dragonflies, though smaller than their giant Carboniferous ancestors, remained skilled aerial predators. The interaction between plants and insects shaped the evolution of both groups, establishing ecological relationships that persist today. The breakup of Pangaea continued throughout the Jurassic, creating new continents, islands, and coastlines. As continents drifted apart, new species evolved in isolation. This geographic separation contributed to biodiversity as populations adapted to different climates and environments. The shifting continents also influenced ocean circulation, rainfall patterns, and climate distribution. The Jurassic climate was generally warm and moist, with fewer temperature extremes than the Triassic. Stable rainfall patterns supported dense vegetation. River systems flowed through forests, creating habitats for amphibians, reptiles, and early mammals. Small mammals, descendants of cynodonts, were nocturnal insect eaters that avoided dinosaur dominance by thriving in niches where dinosaurs were less active. Though small and inconspicuous, these early mammals carried the traits that would later shape mammalian evolution. The abundance of vegetation fueled the growth of the largest land animals ever to exist. Sauropods reached unprecedented sizes during the late Jurassic. Species like Argentinosaurus and Supersaurus approached or exceeded lengths of 30 meters. Their size offered protection against predators, allowed efficient energy use, and enabled them to access vegetation other animals could not reach. The sheer scale of sauropods remains one of the most extraordinary outcomes of evolution. The interaction between giant herbivores and predators drove evolutionary adaptations. Predators developed stronger jaws, sharper teeth, and more powerful limbs. Herbivores developed armor, size, and defensive strategies. Plants evolved spines, toxins, and rapid growth. These evolutionary arms races contributed to the complexity and dynamism of Jurassic ecosystems. Forest fires occasionally swept through Jurassic landscapes, clearing dense vegetation and creating opportunities for new growth. Volcanic eruptions, though less catastrophic than the Siberian traps, also influenced climates and ecosystems. These disturbances fostered ecological turnover, helping maintain biodiversity by opening niches for new species. As the Jurassic period progressed, dinosaurs continued to expand across the globe. Sauropods dominated floodplains and forests. Stegosaurs thrived in lowland regions. Allosaurs ruled as apex predators. Pterosaurs filled the skies, and marine reptiles conquered the seas. The world had become a dinosaur-dominated planet, shaped by the interplay of climate, vegetation, and evolutionary innovation. The Jurassic ended not with a catastrophic extinction, but with gradual ecological change. New dinosaur groups began emerging, continents continued to drift, climates shifted slowly. And the next chapter, the Cretaceous period, would see the rise of even more extraordinary creatures, including the apex predators and towering herbivores that would define the final age of dinosaurs. The Cretaceous period, beginning around 145 million years ago, marked a turning point in the Mesozoic era. It was a world of extraordinary diversity, shifting continents, rising seas, and the evolution of some of the most iconic creatures in Earth's history. Dinosaurs reached new heights of size, specialization, and ecological dominance. Flowering plants transformed landscapes. And apex predators, including some of the most fearsome theropods ever to live, ruled the land with unmatched power. The Cretaceous world was dynamic, vibrant, and full of evolutionary innovation. During the early Cretaceous, the breakup of Pangaea continued. Continents drifted apart, creating isolated landmasses that fostered new species through evolutionary divergence. Shallow seas flooded continental interiors, forming vast seaways such as the Western Interior Seaway in North America. Warm, humid climates dominated much of the globe, though seasonal variations increased as continents moved closer to their modern positions. One of the most profound developments of the Cretaceous was the rise of flowering plants, or angiosperms. Appearing during the early Cretaceous, these plants rapidly diversified. Unlike earlier plant groups such as conifers and cycads, angiosperms used flowers to attract pollinators and enclose seeds within fruits. Their ability to reproduce efficiently and adapt to diverse environments allowed them to spread quickly. Flowering plants transformed ecosystems by creating new food sources for insects, herbivores, and eventually birds and mammals. Insects co-evolved alongside angiosperms. Bees, butterflies, ants, and beetles diversified dramatically. Pollination became a major ecological force, influencing plant evolution and interactions. Insects fed on nectar, pollen, and leaves, forming complex food webs that supported a growing variety of animals. As vegetation changed, herbivorous dinosaurs evolved new feeding strategies. Hadrosaurs, duck-billed dinosaurs, developed intricate dental batteries capable of grinding tough plant material. They lived in herds and occupied diverse habitats from coastlines to forested uplands. Ceratopsians, such as Triceratops, evolved elaborate frills and horns for defense, display, and combat. Their beak-like mouths allowed them to shear through vegetation with efficiency. Ankylosaurs developed body armor of fused bone plates and wielded massive tail clubs for protection. Pachycephalosaurs evolved thick, dome-shaped skulls, possibly used in headbutting contests. Sauropods, though declining in some regions, continued to thrive in others. Titanosaurs, the last great sauropods, reached colossal sizes in the southern continents, including species like Argentinian and Patagoteton, some of the largest land animals to ever exist. But the Cretaceous is remembered most vividly for its apex predators. Among them, Tyrannosaurus stands as one of the most famous. Tyrannosaurus rex, appearing in the late Cretaceous, was a massive theropod, measuring up to 12 meters long and weighing over 8 tons. With powerful jaws capable of delivering bone-crushing bites, stereo vision, and a highly developed sense of smell, T-Rex was one of the most formidable predators in Earth's history. Its robust skull, muscular tail, and strong hind limbs made it both powerful and agile. Although it lived only in North America during the final stage of the Cretaceous, its presence left an indelible mark on paleontology and popular culture. Elsewhere in the world, other theropods held the role of apex predator. Spinosaurus, one of the longest carnivorous dinosaurs known, dominated the river systems of North Africa. With its elongated skull, conical teeth, and crocodile-like anatomy, Spinosaurus was adapted for a semi-aquatic lifestyle. It hunted fish and possibly scavenged large carcasses. Its distinctive sail, formed by long neural spines along its back, may have been used for display or thermoregulation. Giganotosaurus and Carcharodontosaurus were among the largest land predators of the southern continents. These massive theropods rivaled or even exceeded T-Rex in length. They possessed blade-like teeth ideal for slicing flesh, contrasting with the crushing bite strategy of tyrannosaurids. Their size and hunting strategies reflected the prey available in their ecosystems, including large sauropods. Velociraptor, smaller but highly intelligent and agile, hunted in packs and used its sickle-shaped claws to pin down prey. Though much smaller than popular portrayals, closer in size to a turkey velociraptor was a highly efficient predator. Its feathers, keen senses, and lightweight body demonstrated the close evolutionary ties between theropods and birds. Indeed, birds evolved from small, feathered theropods during the Jurassic and continued diversifying throughout the Cretaceous. Early birds such as Archaeopteryx and later forms like Ichthyornis developed powered flight, advanced feathers, and specialized beaks. Birds coexisted with pterosaurs, though the latter remained dominant aerial predators for much of the Cretaceous. Some pterosaurs, such as Quetzalcoatlus, reached wingspans exceeding 10 meters, making them the largest flying animals ever to exist. Cretaceous oceans teemed with life. Plesiosaurs, mosasaurs, and giant sharks patrolled the depths. Mosasaurs, powerful marine lizards related to modern monitor lizards, became dominant marine predators in the later Cretaceous. Their long bodies, paddle-like limbs, and double-hinged jaws allowed them to pursue fish, turtles, and even smaller marine reptiles. Plesiosaurs, with their long necks and small heads, hunted schools of fish and squid-like creatures. Ichthyosaurs, though declining, still inhabited some seas early in the period. Ammonites and belemnites thrived in marine environments, serving as key food sources for predators. Coral reefs expanded across tropical regions. Plankton populations grew, contributing to complex marine food webs that supported diverse fish and reptile species. As the Cretaceous progressed, global climate shifted. The Earth remained generally warm, but differences in temperature increased between equatorial and polar regions. Flowering plants spread into new habitats, altering landscapes and supporting diverse herbivores. Forests became more open in some areas, while dense jungles formed in others. Continental drift continued to shape evolution. As land masses separated, species evolved in isolation. This led to remarkable regional diversity. For example, South America became home to unique titanosaurs and giant predators like Giganotosaurus. Asia produced feathered theropods and early bird species. North America saw the rise of tyrannosaurids, ceratopsians, and hadrosaurs. During the late Cretaceous, ecosystems reached extraordinary complexity. In North America's western interior, herds of triceratops, ankylosaurs, hadrosaurs, and pachycephalosaurs roamed floodplains and coastal forests. Apex predators such as T-Rex controlled hunting territories. Small mammals hunted insects at night. Birds filled niches ranging from fish hunters to forest dwellers. Insects pollinated flowering plants, maintaining interconnected food webs. Predator-prey dynamics shaped dinosaur evolution. Herbivores developed defensive adaptations such as horns, spikes, armor, and speed. Predators evolved stronger jaws, sharper claws, keen senses, and advanced hunting strategies. These evolutionary arms races enriched biodiversity and maintained ecological balance. In the oceans, mosasaurs reached peak dominance. Their streamlined bodies and powerful tails made them formidable hunters. Some species grew longer than 15 meters. Plesiosaurs adapted to specialized niches, with some evolving massive skulls and others maintaining slender necks. Sharks, such as Cretoxorhina, preyed on fish and marine reptiles. Fish diversity expanded dramatically, including early forms of modern teleost fish. Despite its flourishing life, the Cretaceous period was approaching its end. Geological and climatic changes hinted at instability. Volcanic activity increased in certain regions. Ecosystems became more specialized and therefore more vulnerable to disruption. Although life was thriving, it was highly interconnected and fragile. The end would come suddenly, not through gradual decline, but through an event of catastrophic proportions. A massive asteroid impact near the Yucatan Peninsula, combined with decades of volcanic eruptions and climatic chaos, would end the reign of the dinosaurs and reshape the planet once again. But before the impact, the Cretaceous world stood at its peak, a planet vibrant with forests, oceans teeming with predators, skies filled with flying reptiles and birds, and continents dominated by magnificent dinosaurs. Apex predators ruled with unmatched power. Herbivores grew to extraordinary sizes. Flowering plants painted the landscapes with new colors. It was a world of giants, hunters, innovators, and survivors. The Cretaceous world, rich and dynamic, represented the final and most spectacular chapter in the age of dinosaurs, a golden era soon to be shattered by an event that would change life on Earth forever. 66 million years ago, Earth was a thriving world dominated by dinosaurs. Forests of flowering plants stretched across continents. Oceans teemed with mosasaurs, plesiosaurs, and giant sharks. Pterosaurs soared through the skies alongside increasingly diverse birds. Ecosystems were stable, productive, and richly interconnected. Yet everything was about to change in an instant. An event of unimaginable force struck the planet, triggering one of the most catastrophic mass extinctions in Earth's history. It ended the reign of the dinosaurs and reshaped the course of evolution. The story began in the skies above Earth, where a massive asteroid, roughly 10 to 12 kilometers in diameter, traveled through space at more than 60,000 kilometers per hour. Its origins were likely in the outer asteroid belt, where gravitational disturbances, possibly from Jupiter, launched it on a collision course with Earth. For millions of years, it drifted silently, undetected by the world it would soon destroy. On the day of impact, the asteroid pierced Earth's atmosphere with a blinding flash of light. Friction heated the air, creating temperatures hotter than the sun's surface. Within seconds, the asteroid slammed into what is now the Yucatan Peninsula in Mexico, forming the Chicxulub crater. The energy released was equivalent to more than 1 billion nuclear bombs. The impact vaporized rock, water, and the asteroid itself, carving a crater nearly 180 kilometers wide and over 20 kilometers deep. The immediate consequences were devastating. Shockwaves radiated outward at supersonic speeds, flattening forests and killing any animals within thousands of kilometers. Molten rock rained from the sky. Superheated air ignited global wildfires, burning entire continents. Tsunamis, hundreds of meters high, crashed into coastlines across the Americas and beyond. But the most destructive effects were yet to unfold. As the asteroid struck, it sent trillions of tons of vaporized rock, sulfur, and dust into the atmosphere. Tiny particles of molten material, called spherules, spread across the planet. These spherules heated the air as they fell, causing temperatures on the surface to spike. Animals caught in open areas may have been instantly incinerated. Global wildfires burned intensely, filling the air with soot. The massive plume of debris launched into the atmosphere formed a dense cloud that wrapped around Earth. Sunlight was blocked by dust, ash, and sulfur aerosols. Darkness fell across the planet, lasting weeks, months, or even years. Photosynthesis, the foundation of nearly all food webs, collapsed. Plants withered. Phytoplankton in the oceans died. Without sunlight, temperatures plummeted, triggering an impact winter. As plants died off, herbivores starved. As herbivores perished, predators lost their primary food sources. The collapse of ecosystems was swift and total. The mass extinction affected life at every level. In the oceans, ammonites, marine reptiles, and many fish species vanished. Coral reefs, already stressed by environmental changes before the impact, suffered massive losses. Mosasaurs and plesiosaurs, apex predators of the seas, disappeared entirely. On land, the dinosaurs faced their final days. The large theropods, including Tyrannosaurus, could not survive the sudden loss of prey. Giant herbivores such as Triceratops and Hadrosaurs succumbed as vegetation died. Ecosystems that had supported dinosaurs for millions of years unraveled within a geological blink. Only small animals that could exploit alternative food sources had a chance to survive. One of the most important survival advantages belonged to mammals. Small, burrowing mammals were able to withstand the impact winter by sheltering underground, feeding on insects, roots, and seeds resources that persisted even when forests collapsed. Their flexibility in diet and habitat allowed them to endure conditions that exterminated larger vertebrates. Though mammals had existed alongside dinosaurs for over 100 million years, they had remained small and relatively inconspicuous. Now, their time to expand had arrived. Birds also survived the extinction. Although many ancient bird lineages vanished, a group of ground-dwelling birds with beaks capable of eating seeds and hard plant material managed to persist. Their ability to feed on durable food sources during the darkness allowed them to withstand the collapse in insect populations and plant life. These surviving birds would eventually diversify into the vast array of species seen today. Insects faced severe declines, but many recovered thanks to their rapid reproduction and adaptability. Freshwater ecosystems also fared relatively well compared to terrestrial and marine environments. Rivers and lakes provided refuges for species less dependent on sunlight-driven food webs, such as certain fish and amphibians. While the asteroid impact was the primary driver of extinction, it was not the only factor shaping the end Cretaceous environment. Volcanic activity in the Deccan Traps of India had been releasing massive amounts of lava, carbon dioxide, and sulfur dioxide for hundreds of thousands of years. Some scientists argue that this volcanism contributed to long-term warming prior to the impact, weakening ecosystems. Others suggest it may have worsened conditions after the impact by prolonging atmospheric disruptions. Whether the volcanism amplified the devastation or played a secondary role, the combination of both events created an environment too extreme for most Cretaceous species to survive. The extinction event eliminated an estimated 75% of all species on Earth: flying reptiles, giant marine reptiles, ammonites, and nearly all large dinosaurs disappeared. Ecosystems collapsed globally. Food webs broke apart. Forests were reduced to charred remnants. The Earth was plunged into a state of ecological shock. Yet, in the aftermath of destruction, life began its slow recovery. Within a few hundred years, ferns started to colonize burned landscapes, a pattern known as the fern spike, seen in fossil records around the world. As sunlight gradually returned, plants grew back, soils stabilized, and insects repopulated ecosystems. Mammals emerged from hiding, exploiting new resources and expanding into niches once occupied by dinosaurs. Birds diversified into new forms, filling aerial and terrestrial niches vacated by extinct species. Surviving reptiles adapted to new conditions as well, though their diversity remained far lower than during the Cretaceous. Crocodilians endured the extinction event, perhaps due to their semi-aquatic lifestyles and low metabolism, which allowed them to survive extended periods without food. As the planet healed, mammals began to radiate into astonishing diversity. Freed from the dominance of dinosaurs, they evolved into herbivores, carnivores, scavengers, and arboreal species. Their descendants would give rise to primates, ungulates, whales, bats, rodents, and countless other groups. The extinction event, catastrophic as it was, paved the way for the rise of mammals and ultimately humans. The crater at Chicxulub, buried beneath sediment and ocean water, remains a silent reminder of this catastrophic chapter. Geological layers enriched in iridium, an element rare on Earth but common in asteroids, record the moment of impact. Shocked quartz, spherules, and tsunami deposits provide further evidence. These clues form a global signature, marking the boundary between the Cretaceous and the Paleogene periods. The asteroid impact was a stark demonstration of Earth's vulnerability to cosmic events. It reshaped the trajectory of evolution, ending the age of dinosaurs and ushering in a new era dominated by mammals. Without this impact, the world might have remained a planet of giants, towering sauropods, horned ceratopsians, razor-toothed theropods, and swift ornithopods. Instead, their extinction opened the door for new life forms. The end of the dinosaurs was not the end of life, but a dramatic transformation. Ecosystems were destroyed, yet from the ashes emerged new possibilities. The natural world rebuilt itself, species adapted, and evolution continued its relentless course. In the vast story of Earth's history, the asteroid impact stands as one of the most consequential events, a moment when everything changed in an instant, setting the stage for the rise of mammals and eventually the emergence of humans. In the quiet aftermath of the asteroid impact that ended the age of dinosaurs, Earth entered a period of destruction, emptiness, and slow recovery. Forests were burned, skies were darkened, oceans were disrupted, ecosystems collapsed under the weight of global catastrophe. Yet beneath the devastation, small survivors emerged, creatures that had lived alongside dinosaurs for over 100 million years, but had always remained in the shadows. These were the mammals, once tiny and overlooked, now stepping into a world cleared of towering reptiles. Their rise would reshape the planet and eventually lead to the emergence of humans. Before the extinction, mammals were already a diverse but minor presence in Mesozoic ecosystems. They had evolved from synapsid ancestors during the Triassic and had survived through the Jurassic and Cretaceous in small, nocturnal niches. Mammals possessed key adaptations: warm-blooded metabolism, fur for insulation, advanced hearing, and parental care. But they lived in fear of predatory theropods and competed for limited resources. Their small size was both a limitation and a strength. It allowed them to exploit food sources such as insects, seeds, and small vertebrates that dinosaurs ignored. When the asteroid struck, these very traits became their salvation. Small mammals could hide in burrows, cracks, and sheltered environments that offered protection from firestorms and falling debris. Their ability to feed on a wide range of foods, including insects, roots, and seeds, allowed them to survive when plants withered and prey animals died. Many mammals could enter torpor or hibernation-like states, conserving energy and enduring long periods without food. These strategies helped them withstand the impact winter that devastated larger species. Once sunlight returned and plants began to regrow, mammals quickly took advantage of the recovering ecosystems. Freed from the ecological dominance of dinosaurs, they diversified at an astonishing rate. Their evolutionary expansion during the Paleocene and Eocene epochs is one of the most remarkable radiations in Earth's history. Mammals evolved into forms that filled nearly every available niche: runners, climbers, gliders, swimmers, burrowers, and predators. One of the first major groups to expand were the multituberculates. These rodent-like mammals thrived for millions of years, equipped with specialized molars for grinding plant material. They occupied arboreal and terrestrial habitats, feeding on seeds, nuts, and vegetation. Multituberculates were highly successful until they were eventually outcompeted by early rodents in the Eocene. Placental mammals, those that nourish their young through a placenta before birth, diversified even more dramatically. Early placental mammals were small, but they rapidly evolved into new forms that explored fresh ecological opportunities. From these early ancestors emerged the foundations of modern mammalian orders: primates, carnivores, ungulates, bats, whales, and more. In the Paleocene, Earth's climate was warm and stable. Forests spread across continents, creating vast tropical and subtropical environments. These forests provided food and shelter for small, tree-dwelling mammals. Among these were the earliest primates, small, nocturnal creatures with grasping hands, forward-facing eyes, and flexible limbs. Their sensory adaptations made them adept climbers and foragers in dense vegetation. These early primates laid the groundwork for the future evolution of monkeys, apes, and eventually humans. Insectivores and small omnivores scurried across the forest floors, feeding on insects that rebounded quickly after the extinction. Small carnivorous mammals evolved sharper teeth and more agile bodies, hunting other mammals, reptiles, and amphibians. These early carnivores would later give rise to the great predatory lineages of the Cenozoic, including cats, dogs, bears, and hyenas. In the oceans, the extinction had eliminated the dominant marine reptiles. This opened opportunities for mammals to invade aquatic environments. Over millions of years, some mammals evolved into fully marine forms. Early ancestors of whales, known as pachycetids, began as land-dwelling creatures with hooved limbs. They hunted fish along riverbanks and gradually adapted to life in water. Their descendants would develop streamlined bodies, flippers, sonar systems, and other traits that define modern whales. Other mammals evolved to fill grazing and browsing roles on land. During the Paleocene and early Eocene, large herbivores such as pantodonts and euanthotheres appeared. These early ungulates had massive bodies, specialized teeth, and sometimes elaborate skull ornamentation. Though many of these lineages died out, they paved the way for the evolution of modern herbivores like horses, elephants, rhinos, and deer. The Eocene epoch, beginning 56 million years ago, marked a golden age for mammals. Global temperatures rose to some of the highest levels in the Cenozoic, creating lush tropical conditions even near the poles. Forests covered much of the planet, supporting extraordinary mammalian diversity. Primates proliferated in warm, forested regions of Asia, Europe, and North America. Bats evolved the ability to fly, filling nocturnal aerial niches and feeding on insects and fruit. Carnivorous mammals, including early mesonychids and creodonts, roamed the forests and grasslands, hunting other mammals, birds, and reptiles. Some mesonychids became large, wolf-like predators, though they would eventually be replaced by more advanced carnivorans. The emergence of hooved mammals, artiodactyls, and perissodactyls further expanded herbivore diversity. Horses, tapirs, and rhinos represent early perissodactyl lineages, while artiodactyls eventually gave rise to deer, cattle, pigs, camels, and other familiar animals. As mammals diversified, so did birds. Flight gave birds access to new habitats and hunting strategies. Some birds became swift predators, others evolved long legs for ground running, and still others adapted to aquatic environments. The Cenozoic saw the rise of giant flightless birds such as terror birds in South America, which became apex predators in regions where mammals had not yet assumed dominant roles. Throughout the Paleocene and Eocene, Earth's climate remained warm, but gradual cooling trends began. The movement of continents altered ocean currents and atmospheric patterns. The formation of the Drake Passage and the opening of southern ocean pathways would eventually initiate the formation of Antarctic ice sheets. Cooling climates changed vegetation patterns and influenced mammalian evolution, favoring species adapted to seasonal environments. Forest ecosystems began transitioning into more open habitats. Grasslands emerged during the Oligocene and Miocene epochs, providing opportunities for grazing animals. Mammals adapted to these new environments by evolving longer limbs, faster running speeds, and specialized teeth for grinding grass. Predators adapted in turn. evolving powerful jaws, sharp claws, and endurance for long-distance pursuit. Through these transformations, mammals continued to rise, diversify, and dominate. Their intelligence, parental care, flexible bodies, and warm-blooded metabolism allowed them to adapt to shifting climates and ecological challenges. Their ability to exploit new resources and environments made them one of the most successful groups in Earth's history. The extinction of the dinosaurs did not guarantee mammals' success, but it created a world where their evolutionary potential could unfold without competition from giant reptiles. Mammals filled niches that had remained inaccessible during the Mesozoic. They became the caretakers of forests, the grazers of plains, the predators of ecosystems, and the engineers of landscapes. And among these mammals, one lineage would eventually develop exceptional cognitive abilities, advanced social structures, and the capacity for complex communication. These primates, descendants of the tiny creatures that emerged in the early Cenozoic, would evolve into early humans, shaping the future of the planet in ways no other species ever had. But before the rise of humans, Earth would witness another chapter filled with extraordinary creatures, the age of megafauna, where giant mammals dominated continents and shaped ecosystems across the world. After the dinosaurs vanished and mammals began their rise, Earth entered a new era defined by extraordinary diversity and dramatic evolutionary innovation. As climates shifted, continents drifted, and ecosystems transformed, mammals adapted into incredible forms. Many of these new species grew to enormous sizes, becoming the megafauna giant mammals that dominated landscapes from the Pleistocene to earlier epochs of the Cenozoic. It was an age of towering herbivores, fierce predators, and some of the most iconic creatures ever to walk the planet. These giants shaped ecosystems, influenced vegetation, and interacted with early humans in ways that would leave lasting marks on Earth's history. The roots of the megafauna era began tens of millions of years after the dinosaur extinction. During the Oligocene and Miocene epochs, global climates cooled gradually, shaping new habitats. Forests gave way to expanding grasslands, especially in Africa and Eurasia. Open landscapes favored large herbivores and the predators that hunted them. Grazing mammals evolved high-crowned teeth, adapted for tough grasses. Running speed became essential for survival. Predators adapted with long legs, powerful jaws, and sharp claws. One of the earliest giant mammals was Paraceratherium, also known as Indricotherium. Living during the Oligocene, around 34 to 23 million years ago, Paraceratherium was the largest land mammal to ever exist. Standing over 5 meters tall at the shoulder and weighing up to 20 tons, it dwarfed modern elephants. With its long neck and powerful limbs, Paraceratherium browsed high vegetation across Asia's open woodlands. Its massive size protected it from predators, allowing it to roam vast territories in search of plant matter. As grasslands spread during the Miocene epoch, new megafauna emerged. Herds of antelope, horses, rhinos, and camels migrated across plains. Early elephants, including Gomphotheres and mastodons, diversified into numerous species with varied tusk shapes and body sizes. Some evolved shovel-like lower jaws for digging roots. Others developed long spiraled tusks for display and combat. Predators of the Miocene were equally impressive. The largest terrestrial predator of the time was Amphision, known as the bear dog. Weighing up to 500 kilograms, Amphision combined the powerful build of a bear with the speed and agility of a wolf. Other predators, such as Machairodontine, saber-toothed cats, evolved long, blade-like canine teeth, specialized for slashing soft tissue. Although saber-tooths are most famously associated with the later Pleistocene, their lineage began millions of years earlier. As the Pliocene epoch approached around 5 million years ago, climates continued cooling. Glaciations began affecting polar regions. Grasslands expanded further. These environmental changes set the stage for the rise of the Pleistocene megafauna, the animals most commonly associated with the term Ice Age giants. By the Pleistocene, beginning around 2.6 million years ago, massive ice sheets covered large parts of North America, Europe, and Asia. Between glacial cycles, warmer interglacial periods allowed forests and grasslands to recover. This constant environmental fluctuation created a world of diverse habitats, tundras, savannas, woodlands, and steppe ecosystems, each hosting unique megafaunal communities. The woolly mammoth became one of the most iconic species of this era. Adapted to cold climates, mammoths developed thick fur, insulating fat layers, and long curved tusks used for foraging and fighting. Their large size helped conserve heat, and their social behavior resembled modern elephants. Mammoths roamed across northern Eurasia and North America, forming herds and feeding on grasses, shrubs, and bark. Another legendary megafaunal herbivore was the woolly rhinoceros. Covered in dense fur and equipped with two long horns, it thrived in cold steppe environments. Its horns were used for defense and possibly for clearing snow to reach vegetation. Similar to mammoths, woolly rhinos played a major ecological role by maintaining grassland habitats through grazing and movement. Giant ground sloths dominated the Americas. Species such as Megatherium and Megalonyx could reach lengths of 6 meters and weigh several tons. They fed on leaves, branches, and shrubs, using their long claws to pull down vegetation. Despite their slow movement, they were formidable due to their size and strength. North America was home to some of the most diverse megafaunal assemblages. American mastodons roamed forests, feeding on twigs and bark. The American lion, larger than modern African lions, hunted across plains and woodlands. The dire wolf, heavier and more robust than today's grey wolf, formed packs to hunt large prey. The giant, short-faced bear, one of the largest carnivorous mammals ever, could stand over 3 meters tall when upright and likely scavenged or hunted opportunistically. In South America, megafaunal diversity flourished as well. Glyptodons, massive relatives of armadillos, were protected by thick, domed shells and spiked tails. Macrauchenia, with its long neck and trunk-like snout, browsed vegetation in open environments. Toxodons and other large herbivores occupied niches similar to modern hippos or rhinos. South America's unique predators included the saber-toothed Smilodon, which used its long canines and powerful forelimbs to subdue large prey. Australia's megafauna was distinctive and shaped by its long isolation. Diprotodon, the largest marsupial ever known, resembled a giant wombat and weighed up to 3 tons. Giant kangaroos, some standing over 3 meters tall, hopped across open plains. The marsupial lion, Thylacoleo, was a fierce predator equipped with slicing teeth and strong limbs. Megafauna shaped ecosystems in profound ways. Their feeding habits maintained grasslands, prevented forest overgrowth, and distributed nutrients. Their migrations influenced plant growth and soil fertility. Predators kept herbivore populations in balance, maintaining biodiversity. Without these giants, many ecosystems would have functioned very differently. Yet, despite their success, megafauna faced growing challenges toward the end of the Pleistocene. Climate change intensified, as Earth underwent cycles of glacial advance and retreat. Temperatures fluctuated, ice sheets grew and shrank, and habitats shifted. Some species adapted by migrating, others faced shrinking ranges or reduced food supplies. However, climate alone cannot explain the widespread extinction of megafauna across multiple continents. A new factor had entered the picture: humans. As anatomically modern humans spread across Africa, Europe, Asia, Australia, and eventually the Americas, their hunting techniques, tools, and cooperative strategies became increasingly effective. Humans targeted large animals for their meat, hides, bones, and fat. Megafauna, which had evolved without pressure from intelligent tool-using predators, were vulnerable. In many regions, the timing of human arrival corresponds closely with megafaunal extinction. In Australia, most megafauna disappeared soon after humans arrived, around 50,000 years ago. In North America, many species vanished between 13,000 and 11,000 years ago, shortly after humans crossed the Bering Land Bridge. Europe and Siberia experienced similar declines, though some species persisted longer in isolated regions. The extinction of megafauna reshaped ecosystems. Grasslands transformed into forests in some regions as grazing pressure decreased. Predators that relied on large prey declined. Nutrient cycles changed as giant animals no longer transported minerals across landscapes. The disappearance of megafauna marked the end of an evolutionary chapter that had lasted millions of years. Yet, some giants survived into modern times. Elephants, rhinos, and hippos represent the last vestiges of ancient megafaunal lineages. Their ancestors once roamed alongside mammoths and giant sloths. Today, they remain reminders of an age when enormous mammals shaped the world. The age of megafauna was a time of ecological richness and evolutionary experimentation. It saw the rise of massive herbivores, powerful predators, and unique species adapted to every corner of the planet. It also witnessed the growing influence of humans, whose actions would eventually shape ecosystems more profoundly than any natural force. And as the megafauna declined, another chapter began: the emergence of early humans, whose evolution, migration, and survival would forever alter the course of Earth's history. The rise of humans is one of the most remarkable evolutionary journeys in the history of life on Earth. It spans millions of years, beginning with ancient primates living in lush forests and culminating in a species capable of reshaping the entire planet. The human lineage did not emerge suddenly, nor did it follow a straight path. Instead, it was a complex web of branching species, extinctions, migrations, and adaptations. The evolution of humans is a story of resilience, intelligence, cooperation, and constant transformation. The origins of the human lineage trace back to early primates that evolved around 60 million years ago during the Paleocene and Eocene epochs. These early primates were small, tree-dwelling mammals with grasping hands, forward-facing eyes, and flexible limbs. They fed primarily on fruits, insects, and leaves. Their arboreal lifestyles favored good depth perception, agile movement, and enhanced cognitive abilities. As continents shifted and climates changed, primates diversified. Around 20 to 25 million years ago, during the Miocene, the ancestors of apes evolved in Africa. These early apes, such as proconsul, possessed larger brains than earlier primates, lacked tails, and had more flexible shoulder joints suited for climbing and swinging through trees. Over time, multiple ape lineages emerged, some of which would eventually give rise to gorillas, chimpanzees, orangutans, and humans. The direct human lineage split from the common ancestor shared with chimpanzees around 6 to 7 million years ago. The earliest hominins members of the human family began adapting to environments that were changing from dense forests to open savannas due to climate shifts in East Africa. One of the most significant early adaptations was bipedalism, the ability to walk on two legs. Fossils such as Sahelanthropus chadensis, Orrorin tugenensis, and Ardipithecus ramidus show evidence of upright walking. Bipedalism offered several advantages. Walking on two legs freed the hands for carrying objects, gathering food, and eventually using tools. It allowed early hominins to see over tall grasses, spot predators, and navigate open landscapes. It also reduced energy consumption during long-distance travel, a valuable trait for survival in expanding savanna environments. Though early hominins still climbed trees, their skeletal structures show a clear shift toward terrestrial locomotion. By around 4 million years ago, Australopithecines had appeared. Australopithecus afarensis, famously represented by the fossil skeleton Lucy, was one of the best-known species from this period. These hominins were fully bipedal, but retained long arms for climbing. They lived in Africa's woodlands and savannas, feeding on fruits, roots, seeds, and possibly small animals. Their brains were slightly larger than those of chimpanzees, but far smaller than those of modern humans. The next major leap in human evolution involved tool use and increased brain size. Around 2.5 million years ago, the genus Homo emerged. Homo habilis, often called handyman, used simple stone tools to crack open bones, cut meat, and process plant material. These tools marked the beginning of technological evolution, a trait that would become central to human success. With the emergence of Homo erectus around 1.9 million years ago, the human lineage expanded dramatically. Homo erectus possessed a larger brain, more modern body proportions, and advanced tool-making abilities. They crafted Acheulean hand axes, controlled fire, and became the first hominins to leave Africa. Their migrations carried them into Asia and Europe, where they adapted to diverse climates and environments. Fire allowed them to cook food, providing easier access to nutrients and supporting further brain growth. Homo erectus also exhibited social behaviors that were more advanced than earlier hominins. Evidence suggests cooperative hunting, group living, and possibly care for injured individuals. These behaviors laid the foundation for future human societies built on cooperation and shared knowledge. As time progressed, multiple human species coexisted across the globe. In Africa, species such as Homo heidelbergensis and Homo rhodesiensis emerged, serving as transitional forms between Homo erectus and later humans. In Europe and Western Asia, Homo neanderthalensis, the Neanderthals, evolved. Neanderthals were powerful, intelligent hominins adapted to cold climates. They hunted large animals, created tools, controlled fire, buried their dead, and possibly used symbolic objects. Their brains were as large as, or even larger than those of modern humans. In Asia, another mysterious lineage, the Denisovans, lived and interbred with both Neanderthals and early modern humans. Genetic evidence has revealed Denisovan ancestry in modern populations of Melanesia, Australia, and parts of Southeast Asia, showing that human evolution involved extensive interbreeding among different groups. The emergence of Homo sapiens, anatomically modern humans, occurred around 300,000 years ago in Africa. Early Homo sapiens displayed a combination of advanced cognitive abilities, symbolic thinking, and complex communication. Their tool technologies became more refined, featuring blades, bone points, and artistic expressions. Cave paintings, beads, carvings, and ochre markings indicate the development of culture, spirituality, and abstract thought. Around 70,000 years ago, humans began migrating out of Africa in waves, eventually populating all major continents. This migration was aided by advanced tools, cooperative social structures, and the ability to adapt to a wide range of climates. Humans crossed into the Middle East, traveled through Europe and Asia, reached Australia around 65,000 years ago, and eventually entered the Americas around 15,000 to 20,000 years ago, possibly earlier. As humans expanded, they encountered and interbred with other hominin species. Neanderthals disappeared around 40,000 years ago, likely due to a combination of climate change, competition, and assimilation into human populations. Denisovans also vanished, leaving only traces of their DNA behind. By the end of the Pleistocene, Homo sapiens were the last surviving human species. The evolution of language played a critical role in human success. Complex vocal communication allowed early humans to share knowledge, coordinate hunts, transmit culture, and build social bonds. Language enabled humans to develop stories, myths, and teachings passed across generations, a unique advantage that shaped every aspect of human societies. The development of advanced tools, clothing, shelters, and hunting strategies allowed humans to thrive in diverse environments, from tropical forests to Arctic tundra. Fire provided warmth, protection, and the ability to cook food. Symbolic thinking allowed for art, religion, and cultural identity. Cooperation enabled large groups to work together in ways no other species could match. As the Ice Age waned and climates warmed, humans transitioned from nomadic hunter-gatherers to early farmers. This shift, known as the Agricultural Revolution around 10,000 years ago, transformed human society. The domestication of plants and animals allowed for permanent settlements, population growth, and the development of civilizations. But agriculture came much later. The core of the human evolutionary story lies in millions of years of adaptation, cooperation, and innovation. From small, tree-dwelling primates to tool-using hunter-gatherers, the journey of the human lineage shows how evolution shaped a species capable of reshaping the world. The rise of humans marked the beginning of a new era in Earth's history, one where culture, technology, and intelligence became powerful evolutionary forces. And as humans spread across continents, they began reshaping ecosystems, influencing climates, and altering the fate of countless species. The next chapter unfolds with the global migrations of humans and the profound ways they transformed the Earth they inherited. After millions of years of evolution, adaptation, and survival, early Homo sapiens stood ready to expand far beyond their African homeland. Their intelligence, social cooperation, tool-making skills, and adaptability allowed them to thrive in environments that no other hominin species had ever conquered. The spread of humans across the planet was not a single migration, but a series of waves, each shaped by climate shifts, ecological opportunities, and innovations in technology and culture. This global expansion transformed both humanity and the natural world, setting the stage for the civilizations that would follow. The origins of modern humans trace back to Africa around 300,000 years ago. The oldest known fossils of Homo sapiens show a blend of archaic and modern features, rounded skulls, reduced brow ridges, and more delicate skeletons compared to earlier hominins. Early humans lived as hunter-gatherers, moving in small groups, using stone tools, controlling fire, and exploiting a wide range of foods. Their lives depended on cooperation, communication, and shared knowledge passed down through generations. As climates shifted during the late Pleistocene, Africa experienced cycles of wet and dry periods. During wetter phases, lakes expanded, vegetation flourished, and animal populations grew. During drier phases, resources became scarce, prompting human groups to move in search of better conditions. Around 100,000 to 70,000 years ago, the first significant migrations out of Africa began. These early migrations carried humans into the Arabian Peninsula, where fossil evidence shows their presence during periods when deserts were transformed into grasslands fed by monsoons. Some of these early groups likely died out or retreated due to harsh climatic cycles. But around 70,000 years ago, a major wave of migration began, one that would eventually populate the entire world. From Africa, humans crossed the Sinai Peninsula and moved into the Levant. There, they encountered Neanderthals, who had long inhabited Europe and Western Asia. Interactions between the two species included competition, cultural exchange, and interbreeding. Traces of Neanderthal DNA persist in nearly all non-African human populations today, reflecting this ancient contact. As humans expanded further across Asia, they encountered and interbred with another archaic group, the Denisovans. Though fossil evidence of Denisovans is scarce, genetic traces reveal that they contributed to the ancestry of modern populations in Melanesia, Australia, and parts of Southeast Asia. This genetic legacy highlights the interconnected nature of human evolution during global migration. Reaching South Asia, humans adapted to monsoon climates, tropical forests, and coastal environments. Coastal migration routes may have allowed early humans to access abundant seafood and travel rapidly along shorelines. Archaeological sites along the Indian Ocean suggest that humans arrived in Southeast Asia and Australia surprisingly early, potentially by 65,000 years ago. In Australia, humans encountered unique megafauna giant kangaroos, diprotodon, marsupial lions, and enormous birds. Armed with fire, cooperative hunting strategies, and knowledge of their new environment, humans thrived. Some megafaunal extinctions in Australia coincide with the arrival of humans, suggesting that hunting, habitat modification, or both played significant roles. Meanwhile, other groups of humans traveled north across Asia's vast grasslands. They hunted mammoths, woolly rhinos, horses, and bison. They developed sophisticated tools for cold weather survival, tailored clothing, shelters, fire pits, and weapons adapted for large prey. These humans evolved cultural traditions that helped communities survive in harsh climates. As Ice Age glaciers expanded, sea levels fell dramatically. This exposed land bridges, including the Bering Land Bridge connecting Siberia to Alaska. Between 20,000 and 15,000 years ago, humans crossed from Asia into the Americas. Once there, they expanded rapidly, following animal migrations and exploring new territories. By 13,000 years ago, humans had reached the southern tip of South America, marking one of the fastest large-scale migrations in prehistory. In the Americas, humans encountered an extraordinary array of megafauna, mammoths, mastodons, giant ground sloths, saber-toothed cats, and enormous bears. Armed with increasingly advanced projectile weapons and coordinated hunting strategies, human groups adapted quickly to the diverse environments of the Americas, from icy tundras to deserts, forests, and tropical climates. As in Australia, many megafaunal extinctions coincide with human arrival, though climate change also played a role. In Europe, humans arrived around 45,000 years ago. They entered landscapes dominated by Neanderthals and cold-adapted megafauna. Europe's harsh climates during the last glacial period challenged early humans, but they adapted with complex tools, tailored clothing, art, and symbolic behavior. Cave paintings in sites such as Lascaux and Chauvet reveal early humans' deep connection to their environment and their emerging capacity for artistic expression. As modern humans spread across the globe, they interacted with and ultimately replaced other hominin species. Neanderthals disappeared around 40,000 years ago. Denisovans vanished even earlier. Other archaic humans, such as Homo floresiensis and Homo luzonensis, persisted in Southeast Asia but eventually went extinct as well. Multiple factors contributed to their disappearance: competition for resources, inability to adapt to climatic fluctuations, interbreeding with modern humans, and possibly diseases. What set Homo sapiens apart was not just physical capability, but cultural and cognitive innovation. Humans developed language systems that allowed precise communication of ideas, strategies, emotions, and instructions. Symbolic thought gave rise to rituals, art, shared beliefs, and complex social structures. Cooperation expanded from small family units to large tribal networks. Humans learned to plan long-term, store food, trade materials, and create alliances. As populations grew and communities settled, social structures became more sophisticated. Humans created tools with increasing specialization: blades, spear throwers, fishing implements, needles for sewing, clothing, and ornaments for symbolic purposes. These tools reflected advanced cognition and cultural transmission. Knowledge accumulated over generations, each group building upon the achievements of those before them. Environmental changes also shaped human migrations. As the last ice age began to wane around 15,000 years ago, melting glaciers caused sea levels to rise. The Bering Land Bridge flooded, isolating the Americas. Rising seas reshaped coastlines across the world. Warming climates allowed forests to expand into previously frozen regions. Humans moved into these newly habitable areas, establishing populations in northern Europe, Siberia, and the Arctic. In the Arctic, humans developed specialized adaptations to survive extreme cold. The ancestors of the Inuit built insulated shelters, crafted sophisticated hunting tools, and developed clothing from animal skins. These adaptations allowed them to thrive in environments where few other humans had settled. As humans spread, they also shaped ecosystems, controlled burning practices, influenced plant growth and animal distribution. Hunting reduced populations of large animals. The arrival of humans on isolated islands often triggered rapid extinctions of species unaccustomed to predation. Through these interactions, humans became a major ecological force long before the rise of agriculture or civilization. After tens of thousands of years of global migration, humans were present on every continent except Antarctica. Each population developed unique cultures, languages, diets, and technologies adapted to their environments. These cultural innovations allowed humans to thrive in deserts, rainforests, mountains, savannas, tundras, and islands, something no other species on Earth had achieved. The global spread of humans set the foundation for the next major transformation in human history: the transition from hunting and gathering to agriculture. As climates warmed and plant distribution shifted, humans discovered that seeds planted in fertile soil could be cultivated into stable food supplies. Animals could be domesticated for labor, milk, and meat. This shift would give rise to permanent settlements, population growth, societal complexity, and, ultimately, civilizations. But long before cities and kingdoms emerged, it was the worldwide migration of humans, their adaptability, innovation, and cooperation that established their place as the dominant species on Earth. Their journey across continents shaped the natural world, influenced the fate of other species, and laid the groundwork for the remarkable cultural and technological developments that followed. The story continues with the dawn of agriculture and the rise of human civilization, a turning point that would transform both humans and the planet forever. For more than 95% of human existence, our ancestors lived as hunter-gatherers, moving across landscapes, following animal migrations, gathering plants, and adapting to the rhythms of nature. But around 12,000 years ago, a monumental transformation occurred. Humans began to shift from nomadic lifestyles to settled communities, from foraging to farming, from simple tools to organized societies. This transition marked the dawn of agriculture and the birth of civilization. It was one of the most profound turning points in the history of Earth and humanity. The roots of agriculture lie in the end of the last ice age. Around 15,000 to 12,000 years ago, global climates warmed, glaciers retreated, and rainfall patterns shifted. New plants spread into previously frozen or barren regions. Wild cereals, such as wheat and barley, flourished in parts of the Middle East. Large herds of megafauna dwindled, making hunting less reliable. Humans, already highly adaptable and observant, began experimenting with gathering and storing seeds. Over generations, humans learned that seeds dropped near their camps sprouted into new plants. They began intentionally planting seeds, clearing land, irrigating soil, and protecting growing plants from pests. This early experimentation evolved into systematic farming. The Fertile Crescent, stretching across modern Iraq, Syria, Turkey, and Iran, became one of the first centers of agricultural development. Here, humans domesticated wheat, barley, lentils, peas, sheep, goats, and cattle. Farming offered a more stable and predictable food supply compared to hunting and gathering. For the first time, humans could produce surplus food, more than they immediately needed. This surplus allowed populations to grow, settlements to expand, and people to specialize in tasks beyond food production. While hunter-gatherers typically lived in small bands of 20 to 50 people, early farming villages grew to hundreds and eventually thousands of inhabitants. Agriculture also developed independently in other parts of the world. In China, early farmers cultivated rice and millet. In New Guinea, people grew taro, yams, and bananas. In Africa, sorghum, millet, and teff were domesticated in the Americas. Indigenous peoples domesticated maize, beans, squash, potatoes, and quinoa. Each region contributed unique crops that shaped the diets and cultures of future civilizations. As food production increased, human societies transformed in every dimension. Permanent homes replaced temporary shelters, and villages became towns. Tasks became specialized. Farmers planted, shepherds herded, potters made vessels, weavers produced cloth, and toolmakers crafted improved tools. Trade networks emerged as communities exchanged goods and knowledge. Pottery allowed for food storage. Textiles allowed protection from harsh climates. New technologies spread rapidly between groups. With rising populations came new social structures. Leadership roles developed elders, chiefs, or councils that organized communal efforts such as irrigation, defense, and ceremonies. Inequality also emerged as some individuals accumulated more land, livestock, or tools than others. the foundations of social hierarchies, something rare among hunter-gatherers, began to take shape. The development of irrigation systems marked a major advancement in regions such as Mesopotamia and Egypt. Humans built canals, dams, and reservoirs to control water flow. This allowed farming in areas with limited rainfall. Irrigation supported larger populations and increased agricultural output. These innovations allowed for the rise of cities, centralized governments, and complex societies. Around 6,000 years ago, the world's first cities emerged. In Mesopotamia, Uruk became one of the earliest major urban centers. It housed tens of thousands of people, monumental architecture, temples, and administrative buildings. Writing systems began to appear first as records of trade and agricultural production, then evolving into complex scripts capable of expressing language, history, and mythology. The earliest known writing, cuneiform, emerged in Mesopotamia around 5,000 years ago. Civilization expanded across various regions. In Egypt, the Nile River supported a powerful kingdom known for monumental pyramids, art, and a sophisticated writing system. The Nile's predictable flooding cycle provided fertile soil that sustained abundant food production. In the Indus Valley, cities like Mohenjo-Daro and Harappa flourished, showcasing advanced urban planning, drainage systems, and trade networks. In China, early dynasties developed writing, bronze technologies, and complex social structures. In the Americas, civilizations arose independently. The Olmec, Maya, Aztec, and Inca built cities, created intricate calendars, developed writing systems, and engineered monumental architecture. Maize agriculture supported large populations, while terraced farming in the Andes transformed mountainous landscapes into productive agricultural zones. Farming also reshaped human relationships with the environment. Forests were cleared for fields, rivers were controlled with canals, animals were domesticated, altering ecosystems and evolutionary paths. Dogs, the earliest domesticated animals, helped humans hunt and protect settlements. Cattle, sheep, goats, and pigs became vital sources of food, labor, and materials. However, domestication also brought zoonotic diseases, pathogens that spread from animals to humans, influencing human immunity and population health. As societies grew more complex, conflicts arose over land, water, and resources. Warfare became more organized, with armies, fortifications, and weapons. Metallurgy first, copper, then bronze, and later iron advanced toolmaking and weaponry. Trade networks connected distant civilizations, carrying goods such as spices, textiles, metals, and precious stones across continents. Cultural exchange spread ideas, technologies, religions, and artistic traditions. Religion became a central part of early civilizations. Societies developed pantheons of gods, representing natural forces, fertility, war, and harvests. Temples became centers of cultural and political power. Rituals, ceremonies, and myths helped unify communities and reinforce social order. Writing allowed humans to record laws, stories, scientific observations, and administrative details. It enabled the preservation and transmission of knowledge across generations. Literature, mathematics, astronomy, and philosophy emerged as intellectual traditions. Civilizations built astronomical monuments to track the movement of stars and planets, allowing them to create calendars that guided farming cycles. The agricultural revolution did not come without challenges. Dependence on farming made communities vulnerable to droughts, floods, pests, and soil depletion. Crowded settlements increased the spread of disease. Social inequality and labor demands led to hierarchical societies with elites and laborers. Environmental transformations, such as deforestation and soil erosion, had long-term consequences. Yet, agriculture fundamentally reshaped human destiny. It allowed for population growth, technological innovation, artistic expression, and political organization. It laid the foundation for nations, trade networks, scientific advancements, and cultural achievements. The dawn of civilization marked humanity's transition from surviving within nature to actively shaping the environment. As cities grew and empires formed, humans entered a new era, characterized by monumental achievements, the construction of pyramids, ziggurats, roads, irrigation systems, and complex governments. Human societies became increasingly interconnected. Knowledge expanded through writing, trade, and shared culture. The dawn of civilization set humanity on a path that would alter the planet itself. Agriculture transformed landscapes. Urbanization concentrated populations. Technological innovations accelerated. These changes laid the groundwork for the modern world, where human activity would become a dominant force shaping Earth's climate, ecosystems, and future. The next chapter explores how civilizations expanded, innovated, and influenced the natural world, and how their growth eventually led to the interconnected global society we know today. As human civilization expanded across the world, it transformed landscapes, altered climates, and reshaped ecosystems in ways no other species had ever achieved. From the earliest agricultural societies to the rise of empires and global trade networks, humans became a geological and ecological force capable of changing the course of evolution itself. The shaping of modern ecosystems is a story of innovation, adaptation, and unintended consequences, a story that continues unfolding today. After the agricultural revolution and the formation of early civilizations, human populations grew steadily. Forests were cleared for farmland. Rivers were dammed and diverted. Grazing animals transformed grasslands. Farming terraces sculpted mountainsides. Each technological advancement increased humanity's ability to modify the environment. By 5,000 years ago, civilizations in Mesopotamia, Egypt, the Indus Valley, and China were already altering ecosystems on a large scale. Irrigation networks supported vast fields of crops. Domesticated animals grazed across continents. Cities grew into dense population centers that consumed immense amounts of resources. These early modifications marked the beginning of anthropogenic change, human-driven transformation of ecosystems. As populations grew and societies advanced, humans began spreading species far beyond their native ranges. Crops such as wheat, barley, and rice moved with migrating farmers. Domesticated animals like cattle, horses, and sheep followed human expansion. These species reshaped local ecosystems, often outcompeting native plants and animals. In ancient Egypt, the Nile River was carefully managed to control floods and support agriculture. This stewardship allowed Egyptian civilization to flourish for thousands of years. Yet, even there, soil salinization and shifting river channels eventually strained ecosystems. In Mesopotamia, irrigation intensified soil degradation, turning once fertile landscapes into deserts over centuries. The rise of empires increased ecosystem changes. Rome, Greece, Persia, and China cut down forests for timber, farmland, and shipbuilding. Deforestation led to soil erosion, loss of wildlife, altered rainfall patterns, and reduced biodiversity. vast road networks connected regions, enabling trade but also facilitating the spread of invasive species, diseases, and pests. As civilizations interacted through trade routes such as the Silk Road, species and technologies spread between continents. Rice from China reached Southeast Asia and India. Citrus fruits traveled from East Asia to the Mediterranean. Horses spread across Asia and Europe, transforming transportation and warfare. Each exchange influenced ecosystems by introducing new biological players. By the medieval era, human populations continued to rise, and innovations in farming increased productivity. The invention of the heavy plough, crop rotation, and improved irrigation allowed more land to be cultivated. Forests and wetlands were drained to create farmland. Though these innovations supported larger populations, they reduced natural habitats and weakened ecosystems. The discovery of new continents by European explorers in the late 15th century accelerated global ecological change. The Columbian Exchange, the movement of plants, animals, people, and diseases between the Old and New Worlds, reshaped ecosystems across the globe. Crops like maize, potatoes, and tomatoes spread from the Americas to Europe, Africa, and Asia, dramatically increasing food security and population growth. In return, Europeans brought wheat, sugarcane, coffee, and livestock to the Americas, transforming landscapes. Cattle, horses, pigs, sheep, and goats multiplied rapidly, displacing native species and altering ecosystems. Alongside this exchange came diseases such as smallpox, measles, and influenza. These pathogens devastated indigenous populations in the Americas, leading to massive demographic shifts that further altered the ecological balance. Abandoned farmlands reverted to forests in some regions, while plantations and colonial agriculture replaced ecosystems in others. The Industrial Revolution, beginning in the 18th century, marked a dramatic acceleration of human influence over the natural world. Coal, steam engines, and mechanization allowed humans to mine deeper, build larger cities, and produce goods on unprecedented scales. Fossil fuel combustion released large amounts of carbon dioxide into the atmosphere, initiating long-term changes to Earth's climate. Industrial agriculture, powered by machinery and later by chemical fertilizers and pesticides, significantly increased food production but reduced biodiversity. Vast monocultures replaced diverse agricultural landscapes. Rivers were diverted, wetlands drained, and grasslands ploughed. Habitats fragmented into isolated patches, threatening countless species. As cities grew, urban ecosystems emerged. Wildlife adapted to human environments. Pigeons, rats, foxes, and crows thrived in streets and parks. Industrial pollution contaminated air, soil, and water. Forests in Europe and North America shrank dramatically during industrial expansion, though some later recovered due to conservation efforts and economic shifts. The invention of railways and steamships connected distant parts of the world, accelerating the spread of invasive species. Rats stowed away on ships, rabbits overran Australia, and kudzu vines smothered landscapes in the southern United States. These species, freed from natural predators, reshaped ecosystems in ways often irreversible. The 20th century intensified human influence more than any previous era. World population grew from 1.6 billion in 1900 to over 8 billion by the 21st century. Technological innovations advanced at a pace faster than ecosystems could adapt. Cars, electricity, synthetic chemicals, plastics, fertilizers, and global trade revolutionized human life but strained the natural world. Pollution became a major ecological threat. Chemicals like DDT disrupted food webs by harming predatory birds. Plastic waste accumulated in oceans, forming massive floating debris fields and entering the diets of marine animals. Oil spills devastated coastlines and aquatic ecosystems. Deforestation accelerated in tropical regions such as the Amazon, Southeast Asia, and Central Africa. Forests were cleared for agriculture, timber, and livestock grazing. The loss of rainforests, among the most biodiverse ecosystems on Earth, reduced carbon storage and contributed to climate change. Climate change itself emerged as one of the most critical consequences of industrialization. Rising greenhouse gas levels warmed the planet, altered weather patterns, melted polar ice, and raised sea levels. Coral reefs suffered bleaching due to warming oceans. Species struggled to adapt as their habitats shifted or disappeared. Yet alongside destruction came new forms of conservation. By the mid-20th century, scientists and environmentalists recognized the need to protect ecosystems. National parks, wildlife reserves, and environmental laws emerged. Species such as the American bison, the bald eagle, and the California condor were saved from extinction through concerted efforts. International treaties aim to protect endangered species, reduce pollution, and combat climate change. Modern ecosystems reflect a blend of natural processes and human influence. Forests regrew in parts of Europe and North America where agriculture declined. Some species adapted remarkably well to urban environments. Wetlands restored by conservation projects provided habitat for birds and aquatic life. Rewilding initiatives reintroduced wolves, lynx, and bison to regions where they had vanished. Yet challenges remain immense. Many species continue to face extinction due to habitat loss, poaching, pollution, and climate change. Coral reefs decline at alarming rates. Insects essential for pollination are decreasing. The melting of ice sheets threatens coastal ecosystems worldwide. Human activity has become the dominant force driving ecological change, so dominant that many scientists refer to the current era as the Anthropocene. This proposed geological epoch reflects the profound imprint humans have left on Earth's atmosphere, geology, and biosphere. Modern ecosystems are no longer shaped solely by natural forces, but by the actions, decisions, and technologies of one species. The story of Earth has entered a chapter where humans hold the power to either restore ecological balance or push ecosystems toward further collapse. The next outline explores the future, the potential paths for Earth's ecosystems, the role of humans in shaping them, and the challenges and opportunities that lie ahead. The story of Earth spans more than 4.5 billion years, a tale of creation, transformation, extinction, and renewal. From molten beginnings to oceans teeming with life, from towering dinosaurs to the rise of humans, the planet has endured constant change. Now, as Earth enters a new chapter shaped heavily by human influence, the future of the planet stands at a crossroads. What lies ahead depends not only on natural processes, but on the decisions, actions, and technologies of a single species, humanity. To glimpse Earth's future, we must first understand the forces currently shaping the planet. Human activity has altered atmospheric chemistry, changed land use patterns, driven species extinctions, and warmed the global climate. Carbon dioxide levels are higher today than at any point in the last several million years. Glaciers and ice sheets are melting at accelerating rates. Sea levels are rising, threatening coastal cities and ecosystems. Extreme weather events, heat waves, storms, floods, and droughts are becoming more frequent. The next century will be defined by how humans respond to these changes. If emissions continue unchecked, global temperatures may rise several degrees, pushing ecosystems beyond their resilience limits. Coral reefs may vanish entirely in a warmer, more acidic ocean. Tropical forests may dry and burn, releasing stored carbon and accelerating warming. Species struggling to adapt may face extinction. Humans themselves will confront challenges related to food security, water availability, disease, and displacement. However, the future is not predetermined. Humans possess the intelligence and technology to alter this trajectory. Renewable energy systems, solar, wind, hydroelectric, geothermal, are becoming more efficient and widespread. Advances in battery storage, grid technology, and electric transportation offer pathways to drastically reduce emissions. Innovations in carbon capture, climate engineering, and sustainable agriculture hold potential to restore ecological balance. In the coming centuries, humanity may enter an era of ecological restoration. Forests regrown, rivers rehabilitated, extinct species revived through genetic techniques, and ecosystems preserved through global cooperation. The success of such efforts depends on long-term commitment and international collaboration. Future generations may look back on this moment as the turning point when humans chose to protect and sustain the planet rather than exhaust it. Beyond climate and ecosystems, Earth's future includes geological processes that unfold over thousands to millions of years. Tectonic plates will continue to drift. Africa will collide with Europe, closing the Mediterranean Sea and forming new mountain ranges. Australia will move northward, eventually merging with Asia. California will shift along the San Andreas Fault, altering coastlines over vast timescales. These slow but powerful forces will reshape continents just as they have throughout Earth's history. Over the next 50,000 years, Earth's orbit and axial tilt will shift naturally, influencing climate cycles. Future ice ages may be delayed or altered due to human-caused warming. If greenhouse gas concentrations remain high, the planet may avoid glaciation for hundreds of thousands of years. Ecosystems will continue to adapt to changing climates, creating new biomes and species while others decline. In 1 million years, many species alive today will either be extinct or evolved into new forms. Humanity itself may change biologically or technologically. Cybernetic enhancements, genetic engineering, and artificial intelligence could transform human evolution, creating beings that differ dramatically from present-day humans. Such transformations could influence how future humans interact with Earth's ecosystems. In 10 million years, continents will have moved significantly. The Atlantic Ocean will widen, pushing the Americas farther from Europe and Africa. New mountain ranges may emerge, oceans may shift, and climate zones may reorganize. Species evolution will produce entirely new ecosystems, shaped by both natural selection and the residual influences of human activity. In 50 million years, the outlines of modern continents may be unrecognizable. Africa may fuse with Europe and Asia, forming massive supercontinents. New oceans may open. Biodiversity will flourish in ways impossible to predict as evolution fills ecological niches created by millions of years of change. New predators, herbivores, plants, and marine creatures will dominate landscapes, just as dinosaurs and megafauna once did. In 250 million years, Earth may once again form a supercontinent as tectonic plates converge. Scientists predict several potential configurations. One possibility is Pangaea Ultima, a supercontinent where most landmasses join near the equator. Such a configuration would drastically alter global climate, potentially creating vast deserts in the interior and intense monsoons around coastal regions. Life on such a supercontinent would evolve adaptations suited for extreme climates. In 500 million years, the sun will have grown brighter, increasing its energy output and warming Earth's surface. Higher temperatures may challenge the survival of complex life. Oceans may evaporate slowly, and the planet's climate may shift toward conditions that resemble early Venus. Long before the sun reaches its red giant phase, Earth may become uninhabitable for many organisms. In 1 billion years, rising solar output may cause Earth's oceans to evaporate completely. Without oceans, weathering cycles and atmospheric processes will collapse, stripping the planet of its ability to regulate climate. Life, if it still exists, will be limited to hardy microorganisms that can survive in extreme environments. In 4 to 5 billion years, the Sun will expand into a red giant, engulfing Mercury and Venus and possibly reaching Earth's orbit. Even if Earth is not consumed, its surface will be scorched and all remaining life will be extinguished. The planet may eventually be pushed outward or spiral inward, depending on complex gravitational interactions. Beyond the destruction of Earth as a habitable world, the matter that makes up our planet will continue its cosmic journey. When the Sun eventually collapses into a white dwarf, the remnants of Earth, its atoms, minerals, and elements may drift into space, becoming part of interstellar dust that seeds new stars and planets. Just as Earth formed from the debris of earlier stars, future worlds may form from the remains of our own. But despite these distant cosmic fates, the story of Earth's immediate future remains unwritten. Humanity holds unprecedented power to influence the next chapter, to preserve biodiversity, stabilize climate systems, and repair ecological damage, or to push the planet toward further instability. The choices humans make now will echo for thousands, millions, or even billions of years. The future of Earth is a blend of natural forces and human decisions. It spans from the next storm season to the next ice age, from continental drift to the Sun's eventual expansion. And though the planet will continue evolving long after humans are gone, the present moment represents a unique intersection where one species can consciously shape the fate of an entire world. Earth's story is not yet finished. Its future will unfold through cycles of change, destruction, creation, and renewal, just as it has for billions of years. And within that future lies the legacy of humanity, a species capable of both great harm and extraordinary preservation.